It's
Okay, now.
starting. I will paste the link in the chat.
Yes, please. Okay.
Pablo? No.
Yes.
You didn't send me the introduction, but I
Really?
can
Okay.
say the...
I will paste the link in the chat.
I send it to you. Natalia Rodriguez, Diaz Rodriguez.
No,
And Paris. I resend it to the Gmail?
Yes, please. I didn't get it.
Okay.
I mean, did you just send the schedule that you sent earlier, or? That's the only thing I got. But that's not new.
Okay.
So YouTube is working. YouTube broadcast is working.
Okay, that's working. So I will actually put it in.
Natalia, you can change your name because you're connected with my account again.
Okay.
Holy shit, I have to put it in the. Okay, I start everything, all right?
I think we have 57 in the waiting room.
I accept everybody.
Okay.
Yes.
Now we'll explode.
You should ask them to turn off the camera.
Mm-hmm.
Hello, guys. It's Mehdi Kamasi.
Mehdi.
Hello.
How are you?
Hello, Mehdi.
We have still people in the waiting room.
Yeah.
So how can we?
I'm accepting everybody.
I think, can you ask one of the students to take care of the waiting rooms? Maybe
No, they cannot do it. They have to be co-host. Okay.
But David change maybe that so
No,
that
I did not change. Natalia, you can. I think you can do it in the security option. You can deactivate the waiting room.
Okay, enable waiting room. I will deactivate. Okay.
Okay.
It's done.
Perfect.
So now people don't have to.
Well, we have people from everywhere in the world. I can see it in the chat. Oh my God. From Melbourne, from Paris, Philadelphia, San Diego, Glasgow, India. Well, I think, I don't know what time is it right now in United States, but I think it's really early in the morning. So yes, we have to be starting a little bit. Welcome everybody to the BRAIN-PIL workshop. So actually it's brain-inspired perception, interaction and learning with the focus on robotics. And we want to thank you, everybody, all the participants that they will start getting inside. We have more than 250 registrations for the Zoom, and this is also being streaming live in YouTube. If you want to see that somebody actually cannot access to the Zoom but wants to see the workshop, they can access in here in the YouTube channel, right? And well, we have a session that is a workshop that we are really happy to have it. We have amazing speakers and amazing contributions. We never expect how successful is going to be the workshop today on a Sunday. And really thank you everybody for coming today. We will have peak hours with some speakers and less peak hours with some participants, but we want that this is a workshop, it's not a conference. So we will try to, even if it's virtual, to don't have this everything frontal, so there is some kind of discussion and you can actually put your questions. The organizers that we did this happened is below in this slide that I'm sharing. Pablo, but also with me is Mohsen Kaboli, Natalia Diaz Rodriguez, David Filiat, and Tansu Selikel. And we are really happy to have you here. We also will have two people helping in the chat that maybe they can write something in the chat to say hi. So if you have any problem or something, you can always ask them. It's Jansu and Guillermo helping, and well, I'm just talking a little bit so the people are joining and then we can start. Hello, everybody. Hello, Jansu. Perfect. So maybe we were going to also put the hello from China. We have people in China, United States, Europe. Still waiting somebody from Africa, will be super nice. This is the two people that will actually ask, helped in the chat. One important question for the discussion, we will repeat it again afterwards, is that if you want to make a question, you can put it in the chat. But if you want to go to the stage and ask the question with live to the speaker, you will have to raise your hand. How to raise your hand? You just click on your participant, and then you actually more, or maybe you have in the down part, you have something that says raise hand. And with that, we can see that you raise it, the hand, and we will select one of the questions, and then you can ask the question. But I will repeat this more and more and more. So welcome again to the BRAIN-PIL workshop that belongs to ICRA. Unfortunately, that's why I put it a mask on the robot here in Paris. We are not in Paris. We cannot go there and talk and chat closely. It's unfortunate. And we cannot go afterwards to have something, to have a beer. But the good thing is that this is kind of open and everybody can connect from everywhere in the world. I will start already here. It is 11 in the Netherlands that I'm right now, in Paris also, and in Germany, that we are the ones that we are organizing this workshop for you. And so we have these amazing speakers today in the workshop. I'm really happy about this. These are really top people, and we are really thank you that they are joining us today. And I'm really looking forward what they have to tell us about the state of the art in brain-inspired learning, perception, and robotics. We have blocks, okay? The first block, well, right now we are doing the welcome, that we will present ourselves as organizers. And then we will have the first block will be at 11:30 with Jun Tani and Johnny Dambre, that we will have a kind of a mixed interdisciplinary approach to neurorobotics, plus 3 really amazing contributions to the workshop. Then we will have a second block at 1 o'clock that will be more robotics hardcore, but also with a biological inspiration. Like for instance, Oike will actually talk about controlling locomotion. Then we have the third block that we will more neuroscience approach, where we have Mehdi Kamasi and Matthew Botnick, that I'm really looking forward those talks. And in the end, we will close with the close to the sensors with and the body with Fumiya and Ravinda, that they will talk also about soft robotics and tactile. So anyway, and at the end, the people that resist, you will be able to access the contributions and ask the contribution speakers all the questions that you have, share your experience, and so forth. For the poster session, we will bring, after in some minutes, in some hours, we will bring the list of the Zoom links that you have to click if you like one of the posters and access. Actually, you can access all the posters. Good. Anyway, I wanted to say before we start, two important things that I think that these are really important. The first one is organizers, but the most important one, this is the Twitter. We want to use BRAIN-PIL as the hashtag. If you want to say something, put it BRAIN-PIL. We are also attached to the ICRA Twitter account, and it is streaming on YouTube. I already put it. Maybe it's one of the chat helpers can put a streaming again, so the people can actually present to the people that they want to see, but they don't have a registration link. Good. So now we go to the organizers. I feel like, I have to say that I feel like I'm talking to nobody. So sometimes I just talk and talk. So if other of my co-organizer wants to also to talk and say something, they can always say it, because this is a workshop. This is not a conference. We want to make it more relaxed, more interactive. But let's talk about organizing then. So we have, I will start with David Filiat, that actually is hosting us with the Zoom. So if any technical situation happens, it's his fault, not the rest. No, I'm kidding. I mean, this is I think it will be really good. Thank you, David, for helping in the organization. And maybe, David, you want to come to the stage and say some words about you?
Yes, thank you, Pablo. Hello, everybody. So indeed, I did not play the biggest role in this organization. So I want to thank all the co-organizers for doing most of the job. So just a few words about me, just to put this into perspective in the workshop organization. So I'm mostly coming from robotics and working on robotics and machine learning since a bit of the beginning. The beginning of my career, I was working mostly on navigation for mobile robots with some biological inspiration. And then recently, I've turned more and more to machine learning for robotics, applied to computer vision, navigation, reinforcement learning, and things like that around mobile robots or humanoid robots. And just a few words about the context. So I'm with Natalia. We are part of a laboratory in France. It's situated in Palaiseau in the south of Paris. We belong to an engineering school in the south of Paris, which is called ENSTA, E-N-S-T-A. So ENSTA Paris is a very general engineering school with a lot of different areas for the students, and one of them is robotics. So I run a lab in ENSTA, which is called a Computer Science and System Engineering Laboratory. It's quite a medium-sized lab. We are 50 people, counting PhD students, postdoc, and everybody, and the researchers. And so we belong to a team which is called Autonomous Systems and Robotics, with three main research areas. One of them is on the design of system and the safety of system, mostly applied to robotics and autonomous vehicles. Another one is on computer vision with a focus on an embedded vision. So with real-time computer vision and image processing. And the third one is about what we call cognitive robotics, which would be called artificial intelligence for robotics, maybe at the moment. So it's mostly working on navigation, computer vision, human-robot interaction, and machine learning for robotics. And on this particular subject, we have a joint team with a French organization, which is called INRIA. So INRIA runs a lot of different research teams all around France. And we have a joint team with them, which is called the Flowers team. So it's run by Pierre-Yves Houdeillet. The team, the main part of the team is located in the south of France, in Bordeaux. But me, Natalia, and another colleague, Mai, are members of this team also. And the INRIA Flowers team is working on developmental robotics. So maybe you know about Pierre-Yves working mostly on curiosity, explorations, and we are working on a related topic with him and other members. So that's it for introduction. I will give the floor to Natalia just to say a few words about her.
Hello, everyone. Yes, I am assistant professor with David in the same lab, and since I've been there since 2017, and I've been mainly focused on computer vision applications for robotics, deep learning, reinforcement learning, and neural symbolic learning and reasoning with visual and language models, with the aim of helping autonomous agents to learn autonomously, more concretely with state representation learning to make reinforcement learning more efficient, continual and lifelong learning, open-ended domains. We have collaborated with, we are currently collaborating in projects with Renault and Segula Technologies, other companies, and Sorbonne University working on explainability and trying to make deep learning more explainable for different audiences. So yes, this is about me. And I want to thank Pablo, Mosen, everyone, especially Pablo, who has done a perfect planning and has done a lot of the work and all the attention to all the details. So I hope you enjoy, and I'm also very excited to learn about all of you and discuss further.
Thank you, Natalia. Yeah, actually the details are something interesting in this kind of events that actually goes against our health stress of life. So, okay, I will say something because unfortunately, other organizing here, that is Tansu Selikel, that is a director of the DCC of the Donders Institute for Brain and Cognition, cannot be here today for personal reasons. And I want to say some words about it. So two organizers from here, we belongs to the Donders Institute, that maybe for the neuroscience community, this is known, but for the robotics community, this is kind of unknown sometimes, because it is more related to brain research, right? And actually the core thing of the Donders Institute is to understand the mechanisms that underpins human cognition and behavior, and also for health and for disease. And actually, it's also the Donders Institute works also with the hospital that is in the Radboud University in the Netherlands. And it is more related not only to the intelligence system itself, but also to the human part, human science part. Okay. And I want to go a little bit deeper in here, because what we do is actually to try to address from molecules to minds. And we apply AI in all the scales, and we try to understand how the neurons works, how animals models works, how we can go to social science, how we can go to directly to the patients and to the behavior, and for sure to the human behavior. I want to stop in me. This was short actually for explaining the Donders, but you can always access to the website that is in here in the Donders in the Radboud University. I will stop with me. I'm just started as assistant professor in cognitive AI at the Donders Institute, and I'm working in this lab where we actually do these two ways that I really love, and that's why also this workshop is actually really fitting, is that we try to understand the computational principles that are under the brain, under natural intelligence, And we want to use these principles to actually build better intelligent machines. And in this loop is where we move, and this loop, this interdisciplinary aspect is where the workshop is working. But also we need the robotic side, because if not, how we can put all this theory into the machines that we will use also in this industry and in other places or with the humans. And for that, I want to actually ask Mohsen to also say something about himself, because we have a company also involved in this workshop. So it's not only academia, and this is also really good to have it. So please, Mohsen.
So thank you very much, Pablo. Then I will just share the screen from here. Yeah, I hope you can see here the. Okay, so hello everybody. I'm Mohsen Kaboli. I'm a senior research scientist at the BMW Group Research. So maybe you know already about the BMW and BMW products, but you should know also at the BMW we have research, very big research departments. Almost 20,000 people at the BMW are working in research and R&D. And last year, we initiated the BMW Center of Excellence in Robotics, Artificial Intelligence, and Cognitive Systems. Basically, we do research, applied research in these three areas. And we are having almost 300 PhD students there, working on especially machine learning, artificial intelligence. And the main direction I can show you here is, if you see here, we are working on autonomous driving. And you know that BMW has the most number of robots in the production line and the other head units. So we are dealing with a lot of issues and problems related to the manipulation and industrialization. So we are bringing a machine learning and AI to solve these problems. And also you will see the other activities at the BMW. And the main direction at the moment related to the products is autonomous driving, and which we have almost 600, 700 researchers in this area. And basically, I'm from the department which we do the research, innovation, and new technology. And we are focusing on interiors of the vehicles and also the robotics. When it comes to the robotics, basically we work on human-robot collaboration and collaborative robots. For the human-robot collaboration, we are considering the sense of touch and vision in order to bring the safety. And when it comes, for example, to manipulation, we try to find out how we can manipulate the deformable objects or like a transparent object using both touch and also the vision. The other direction is which we are working on to make the interiors of the vehicles intelligent, or we call it cognitive vehicle, and to make the interiors like a robotized. Means the interior of the vehicle will be will be reconfigurable, can be like a living room, can be the office, and you can interact with the vehicles via different sensing modalities. Vision, touch, as well as also the audio. And my focus at the moment for the interior vehicles is the touch. I can show you just small videos here. We would like to find out how you can bring the sense of touch to the vehicles. Everywhere in the vehicle will be touchable. You can touch it, you can interact, and you can communicate, which we call it also the touchable vehicle, and you can get also feedback while you are communicating with the vehicles. So I would like to stop here because we don't have enough time. But as I said, we have very close collaboration with the universities. We have many internal funded projects, internal funded PhD students, and we have also external funded, like EU funded projects. We have several Mercury ITM projects, which at the moment we have several open positions for the PhD, and we would like to, now we are hiring. If you're interested to work at the BMW, and I would encourage you to either send me like informal CV, or you can go to the BMW website. And the PhDs are also involved or engaged to the top universities. For example, my PhD is now engaged to the Imperial College London, Cambridge, as well as University of Glasgow and TU. So I would like to stop here, and then I will give it back to Pablo and Natalia in order to have our speaker here.
Yes, we can see that industry has more meanings to sell themselves. Academics, we are so humble sometimes. It's good to have somebody that actually sells something really good. Thank you, Mohsen, for this amazing presentation. I think we are kind of ready for starting, because maybe the people didn't come to actually listen to us, but they come to listen to the speakers. So we will have the first one, I think, that will chair by Natalia. I think everybody can see the schedule, right? We are streaming. By the way, we are going to record the sessions, so be aware that this will be recorded for the posterity, and that is also good. We are in the BRAIN-PIL workshop at ICRA 2020. It is actually 11:29 in Paris time, also Netherlands and Berlin. What else? Everybody's ready here. So I will actually ask the first speaker that we have, and also Natalia, to present him, if you can. And thank you everybody for coming here. You always can see also this in YouTube. After the two speakers, we'll have two speakers, and then we have an interactive session that you can ask questions, put the question that you want in the chat, and then also remember to raise the hand in the end to select the questions. And afterwards, these two talks, we will have the contributions here that please don't miss it, because they are actually really interesting. So please, Natalia, go ahead. Is somebody recording the session?
Oops. No.
Can you record the session, please?
Okay, I started recording.
Oh, perfect.
Okay.
So, sorry to say again, because this is recording. Welcome again to the virtual workshop of BRAIN-PIL, ICRA 2020. We start the first session. That chaired by Natalia. Please, Natalia, go ahead.
Okay, hello everyone again. So we start with the first block of very interesting speakers. The first one is going to be Jung Tani. While he starts maybe preparing, I will do a brief introduction. So Jung Tani is a full professor at the Cognitive Neurorobotics Research Unit in the Okinawa Institute of Science and Technology, Graduate University, OIST in Japan. He's also author of the book Exploring Robotic Minds, Action, Symbols, and Consciousness as Self-Organizing Dynamic Phenomena. And he's going to speak about cognitive neurorobotics, a study using predictive coding and active inference framework. I'm looking forward to hear about what we have to learn today. So please, if you have any questions, raise your hand through the Zoom option. We will have about 15 minutes discussion at the end of the session. So you can at least write it down for now, or write it in the chat also. So yes, please, Jung, when you are ready, you can start sharing. Welcome.
Okay, yeah. Can I share now?
Yes.
Okay. Ah, okay. Just wait. Okay, do you see the screen, right?
Not yet.
Yes.
Now, yes.
Yeah, okay. Okay, great. Yeah, thank you very much for inviting me to a really exciting workshops. I actually wanted to go there physically, but this time so we cannot do that. So, but anyway, so yeah, so I'm now in Okinawa, and maybe, yeah, it's a lot of, can you see the ocean from my window? No? Can you see?
Yes.
That's,
Yes, very nice.
Yeah, we can see that.
yeah, right. So now almost sunset, so coming. So yeah, I'm actually living in a house in the campus. So that's a beautiful place. So I'm back my camera. Okay. Okay, it should be okay. So, okay, so today I like to talk about predicting the active inference framework. Actually, I have been working a long time, yeah, 20 years. So for this subject. So, okay, so then first I'm going to introduce what's predicting active inference is briefly. So then the predicting is something like a principle for the perception. So that started from the Helmholtz days, but these days very famous because of Friston, the other people making this kind of things very the people starts to, you know, be attracted. The idea is something like we have a top-down sensory prediction or expectation, that we have a bottom-up reality, and we want to make the error between the expectation and the reality by changing the latent state variable internal state. So that's the maybe free minimization or prediction error minimization. So that the error is minimized, so then perception is achieved. So and the active inference is a relatively recent one, especially discussed by the Friston. So that is for the action generation. The idea is that, again, this is something like I try to make the error between the predicted sensation, the actual one, but by generating adequately acting on the environment, by acting, and the error is minimized. So that's two things. Actually, those two are not separated process. So then I have been working something analogous to those framework, and then especially the using more application to the robots using recurrent neural network, and the recurrent neural network somehow organized in a hierarchical one. So then I'm going to explain that. So that one. So then first is about predict coding idea. So that is something like we have a prior intention in a higher level here. Then we have a prediction or expectation. So both exteroception and the exteroception, something like a vision. We have a predicting, and then we have a reality from the environment. If you got error is propagating. And through the propagation, I actually have used the backprop for a long time, but by using error signal propagate there, each layer, the intentions, latent variable is changed so as to minimizing the error. Then error is minimized, so then that means that actually recognizing the sensation, perception is achieved. So, and then, so that is predict coding, and of course, and then you can learn it. Is not only changing latent state, but simultaneously synaptic ways updated in the direction of minimizing the error. So that is actually learning process. So then we think about active inference. So active inference is something to do with action generation together with perception. So then we have again the intention is higher level, and it's going to be the anticipate for both the vision, exteroception, and proprioception. Proprioception is actually joint angle kind of things for the robotists. So then we're going to predict, then predicting in the joint angle, and that is actually targets to the controller. So then the putting the targets to the controller, and then motor command is generating, and then acting on the environment, actually the state in the environment is changed. So you got the sensation, both proprioception and the exteroception. The proprioception is actually real joint angle of the robot. You might have some kind of error, but this is something like PID, error feedback control, and actually motor is modified in the direction of minimizing the errors. That is something like a active inference part. But there are other way of thinking active inference exists, but I'm kind of talking about the basics or maybe easy example. So then, but still we might be have the error. Both this is a proprioception and exteroception. The error is still in propagating back, and then this in a prior change. So that's the posterior change. So then actually we have two things to be changed, possibly changed. One is environmental state, the other is internal, it's latent space. So then which is going to be more changed? That depends on the strength of the prior. And so that is the other issue. Today I don't discuss that part, but that something like a balance between how much prior is strong. Prior strong means that how sharp the distribution of the, how narrow the sigma, but I don't go that discussion today. So then the active inference actually, but okay, so this is a famous paper by the Preston and actually understanding the active inference. And he sent me the paper, the preprint to me about 10 years ago, and then it's written that the idea in this article can be regarded as a generic Bayesian perspective on the connectionist scheme introduced by Tani 2003, Tani 2004, or something like that. So then I learned that what I have been doing is something called active inference. But the difference is that, so as he said, his approach is Bayesian, but my approach has been long time kind of a deterministic recurrent network. But I think that Friston, what he did is more general because it's the Bayesian perspective. So, but that part I cannot tell so much today. So anyway, so but my old work related to the predicoding, something schema related to predicoding active inference. And recently I wrote a book, and then if you are interested, please look at this. Okay. So, and then today, I like to talk about our recent project on active inference, especially about goal-directed planning and for something to do with the visual mental simulation. So that was my student mainly done in Jung. Okay, so then something idea is something like that. So we are using this arm type robot to think that, so we have a initial block configuration. We have this red one, blue one, green one here. Then robot is asked. So this is the goal. So visually shown, this is the goal stage robot have to achieve. Then robot have to make the visual planning. What should I do? So then what he should do is putting the blue one to here and the red one here, the mental image generated, that one the visual trajectory as well as the proprioceptive trajectory generated, then in the mental planning, and this can be done. So then this is another configuration, and the robot might be asked that you have to generate this tower, then another mental image achieve this kind of a power, and this is another one. So then what we do is that so goal-directed planning is conducted after learning of a set of the tutored perceptual experience for manipulating objects in the various configurations. That is the first we do the training, tutoring a robot for the many way of manipulating objects, like a 200 trajectory. After enough training them, then we ask something like a novel goal, like shown like this. Then how a robot can do it. So that is a task setting. So then we have a focus. The first focus is the goal-directed planning by the active inference. that is something like a planning in the latent space instead of the motor space. That's kind of thing that many other people, including myself, have been working. So recently, the Hafner, the planet is also one famous example. Also, at the development, we kind of, this is visual things and the visual thing, but we have not, it's not wise to manipulate to plain vision, but rather we have to better to use visual attention or visual working memory, writing to the visual working memory, reading those things. I'm actually quite inspired by the draw architecture shown by the Gregor and several years ago. So actually, but we are applying something similar, analogous way of thinking to the robot planning and active inference. So, and then, but the most important things, I'm not kind of selling our architecture, rather than we want to report some emergent phenomena which we found through our robotics experiment. So that is not we have designed. So it's a phenomena itself is something comes out. That was kind of interesting, and also something related to the developmental psychology. So that's why. So we'd like to report this. So okay. So then maybe we start with goal direct planning. But the prior studies, many studies use forward model. So that is something like we have the motor is inputted, and then the vision is inputted, then predict next vision. So that is a forward model idea, right? So and then this is a time. So okay, then if you provide distal goal image is given like this, how I can achieve it? Then you got error coming. And then minimizing error, then you're gonna kind of optimizing this motor sequence for the minimizing the this error. Then if the error minimized, the goal can be achieved. That is a conventional idea. Use something the forward model. However, the problem is that such place for the motor plan could be very huge. Depend if with the motor dimension is increased. The also more big problem is that as arbitrary motor inputs, so when you kind of predicting vision, but this part of the motor pattern can be put arbitrary motor input can be given. Therefore, some fake plan of never experienced, the fake plan with the unrealistic visual image could be also generated. That is a problem of the using the conventional forward model. Then what we should do is something like the planning in a latent space. That is, so maybe so what does it mean? So I'm going to explain that one. So then this is kind of the times goes this way, and this is a lower level latent space activity, middle and higher, and then this is going to be is predicting the visual perceptive sequence. Okay, so then we have something like initial states, and then that one is represented by the mean and sigma. So then we provide goal image here. So this is something that's a predicted model from the initial states to the, so it's going to be actually hierarchical organization and predicting visual process sequence, but that prediction can be made through the learning. So, and then if it can predict, that means that if we provide a goal image, and then what you currently have. So if you have the error is propagating, and then actually try to minimize by iterating this latent state variable, that is initial state variable. So then if you find the optimal latent state, that initial state variable of this one, then you can achieve the goal. That's minimizing the error, and the sequence of visual process sequence can be generated. So the good thing is that such spaces can be confined in a latent space, in the vector space, And also the search space is quite confined in the motor space of well habituated. So that is it's not we are doing the planning in this motor space, but rather latent space, and it already have trained well for the many trajectory. So therefore it can generate a plan for the well habituated. Therefore, we don't have so much fake motor plan. So that is goodness of using latent space planning. Okay. So then next is the development of visual attention, the visual working memory for the visual goal direct planning. So that is the idea is that, as I told, that is inspired by the draw. And then the one important thing is that the development of a visual attention mechanism, the learning where to attend without explicit teaching, and also development of adequate use of visual working memory, learning to what to read and what to write when into the working memory without explicit teaching. So then I'm going to explain the first that the visual attention, the working memory part. So that is we have a LSTM, and then we have kind of a current visual inputs 64 by 64, and then it's going to predict one is peripheral vision of 32, 32. The other is something like a focused vision and the centered one, and the 32, 32 along, and it's going to along with the attention parameter, that is where to attend, what kind of scale. And those attention parameter is generated by LSTM. Then we are going to synthesize next time prediction of 64, 64 by the kind of a pasting these two things together to here. Okay, so prediction, so merge prediction of a peripheral and central one is merged to here. Then we're gonna have the background working memory, that is very important. And then some masked part of this image, which part is masked is coming from the LSTM, saying that this part is going to be saved here. Okay. So then we have and this part is kind of saved and or erased. So then we're gonna have the image in the working memory can be okay, preserved, erased. Then we're gonna have the masking, and then this part of the working memory, visual working part, this part of the current prediction, these two things is maybe put into here. This is the actual final visual prediction output. So that is a lot of the process, but it's focusing on or putting something in the working memory. But what has to be put on the working memory, those things are completely determined by LSTM through the learning. So the important thing is that all these mechanisms can be self-organized by means of synaptic changes in the network with prediction error minimization. So and this can be done because the whole network is differentiable. So then this is a whole architecture. So then we have a LSTM, the layer of stacked LSTM, the dorsal part and ventral part. And this part is, I already explained about the attention, the visual working memory part. But basically what we're going to do is something like this part of the LSTM generating this dorsal part is kind of predicting peripheral vision, as I told you. The other, and then maybe proprioception, that is the motor ones predicted. And then this is something like a central vision part is predicted for the ventral, and the attention vector together. And a lot of the masking also predicted. So then, but what we do is something that is again, initial state we have here. So then it's going to predict sequence of the motor as well as a sequence of visual frame, right? So like the 100 for the one trajectory. So this one, and we have to minimizing the error then all the functionality is determined through the learning. So let's see the example after good training of 200 trajectory. And then now we see that this is initial image. So that the robot is now looking. The camera is something, I'm not sure how, but is in front, the camera in front of the arm. So the robot is actually looking where the object is here, and then show the robot. This is your goal. You have to achieve this one. Okay. So then the then the first is what kind of visual plan or visual image generated for the achieving by the network. So this is a final sequence of visual prediction. So yeah, actually that is you see that is in the goal achieving image generated. This is not physical one. Actually, network generate this kind of image. And let's look at the attention part. So it looks like system is attending to whatever the grasping the object as attention go there. That is a good strategy, I think. And the very, very interesting part is the background, the working memory. So this one. So what kind of image is stored? I will show something I think interesting, right? First is that the robot is not shown there. Once again, but when object moved and that one is appear there. So it's not, it's kind of the important event is stored, like green one is now put on the blue, and now red one is put on the green. So something event like things, but something sequence of a static image is stored, it's kind of is processing. And we don't see is a movement itself, like a robot hand is moving. That's why it's not shown there. So this is the final one, physical one. After the plan is generated, they ask the robots to generate plan. Actually, just one. Okay. So the emergence, what we got is, so one thing is that so this is okay, particular goal given to the robot in the starting point, and this is actually the how it goes, right? So then this is the working memory part. Okay, so then you see that when the hand go there here, you cannot see it. You can see it, but the working memory part is that you see it. So the system is actually can see it, what is there. So that is important information. That is something stored in the working memory. So then something emergence is something like the concept of object constancy was captured. So when you don't move the object is there. That idea is somehow developed. The other things is something to do with sensory attenuation for the self-generated action was observed. So that is, yeah, Brakeman and other people talking about sensation originated from the own behavior action is kind of attenuated, but that kind of things was observed in working memory. Okay, so then we did a little bit more. So that is one of my postdoc come up a question like how to deal with unseen objects. Like we have done like teaching like red, the blue, and green, and it's successful. However, if you introduce a new one like the purple one, can robot do it? And then so okay, so that is something like in generated models such as usual recurrent neural networks, contents and the function for manipulating them are often inseparable. So if we train the recurrent network, it's kind of the video image processing, that's kind of thing, something in a trained one object, the color of the red one, and blue and green, those things are okay. But if you ask the network to do with new color things, it's impossible to do that. That is because it's the information processing of the recurrent network or generative model. The contents and the functional manipulation are not separated. So, but that's good things for the connectionist things, but sometimes not good. So compositionality for something like that. So then what he considered is that adding the new working memory prefrontal, it's like, okay, so anyway, so adding another working memory. Okay. Then what happens is something like this is already trained one, okay, but this is a purple one, but it can be done. So actually, this one is second working memory. So it's kind of the object is moved and that kind of transformation image is generated, but that it can be done not only for the round object, but it's a new one. It is also possible. So this is another one, and the orange one never learned about it, but it can do that. So what's happening here is that it looks like is a working memory part is something like when the object starts to move, it's copied, masked copy to the working memory. And this part is doing something like a affine transformation like things goes on, but that type of the transformation is parameterized by the LSTM. LSTM is sending the sequence of parameter, and that one is fed into the this one, and then affine transformation kind of thing is done. So now what we see is that the contents with different colors, in this case, the function for manipulating them, that image transformation are developed as separable by using two working memory things. So imagine the phenomena observed today is something like in this experiment. First is autonomous development, the visual attention, and the visual attention to intended action. The meaningful image contents were preserved in the first working memory as segmented from visual flow. So then that is sensory attenuation for self-generated action and preserving the occluded image by developing sense of object constancy. The final second experiment showed that by introducing second working memory, some non-trivial information processing mechanisms developed, such as like a separation of the contents and the function of manipulating them. Okay, so that is all the things I like to talk today. So I like to finish my talk now. Thank you.
Thank you, Jung, for your talk. If people have questions, can please raise your hand in Zoom. Okay, Manfred Epp is having a question. Please go ahead.
Yeah, hello, can you hear me?
Yes.
Yeah.
Okay, great. So Yun, thanks for the talk. That was really great. I have a question to the active inference and the minimization of free energy. So as far as I know, Friston says that the forward model should minimize the free energy, which implies to select actions that are in such a way that the forward model doesn't violate the actions. But shouldn't it be the other way around, that actions are selected to maximize the prediction error, so to learn the most for the forward model? Can you say something on your perspective on this?
I'm not so much catching what you said. The first is it's a bit, as I told you, it's a bit different from the standard forward model, right? So because standard forward model is the motor sequence is input, right? And then, but we don't have motor input, so. But maybe that is a minor difference. But I couldn't get the question. What is the essential part of your question?
Okay. So in order
Yes.
so you have this forward model, and you're trying to you look at the prediction errors, right? And then you select.
So maybe I show you the stop. I show you the slide of that part, and then
yes.
it may be more clear to understand your question. Okay, so this is something like yeah. Okay, please continue.
Okay, so how do you select the actions with respect? So how do the prediction errors influence the action perception? This
okay, so that is, we don't select action, but we are changing the latent variable. So that is, but actually in this case, the initial state of the latent variable. Then, so then we are using something like initial sensitivity characteristic of the recurrent network. So maybe something like context units. If you determine context units of initial step and all the sequence is determined, that's including the output of the visual proprioception. The proprioception, once you do, proprioception is almost like a motor command because that is joint angle is right. So, but actually not motor command, but the motor command is that part is something PID controllers doing. So that is part. In this case, active impedance is the sub parts. More I would say so.
Okay.
Yeah. But once you determine sequence of proprioception, that is mapped for the latent variable of each time step. So then the motor sequence can be determined, but searched in the latent space. But you can do other is this because this is deterministical network, and then if you the recently we are doing that we are random variable also here. So then we're gonna plan for the not only initial state, but all the steps we're gonna plan for this latent variable. That is also possible, but that should be better. Yeah.
Okay, I think I got it. I think I should look at your papers then again. But thanks a lot.
Thank you.
Okay, great.
Okay, maybe I have another question regarding compositionality, which is something that is being assessed in deep learning models now. Is there any model, any quantitative way to assess how compositionality emerges? Or is this an invariant property that we should look at, or how is it properly assessed? Maybe you can tell a bit more about it.
Okay, so then maybe this is not good. It's not good. This current study may not be so good to look at the compositionality. But if you look at our old work in like a multiple time scale recurrent neural network, and then we show that set of the primitives. So its learning is done by the continuous sensory motor sequence repeatedly. But if there are some kind of a minimal set of the primitive, then network is going to segment them to the set of the primitive. The higher level starts to manipulate them. Then we can assess like if we ask the robots to adapt to the new combination. So then it looks like a robot is kind of successful for manipulating the compositional way of manipulating the primitive. But it's not so mathematically way of, it's not so much mathematically rigid way of saying. So, but we used to work on that in that way. So in the old days.
Okay, thank you.
Yeah, maybe you might look at my book, and I wrote a lot about that.
Yes. Okay, so maybe we proceed with the next talk.
Thank you very much.
Thank you.
Thank you.
Thank you very much, Jung. It was very interesting. I just want to say that people can still interact and ask more questions maybe at the end of this session.
Yeah, I know.
So thank you very much.
Yes,
and
Natalia, let me say one thing beforehand. So I'm writing in the chat, people can actually answer in the chat the questions if they think that they have an answer for the questions, or to explain more what they think about it. So they can always the chat. I'm writing some ideas also in the chat so the people can think about it as well, okay, for the discussion afterwards. Sorry for an interruption.
Okay, no problem. So we will move on with the next talk, which is Joni Damr. While she can start perhaps sharing her screen, I will briefly introduce her. Joni Damra, yes, is here? Yes, okay. Okay.
I cannot
Okay.
share my screen at
Yes,
the
yes,
moment.
please go ahead. So Joni Damre holds a PhD in computer science and engineering from Ghent University, and she is full professor at the same university in Ghent. And after working on digital hardware, she made a successful shift towards machine learning and neural networks and became full-time tenured professor. Her work covers a broad spectrum on interconnected topics related to machine learning, deep learning, and embedded implementations thereof, and robotics and brain-inspired computing and conventional computing. And her talk is going to be integrating biological insights into practical AI, a pragmatic viewpoint. And thank you very much, Joni, for being here with us. The stage is yours.
Okay, can you hear me?
Yes.
Okay, good. So yes, thank you for the introduction. Maybe just a very short introduction of who we are, because I don't only speak for myself. So I'm Joni Damre, and I'm part of a research team with two colleague professors, Professor Wijfels and Professor Belpame at Ghent University, and also affiliated with IMEC. Now, what we do is a mixture of all kinds of things. What we definitely are not is a neuroscience lab. So we started off in machine learning, moving on to brain-inspired hardware, also doing robotics, both robot design and robot control. And we also work in computer science education. So some of the recent topics we've been working on, as you can see, they are very broad. In the pure deep learning side, we work on things like sign language understanding. We also work on things to do with robotics and with the brain-body co-optimization, trying to optimally exploit physical computing by changing the body morphology, by introducing compliance. And actually there we also have some nice recent results where we finally managed to show quantitatively that there is a sort of ideal range of compliance between very stiff and very compliant, where ideal means easy or the most easy to control, and also good with respect to power consumption, etc. So these are some of the things that we do. We also do social robotics, that we study non-verbal communication between humans and robots. We work on resource-efficient computing and learning, so all kinds of things. Now, my talk today will be focused mostly on the use of self-organization in deep learning workflows. So some time ago, some people in the audience will probably remember this, the question was asked to a larger audience, of which I was part, how can biology and neuroscience help AI? And how could it bring us closer to robots, say autonomous agents? Now, as I said, I am a computer science engineer, and from my perspective, there are a lot of questions still. So what exactly can we do with neuroscience-based techniques? Can it increase accuracy? Can it improve power efficiency? Can it make robotics cheaper? Can it help us achieve useful results faster? And most of all, how can we quantify this? How can we evaluate the technologies that exist? Now, I've been around in neuroscience contexts for a while, starting with the beginning of the Human Brain Project. I've seen lots of very interesting things, lots of impressive results, but they're all very fragmented. So let's start from my perspective, as this is the stuff we all know. Recent AI progress is still largely dominated by deep learning, which is sort of a hype and backpropagation, and it works amazingly well for well-defined tasks, usually single tasks or sets of tasks that are closely related, and most often on well-defined and monomodal data that ideally follows the IID assumptions. Now that is well known, that is now being exploited by industry to an increasing extent. But when it gets more complex, and when you start to think about using multimodal data, using physical agents, things that operate in the real world in real time, then end-to-end learning and deep learning break down really quickly. And one of the main causes of that is the fact that the data needs and the compute needs for training really become unmanageable. And so the learning convergence also, when we look, for example, at reinforcement learning in the physical world, you see robots trying to do the same tasks for huge amounts of time, or lots of parallel robots trying to do that. So this needs huge computing resources and huge amounts of data. So in short, deep learning is data hungry, compute hungry, and also power hungry. You almost need a power plant next to your GPU center if you want to do Google level kinds of research. So what is our ultimate dream? Since this workshop is linked to ICRA, I'll focus a little bit on robots. So in robotics, the data ideally is multimodal. You have multiple sensors, you have proprioception, you want to integrate all of that into your agent. You are working in the physical world, which means that your data is going to be noisy, it's probably going to be non-stationary, and there's going to be a lot of variability. So there's no way you're going to be able to sample all the possible occurrences of variability during training. You will be having large data imbalance. There will be lots of common events which are not really interesting, and there will also be unexpected, rare events, or even totally unseen situations. An important thing that is very often not present in traditional deep learning, that is that physical agents operate in continuous time. So you do not randomly shuffle your data, you just have to learn from the data as it comes. So what we really want is physical agents that can do what we can do, but can do it better, and ideally also more reliably. In addition, we want it to be affordable. So we want to be the hardware to be affordable, both the mechanical hardware and the compute hardware. And we also want this thing to consume as little power as possible. So that's sort of the holy grail. But besides from that, because we definitely aren't there yet, and won't be, I think, in quite a few years, but there are a lot of simpler problems in AI that could also benefit from new perspectives, which I hope to find also in neuroscience. So this is what is often claimed. So biologically inspired can solve a lot of things. We can base ourselves on biological brains, biological bodies, because of course there are a lot of similarities. Our biological bodies and brains are highly optimized results of a constrained co-evolution. And they are sort of targeted to meet many of the requirements in robotics, which is sort of evident because we are creating robotics more or less in our own image, and also to operate in our own world. But is this exactly what we need? Because biological brains and brain-body interaction are still very partially understood. So we know principles, I see fragments, I see very nice examples like the previous talk about certain aspects of biological inspiration being used in robotics. But there's still a lot we don't understand. In addition, the biological brains and bodies are optimized or have been optimized in a very long process for a totally different material system. So in robotics, in computing, in AI, we're usually using GPUs. So we're working with GPUs, which means digital computing, which means discretized time and discretized numbers. And in addition, our brains and bodies have been optimized for a different goal than what we usually expect from AI. As the goal there is survival of the species. This means that anything you do needs to be good enough, but it does not have to be high precision as we often expect from AI. So for these reasons, I think we have to be careful when claiming that neurobiology or neuroscience can help solve all our problems. So let's go back to the world of deep learning and the data limitations, because I think the need for excessive amounts of training data is one of the biggest problems or bottlenecks that we have. And so there's been several attempts at overcoming this. One is to look at more compressed representations of the data. And some of the earliest approaches there was actually doing compression and decompression by doing autoencoders. So you take all your input features, you train sort of a bottleneck network to be able to reproduce the input features from a very much smaller representation space, so a latent representation. And this has led to multiple extensions, so increased robustness by doing denoises, by trying to filling in the gaps, by doing recoloring. But the main problem of this approach that it is based on a detailed reconstruction of the original sensor data, which means for an image, your error function, your loss function is optimizing the reconstruction of all the individual pixels, whether they are important or not. More recently, and I think this is currently the most popular approach, that is to say, just use someone else's data, transfer learning. Transfer learning is standard practice at this moment for almost anything to do with images. So images, you take networks trained on ImageNet, which is a huge data set, trained to classify images, and surprisingly enough, just reusing parts of these networks and the parts that we claim do feature extraction works amazingly well to solve tasks on relatively small target data sets, and even on data sets that are totally different, like say biological data, microscopy data, or other medical images. And so this is common practice at this moment, but of course you are stuck only here to types of sensor data where these huge unlabeled data sets exist. However, the main lesson here is that if you do that, you can do learning with orders of magnitude less labeled samples. So this is good news. And in addition, if you look at the resulting deep learning networks, really the bulk of the compute power goes into this transferred block. There are other attempts at scaling up, commonly addressed with the term of self-supervised learning. And although there's many techniques that are being parked under that hood, I would like to focus on the ones that try to learn about causality, spatial and temporal relations, intermodal relations, using labels that are only extracted from the data itself. And many of these originate exactly in sequential contexts, in robotics, processing video, processing time series. So these are definitely useful for our context for robotics. But actually, and now they almost all operate on the raw sensor data. So they work on the raw video data. But in principle, they could also work on extracted latent representations. So these techniques are sort of orthogonal, except maybe for some of the language embedding techniques, are somehow orthogonal to trying to reduce the dimensionality of the data. So my best bet for global gains using or introducing biologically or neuroscience experience into traditional AI flows is to focus on sensing and feature extraction. And there's a few other things that I haven't been talking about, but the digitization that we use now of the analog world, especially in vision, in artificial sensing is hugely inefficient. You see here an example of a traffic monitoring data set where the images are captured at a very, very high resolution, because you also want to be able to identify the vehicles that are far away. The frame rate at which you need to process is time synchronous and determined by the fastest events you want to detect. So everything is sampled at sort of a worst case setting. And any pre-processing that you do on any sensors is usually done digitally. Yet the gains from transfer learning show that a large fraction of the labeled data is used only or mainly for learning feature extraction. So maybe we should try and focus on doing that more efficiently. And the good thing is that sensing and feature extraction are exactly some of the parts of biological systems that are best understood. So I try to think about a story like this. So this could be an agent, but it could also be another AI system, where I think it would be a good idea to think about problems in decoupling the representation learning from the other computing levels. So I think we can maximally use biological insights, first of all in biologically inspired sensing, and then in trying to use self-organized feature extraction as inputs for trying to create an internal, a latent representation, which could be purely spatial or spatial-temporal, depending on the techniques, of course, that you use here. And then anything else, which are the more difficult things, the things that we are really struggling with now. So how do you abstract these things into higher level context? How do you work with memory? How do you manipulate this data to come up with the answers to whatever tasks you are solving? How do you extract from this representation the signals that you need for to drive active sensing, to drive attention mechanism? All of these things can be inserted into this inner bubble. So I think it's really possible to decouple these things. So although I want to focus on the last bit, just a few other things. So I'm very much in favor of also further investigating things like biomimetic sensing. So what we do now is just raw capturing the data and doing anything in GPU or CPU, whereas in nature we see so many very smart bits of analog hardware that happen before the actual captation of the data, thinking about our ear, thinking about the whiskers of rats and such, thinking about the ribbons on our fingers that help or facilitate touch sensing, etc. Then there is the whole story about the worst case resolution. And so, as I said, especially in computer vision, the resolution and frame rate are determined by the worst case, whereas in our body, our eyes have, first of all, a dynamic focus and orientation. And so we have saccades. We do not see the whole image at high resolution at the same time. We can use attention to focus on certain areas. And at the same time, we have also sensing at different levels of resolution happening at the same time. So we can have low-res images being processed at the same time as very local high-res images. And so these things would happen here in the dark blue ring, where I think there's a lot of optimization that can be done also, not only for robotics, but also for other AI applications. But the main thing, I think, where we really should focus some more attention is on biologically inspired feature extraction, because the principle of this have been known for a long time, have been studied multiple times, but mostly in hello world types of examples, or in very, very specific tasks. So what are, I think, well, this is what I have learned from being among neuroscientists for a while. So what are sort of the main principles? First, there's this thing that is generally called the Hebbian aspect, so that the consolidation of connections between neurons, between layers, sort of captures causality and correlation, and there's a lot of learning rules related to that. Then there's a local inhibition and winner-take-all kind of mechanisms that drive us to efficient coding by decorrelating features, basically. And then there's local self-regulation, which basically avoids the learning to become unstable through positive feedback. So these three mechanisms really have to be there. And here already you see that some of these things make it difficult to be incorporated into traditional flows, because on the right here, there's a picture of what happens during inhibition, because usually in deep learning, each layer is uncoupled, but during inhibition, there are couplings within layers, and these couplings make that the neuron activations have to evolve to relative levels. And this happens at a time scale that is basically below the frame rate, or what you would call the frame rate in captioning. So parts of these things, and especially inhibition, introduce different time scales that we are not accustomed to work with in traditional deep learning. Then there's a question of spiking or non-spiking. And when you really go to spiking, you see that trying to do that on standard digital computing is not really efficient, but we see that the spiking hardware really is coming now. Neuromorphic chips, I think Louis is one of the furthest advanced there, but as far as I know, it's still not available to the general public by just ordering one, or maybe not so easily. So these things are coming. They really need to be evaluated in a systematic way and in standard task flows. So, but the thing is, so if many of these building blocks have been there for a long time, what is stopping us to use these insights to try and improve the representation learning in standard deep learning flows? And one of the main reasons here, I think, is still the communication gap. The computer science and neuroscience are still, to a large extent, separated. And I think the only place where they do come together is exactly robotics research. So this is sort of a call to you to try and collaborate even more, because computer science on the right side and neuroscience on the left side usually think about different things and speak different languages. Now, the second step, since I am coming from a computer science and engineering perspective, is identifying the questions. And for a computer scientist, at the moment, it's sometimes very difficult to know where to start. I included roboticist here. Of course, I mean traditional roboticist and not neuroscience oriented roboticist. So the first question is to spike or not to spike. It generally claimed that spikes are more efficient, they are fast, they can work at low power budgets if you have custom hardware. But we don't see a lot of comparisons at the task level between analog neural networks and spiking neural networks. Do we need custom hardware, or can we do things in standard hardware if you use, for example, rate-based neuron models? How do you deal with the different time scales? Can self-organized learning even be implemented efficiently in digital synchronous settings? Or do things really break down when you start to simplify them to improve computational efficiency? And how do you ever start tuning the huge numbers of hyperparameters? I have played around with a number of self-organized networks myself. My students have done so. And every time we do bump into the same problem, that is that whether it even does anything useful or not is extremely sensitive to the settings of specific hyperparameters. And overall, what we see is a lack of quantitative and comparative assessment of all of these rules. So what I think we should establish is, first of all, of course, a common language, because computer scientists usually do not understand neuroscience, and possibly also vice versa. We need to invest and really collaborate into comparing models and learning rules to study the impact and to study the effective tuning of hyperparameters. And we need to set common benchmarks. And I think we need several levels of benchmarks. One is just unsupervised feature extraction for, say, the simple tasks, so monomodal tasks, but more challenging than, say, MNIST. And to use this feature extraction as a first step in a supervised learning context and compare the accuracy and the data efficiency of learning. And the second step is to have unsupervised feature extraction for real-time and multimodal tasks. And that's a lot more difficult because it's more difficult to have standard tasks that are reproducible and are still representative for the physical world if you work in simulation. or to do similar experiments in different labs and different settings. And so this is a difficult one, but I really think we should try and achieve that. So this is my frame of thought. I'm not going to give you the answers. I'm just going to say that our lab is also trying to make a few steps among this road. And this is with credits to my master's student, Jules, who will be graduating in a month or so. So what he tried was first, well, his goal was to evaluate self-organized learning in a traditional deep learning context. And so he started off by identifying a promising model, which at that time was a recently supervised work by Kotov and Hopfield on unsupervised learning by competing hidden units. But what he did then was he made a huge effort to develop a PyTorch library that is modular and extendable and can be used on a larger scale for evaluating self-organized feature extraction in a digital computing pipeline. And so what you can do there is make one or multiple self-organized layers, and these can be convolutional layers or dense layers, which are then followed by one or more traditional backprop layers. So you can build architectures in which you have a self-organized feature extraction part, followed by task-specific backprop optimized part. He implemented the Kotov-Hopfield learning rule and several other more standard or more classical Hebbian learning rules. And he introduced a lot of support for analysis and visualization. Now this toolbox will be released this summer, and we will try to write a paper about that first, and then it will be released through GitHub for everyone who wants to play with it. We did a few sanity checks. We managed to reproduce at least some of Kotov and Hopfield's results. So in that paper, they still did Hello World benchmarks. They did MNIST digits and Cypher 10. We managed to more or less reproduce the MNIST digits results. We did not manage to reproduce the Cypher 10 results because of the hyperparameter tuning. And we also did an additional benchmark, which is MNIST fashion, just to check that it also works on other benchmarks. But already, again, we bumped into the fact there are many new and unfamiliar, at least for deep learners, hyperparameters, and that the insights are lacking and that they're often also not in the papers that we read. For example, in the Kotov-Hopfield paper, there are quite a number of things that sound like small hacks and that are not really well motivated, but if you turn them off, all of a sudden performance gets a lot worse. So I think there is a place to interact with neuroscientists who really understand these parameters and who hopefully understand what they do and why they are important. It is also really, really, really necessary, even more than in deep learning, to mention all hyperparameters in publication to allow reproducibility. And then we did a small test just to show that you should always be critical because we know that MNIST is an easy problem. The architecture involved one hidden layer of 2000 fully connected hidden neurons, followed by a readout that was trained with backpropagation. So 2000 hidden neurons is already quite a lot. So we replaced the unsupervised trained layer with a random layer. And so in the left column, you see Hebbian learning with backpropagation. In the right, random neurons with backpropagation on the readout layer. And you see, if you look at the test performance, that actually there's not a huge difference. So yes, the self-organized layer is slightly better than random, but it's not a lot better. On the other side, of course, the self-organized learning is not that much worse than end-to-end backpropagation. So it's somewhere in between. And so it's better, but it's not much better, probably because this learning rule is not the best we can do. So we're not quite there yet. But also because there's not a lot of margin on MNIST when you use 2000 hidden neurons. And so conclusion, also when comparing and evaluating these learning rules, always be critical of your own results and of the relative value of these results. So what does this mean now? For this particular learning rule, not much yet. However, it does show that trying to use biological learning is not so exotic anymore. So we show that we can just run it on GPU with actually using parallelization, because this is up to 14 times faster than just a standard NumPy implementation from the paper. It can be integrated, thanks to the fact that it's a PyTorch library, it can be integrated into any standard deep learning tool flow. And our implementation does support standard dense and conv layers, but no recurrent layers at this point yet. And so I think this library can facilitate a path to explore integration of self-organized learning with state-of-the-art deep learning. So there's a lot of things that still need to be evaluated, actually almost everything. And in particular, I think we are now ready to answer the questions on data efficiency. So how much labeled data do you need? How much unlabeled data do you need? The resource efficiency. How does this performance degenerate if you reduce the number of neurons on the self-organized layer? And how, of course, does it compare to different learning rules and different hyperparameter settings? In summary, so my personal belief on what biology and neuroscience can do for us, I think it can dramatically increase the efficiency of learning internal sensor representations by separating this from anything that is task related. And I think all the building blocks are there to convert the ideas and concepts into engineering and into working solutions that could be used by industry. But there's some things we still need, and we need to identify fair benchmarks to compare across platforms, across learning rules, across hardware implementations. And we really need to evaluate all the dimensions into the equations. So we need to evaluate accuracy, but also power, speed, cost, and reliability. Okay, that concludes my talk.
Thank you very much, Johnny, for the interesting talk. If you have any question, please raise your hand in Zoom. We are going to have now a few minutes. We are a bit behind schedule, where we can also host still questions for Professor Jun Tani, but first we will like to address for Johnny Dambre. If you have any, please raise your hand and unmute yourself.
There is no question. I have question here.
Okay, go ahead.
So, Johnny, thank you very much. It was very interesting talk and presentation. I really enjoyed. So actually, as you know, I'm also working on a transfer learning. But one question I have here, if we will have many prior knowledge and we are searching to find the best prior knowledge in order to transfer, it may take a lot of time. And then it's better to go and to learn from scratch. One of the reasons is because in robotics, we don't know where to save or to store our knowledge. And then therefore, we don't know from where to retrieve the knowledge. So what is your comment here? How we can learn from neuroscientists?
I'm not really sure what you mean by how to store and where to retrieve the knowledge.
Means, for example, when in a human, we are storing our, for example, visual information in specific part and then tactile as well, right? Like, and even we have like associate memory, plasticity, and so on. But in robotics, for example, when we want to store the data, we are just putting the data in one, let's say in a memory, in a hard drive and so on. So when it comes to the transfer learning, when you want to transfer the prior knowledge, so as you said, we have to find the similarity between prior and the task, right? So if we will have many prior knowledge, then we have to search. what are the relevant or similar information in order to transfer. So when we search, then it takes a lot of time, right? Because one of the reason we do the transfer learning is to save our time, right? So because it's faster than learning from scratch. But if you will have too many prior knowledge, then if you search, then there will be you have to spend a lot of time. So it's better to, in robotics, for example, it's better to learn from scratch than to transfer from the prior knowledge, because we don't know what is the relevant prior.
Yeah, but the searching, if you have this representation learning, what happens is you sample the world, you observe the world, and the memory is in the network, basically. So if you observe something that you have seen sufficient times enough before, then certain features in your embedded representation will activate, and so you will that will be recognizing. So if this thing, certain things, neurons get a high input or become active if you recognize certain things. So what you get is an embedded representation of events and situations that are in some way meaningful to you from experience. I don't see the searching bit there. And so when we talk about transfer learning and deep learning, it's just say you have a network that is trained to recognize certain features in, for example, images, and you use that same network on images from a totally different origin. So I don't see the searching there. Actually.
Because usually when you want to get the priors, means to know, as I said, different experience. If you have different experience, so to transfer those experience into the current task, we are usually in general in transfer learning. This is a problem in transfer learning, is regardless of if using the deep learning or any other learning method. But the problem is we need to find what are the prior, most relevant prior knowledge, right? So we have to find, in order to find, we need anyway some criteria, but to check these criteria with many priors or many information anyway is time consuming.
But about the transfer learning I'm referring to is only low level sensor representation. And even there, as I said, you can only do this for those sensors for which you have enough data to actually learn something transferable. I think you are referring to transfer of higher level concepts and situations. That is indeed much more complicated. I think there you can only do transfer between, I don't know, suppose you have a bunch of robots all operating in their own environment. They can probably transfer their experience to each other. But
this is also one of the application, yeah. So,
but
I think we will have time later to.
Sorry.
I think we will have time later because we were gonna have iNavigate project. We will have time to discuss. Yeah. Maybe I will give time to the others to ask questions. But anyway, thank you very much.
Okay, maybe we just take a last question from the YouTube channel for Professor Juntani. How did you, Yang ask, how did you generate goal images for training? And also for the slide on variational predictive coding, how did you divide the latent space into different hierarchy, high, low, and medium?
Juntani is here? Oh, yeah.
Is Juntani here?
Yes, it's here.
Okay.
Yeah, okay. So then, sorry that. So you asked that how we can set the hierarchy. Is that the second question? But what
the first one is how you generate the goal images for training.
Okay, goal image things. Okay, so then maybe back to the slide of the. Okay, so I have to share the slide. So. Can you see the slide
yes.
now?
Yes.
Okay, so then back to the So I think something similar question from the previous questioner in 30 minutes ago. So then I back to this slide. So maybe I didn't explain so well. So this is something like a recurrent network time processing. Okay, then consider that it was already run. Then it's something like this higher level. So it's a okay. So then the middle level, lower level. So but it's now in the presentation of the Junk work I did. That is, I use the LSTM, but now this slide is something for the MTRM. So that one is time scale predefined, and like a time constant of a recurrent network is set larger, and this is something like a set to the middle, and the lower one is a very fast time constant of a continuous time recurrent neural network. Okay. So that's the general one, but the LSTM thing is more complex, so then I don't explain in terms of LSTM. So then what is a recurrent network? This one is actually except initial step, and context unit or latent state is processing the deterministic. So therefore, recurrent network is a deterministic dynamical system. If you set initial state, and the recurrent network development, time development of recurrent network is kind of determined completely. So then the trajectory is determined. So then if we train the many sequences like a visual perceptive sequence of the robot, then each one is trained, but each time, so we're going to adapt initial state for each training sequence. We do a lot. Like a fast robot grasping the red one and put on the green, or red one to put on the blue and grasping and put on. So those many sequences, that is actually visual perceptive sequence. We let network many sequence parallel manner. Each one is run, but each one is run with same synaptic weights, but each one is differentiated with initial states because trajectory is different, right? So it's a robot always starting from same home position, okay? But it's an object located in different place. Then then needs to generate different trajectory visual process sequence, and that's seed. So seed for generation is initial states. Okay, because deterministic model. But if we use a recent, okay, but I don't go that one. So then in order to, so if we want, so this is a goal image of the end, some kind of goal image. And this is a prediction of visual perceptive sequence. And if this one kind of distal one, the match, in order to make match this one, the error minimized. And the error is back propagating, okay, through time. So back propagation through time, and then changing the updating the latent initial state value of this one, okay, so as to minimizing the error. So that is the planning search process. So searching in the latent space, but latent space of the initial step. Is it clear? So that means that if you change the initial state, it can generate many possible visual perceptive sequence that is generated. It's self-organized, so the learning of many trajectory. So that is kind of a predictive model about the interaction with a block. So that is kind of causality is learned. Then we provide as an end condition what kind of the goal position, goal constraint, and what is the initial state condition. Initial is a visual constraint, so located the object in a always different. So then we're gonna kind of infer that these things, visual perceptive sequence, possibly connecting from the initial visual states to this one by manipulating initial latent space variable. So that is our way to go. Is that?
it's super interesting, but I think I have to cut you. I'm really sorry. And I really insist that the people that they really want to know more about Jun Tani's work, I suggest them to read his book, and also to get a look to his website. And you will see how he managed to use the attractors and the recurrent neural network to do this kind of task. I think it's an amazing work. So I recommend to everybody to actually get deep into the papers. And of course, if you have always questions, you can always write to Jun, and he will actually try to solve your questions. And I think this was actually amazing, 2 first talks of the workshop. And actually, we have from Belgium and also from Japan. So Jun is in Japan now. It's night already. I think everything is closing. So I think we have to move on because we have a little bit of time. We lost a little bit of time.
Yeah, thank you. Yeah.
And
Thank you very much, Jun.
Thank you very much, Jun.
Johnny, thank you very much.
And Johnny, also thank you very much. Don't leave, please, because we have the contributions right now. And I think that maybe you have some questions for that.
Yeah.
Okay, so I ask please Alexandre Petit to start sharing his screen, just because we are a bit late. So the first contribution is going to be by Alex Pitti, Matthias Coy, Sofiane Busenna, and Catherine Lavandier on complementary working memories using free energy optimization for learning features and structure in sequences. So thank you, Alex.
Thank you.
Whenever you are ready.
Yeah.
Actually, I have to say that Alex is in Paris. He's the only one that is actually in the conference right now.
And actually, I'm 1 kilometer from the conference, so I would have meet you there. It would have been nicer. I don't know if you see my slide.
Yeah, we can see.
Yes, perfect.
Okay, so thank you. And so already the 2 talks are really enjoying. I just want to present shortly what I'm doing about complementary working memories. Basically, the main idea is that remembering is an active and dynamical process, and keeping trace of information is prone to errors, noise, and variability. This is why the recall of memory sequence has to be a dynamical reconstruction and similar to a controlled process. So the idea is that memory recall is not a one-shot, it's a generative and causative process of neural chains. So using this idea, well, I propose 2 mechanisms, error prediction, to serve to control actively one system, pretty similar to active inference, and to generate back trajectories not prescribed in advance. So predictive coding and also free energy minimization, which has been introduced by Jun Tani, can serve for memory sequence generation and recall. So I will not go through this, but just to present one model of it. So we start on working on a model called Inferno for iterative free energy optimization for recurrent neural networks. Pretty much 2 networks, one for control, one controlling the other, and to learn to generate, select, and amplify dynamics, and using noise for optimization. So we start to use this network recently for language processing, and we were trying to model what's going on the primary audio cortex in the green part and the Broca area in the red part. One is for sound repertoire, and the other is for
Alex, I think we are not seeing your slides move.
Really?
We just see your first slide.
Already? I'm so sorry. Did you?
No. Now.
You don't see this one?
Now, yes. Now it's changing. We were in the first one still. Now it's changing.
So sorry for this. So I was presenting this network we were trying to model, and on this problem of language processing, trying to model the sound repertoire and the syntax also. So one is for learning really the low-level vowels or sound primitives, and the other is to learn the structure behind it. So I can explain you more in the poster session this afternoon how it's going on and how to combine the two based on free energy principle. Thank you. I hope it's fine.
Thank you very much, Alex.
Thank you, Alex.
Sorry for that.
Okay, so we will pass to next speaker, which is Sengdu Sai and Ismail Artuk, exploiting refractory period for functional multiplexing and short-term memory in spiking neural networks. So you can please go ahead.
Okay, I'm going to share my screen. Yeah. Can you see my first slide?
It's good.
Oh, great. Okay. I'm Zhendo Zhai. I'm a second-year PhD student from University of Missouri, Columbia. I work for Dr. Akhtar Ismail. Today, I'm going to talk about our research on spiking neural network and the potential of spiking neural network on robotic. This spiking neural networks has recently received attention due to their low power and efficiency. Considering the constraints of robotic application in terms of area, power, and performance, spiking neural network appears to be an attractive path for real-time interaction and learning. While conventional spiking neural network does not model the refractory period, we find that modeling refractory period would further open up a path for improving efficiency and performance in those domains. We find that the refractory period of a spiking neuron can enable functional multiplexing and short-term memory. So first, I'm going to give a brief introduction of spiking neurons. Spiking neurons can have 3 states: resting state, spiking state, and refractory period. When a neuron is in a resting state, it accumulates the input connect to it. When they reach the threshold, it will generate spike. And after the neural spike, it will enter a refractory period and become unresponsive. In this example, N1 is a spiking neuron and is firstly in the resting state. When it receives stimulus, it will emit a spike, and which is considered as logic 1. After spike, it will enter refractory period, and there will be no output, even there's still input here. The output of spiking neuron depends on its current state. And in this example, the output on N1 will change from 1 to 0 when it enters the refractory period. So by using refractory period, we can realize the functional multiplexing. Functional multiplexing is a method that allows the spiking neural network to realize different functions during distinct time periods. Functional multiplexing allows us to reduce the number of spiking neurons needed to implement respective functions separately. And that will save area and power consumption and meet the constraints of robotic applications. As an example, we can build a network behave as XOR and NAND gate by exploiting refractory period. So here in this example, when neurons, when N3 and N4 enter refractory period, the structure's function will change from XOR to NAND. With the functional multiplexing by exploiting refractory period neurons, both XOR and NAND can be realized with 7 spiking neurons, while about 10 neurons are needed to build XOR and NAND without using refractory period. In addition to functional multiplexing, the existence of a refractory period gives an inherent short-term memory capacity to a neuron. So here in a neuron can be in refractory period only if it recent spikes. In this example, N2 want to receive an input and it enter a refractory period after spiking. During the period, N2 won't be responsive to the probing input and that will indicate N2 has recently spiked. And in a sense, if a neuron keeps in that sense, a neuron keeps a short history of its recent activities. But on the other hand, if N2 spikes when the probing input is provided, it will indicate that N2 has not been recently spiked. And this short-term memory can be used in different learning mechanisms. Refractory periods of spiking neuron can be exploited to enable functional multiplexing and short-term memory. And both functional multiplexing and short-term memory are both based on refractory period will be key to build efficient learning, sensory information processing, and motion planning in robotic applications. Thank you very much for your attention. And is there any question?
Okay, thank you very much.
Thank you.
I believe we have to go to the next contribution.
Oh, yeah.
Because we are a bit behind, but everyone can go ask questions in the poster session where you will be provided with the link to the Zoom session. So the next talk is by Yunus Seker, Erham Ostop, Mete Tuluhan.
Hello. Can you hear me?
Yes.
Okay.
Minoru Asada and Emre Ugur. And the talk will be towards a mirror neuron system via dual channel conditional neural movement primitives. Okay, the stage is yours.
Yeah, I think you have to stop screen sharing. Yeah, thank you. Can you see my screen?
Yes.
Okay. So hello everyone, I'm Yunus from Boğaziçi University, Turkey, and today I'm going to talk about our work with the collaboration of Osaka University and the University of Tokyo. So let's start with mirror neuron systems. Studies find that there are mirror neurons in the animal's brain that fire both when the animal acts and when the animal observes the same action. And it's a common belief that these systems support imitation learning in both humans and animals. However, how this is achieved and the developmental base is not very clear. Here, in this study, we propose a computational mirror neuron system that allows our agent to understand the equivalence between its own action and the observed one. And we are aiming to do this by following an effect-based learning approach through self-exploration. In this study, we are using conditional neural movement primitives to learn actions from self-exploration. CNMPs can learn complex multimodal trajectory distributions and can be conditioned at any time point to make predictions. And similar to mirror neuron systems, CNMPs can make predictions with partial observations, and also they are successful at intention predictions. Before explaining our proposed model, let's have a look at CNMPs closely. This is the general figure of CNMPs. On the left side, we will explain how CNMPs are trained, and on the right side, we will show how we can produce the new trajectories according to novel configurations. Let's start with our demonstration set here. It's a function from time to record the sensor motor values. And in every training step, a random demonstration is chosen. From this demonstration, a number of random time and sensor motor couples are sampled as observations here. In addition, a random time step is also chosen. Our aim here is that the system will try to predict the value of this time step using the observations. So in this step, the sampled observations are passed through a parameter sharing encoder layer to get their representations. These representations then are merged into one by using an averaging layer here. In the end, we have a representation that holds the information for all observations. Here, the general representation is also concatenated with the query time step and passed through a query network. And in the end, we have a mean and variance prediction for the sensor motor value in the query time step. To train our system, we calculate the log probability of the ground truth sensor motor value on the predicted Gaussian distribution, and we backpropagate the minus value to train our system. So by repeating these steps again and again, our system actually learns how to make conditional predictions. Now let's see how new trajectories are produced. After training, we instead of sampling sensor motor values, here we define novel observations as our goals that we want our systems to satisfy. And we will query our system with all time steps in order to get the whole trajectory prediction. So in the end, we get mean and variance predictions for the whole trajectory, and that result will satisfy our defined goals at the start. This was a summary of CNMP. Now I want to introduce the experiment setup, and then we will go to the proposed model. So this is our experiment setup. There's a UR10 robot and an object in the middle of the table, and also there's a vision sensor looking to the scene. We collected different pushing and grasping action with different approaching angles, and recorded the joint values and the images of the scene, as you can see on the right, for example. In the end, we collected 40 pushing and grasping examples. So this is our proposed system here. This figure shows the dual channel CNMP architecture that we're training our images and joint values together. A dual channel CNMP means that there are two separate CNMPs, but they are sharing a single latent space to form the representations. Now let's have a look at in detail. So here we can see that the upper part of the system is the CNMP that is trained with image information. The observations are image, and the predictions are going to be images. On the other hand, if we close the upper part, we can see that the below part of the system is another CNMP that is trained with actually joint values. So here the important point in the system is that the representations of the both systems are fused into one by using a dense layer here. You can see in the red circle. This layer allows our system to share related information between these two channels and makes them learn together by mirroring the information for the same time steps. So we have some preliminary results here. In this experiment, firstly, we test our system to see if it can predict the approaching angle and the type of the action just by using a single visual observation that is not in the training set. So here the images on the left are the observed frames that are inputs. We want our system to predict the rest of the trajectories according to it. The videos on the right shows our prediction results, and you can compare them with the ground truth videos in the middle. Let's have a look at this example. On the observed frame, you can see the approaching angle of the robot is from here. And you can also see that the gripper of the robot is closing, so this indicates a grasping action instead of pushing action. When we look our prediction result, you can see that our system can successfully predict the angle and the grasping action, and it gives us this nice video. We have another experiment here. So in this experiment, we tested our system's generalization capabilities. We use different object colors, gripper colors, and object sizes in our observed frames as inputs. And we see that our system can generalize its knowledge to these situations and successfully predict the angle of the approaching angle and the type of the action as a result. We also examined some failure examples. As you can see here, the object is dropped on the table, but the predictions is not very well. So as our conclusion and future work, we can say that prediction and generalization results are promising. In the future work, we will work on using the predicted joints as well, and try to test our system from different perspectives instead of just the self perspective of the robot. Thank you so much for listening. If you're interested in our work, you're more than welcome to visit us in the poster session.
Thank you, Mohammed. Very interesting. And we are going to proceed now to the second block of contributions. You can ask further questions in the poster session.
Okay, yeah, sorry, I will take him a little bit from here because we are really running low, later. For the contributors, please 5 minutes, not more, because if not, we don't have time on this Sunday. Welcome everybody to the virtual workshop BRAIN-PIL from ICRA 2020. We are already having the, thank you Mohsen for sharing the screen. We are already in the second block. We really thank you everybody to be here. And this session will be chaired by Mohsen. So please, Mohsen, go ahead.
So thank you very much, everyone. I hope so far you enjoyed the presentation and talk, which I did. So for to whom joined the workshop recently, I'm Mohsen Kaboli, the Senior Research Scientist at the BMW Center of Robotics and Artificial Intelligence. So we're gonna have two interesting talks today and two contributors. They were gonna present their papers or the posters here. So we're gonna start with Manuel Lopez. So Manuel is associate professor at Institute Superior Técnico in Portugal. Prior to that, he was senior research scientist at INRIA. Basically his research interest is in application on human-robot collaboration, joint work with machines and educational technology. So Manuel, are you ready?
Yes, let's see if it can. So, you have to authorize stuff.
Great. We can see your presentation here. So the stage over to you.
Is the camera working? I cannot see it.
Everything works properly.
Okay. So thanks for organizing this with this quarantine. Everything is confusing, and for a workshop usually we like to discuss, and it's much more difficult. So thanks, but to still do it. So I like to always think about this relation between the biology and artificial intelligence. So I think it's very nice, all the system. So for this workshop, it's difficult to decide on a topic, right? Because it's about the brain, but it's about the robots. So my talk is more about the discussion about the different approaches, and to see, I know if our approach we are taking for robotics in AI is following what animals are doing. So it's very speculative, let's say. So the question is, are you really aiming at the real problems in robotics in AI, or are we creating difficult problems but that are not real? And is the brain doing the same thing? So my presentation, I'll present what I think it's our approach. So the way we approach science, like we in general community. So then some examples about animals that I think they don't address the real problems in the same way as we do. And then I'll show a simple example, or that's maybe a bit different from the others, to see how can we approach complex problems. Okay, how can I go? Okay, sorry, I have to start with the definition of intelligence. Everyone knows that's what it is, but actually we sometimes forget. Okay, so in animals, intelligence is not about just grasping, it's not just about planning or reasoning. It's a combination of everything, and the learning and leading with the new situations it's a very important aspect. Okay, so intelligence is not one of these aspects, is everything at the same time. So it's not taking a database that we download from the web and collapse it with a neural network. It's deal with real problems that involve many different skills. Okay. So how are we getting to artificial intelligence? So actually, we have a bureaucratic perspective that we divide universities in different departments and different fields, and we have different conferences and different experts, and we hope that we can get to something. But actually, that's what we really do as scientists and academics also. Something is clicking here, I don't know what, sorry. Maybe shut that up. So what we do is that we take a robot that is composed by different components and we cut it, right? We take the robot, we cut the robot, we take the arm, we take the head, and we hope that we solve each problem independently, right? We take the hand and we solve the grasping, we take the arm and solve the reaching, we take the head and we solve the planning. Okay, this is like as if a dog has to cross an obstacle, and what the approach we take is like we propose 5 master theses. One does the computer vision to detect the scene, another one defines a cylinder in his objects and tries to find an obstacle-free path. Then another computes the optimal path. Then another computes the motion of the center of mass. And then another computes the joints for the muscles. And of course, a dog doesn't do this, right? It would be impressive to see a robot doing a task like this in a fast, without a pre-programmed way. Okay. So we are decomposing the problems, right? We are the planning. We try to make it very optimal, very difficult, and send to each guy. With the vision, we send to ICCV. We manipulation, we send to Iker, and then we submit locomotion to humans, right? And then what we hope with this approach with science is that if we solve optimal each of these parts, then we combine everything and you have an optimal approach. Okay, that's what I think we have been doing for last centuries, let's say. I don't think that the brain is doing this, and I think that of course this has advantages and we evolve a lot, but it sometimes makes the problem more difficult. I like these 2 slogans, let's say. So this from computing, this from Donald Knuth, is like premature optimization is the root of all evil. So this is in context of programming, right? Sometimes you try to optimize your code, and then you never have the final product ready, or you have then, when you combine everything, you have bugs. And then there's another citation from Rich Sutton that I know sometimes we don't understand the difference. It's like approximate the solution, not the problem. Okay, so I think usually we do the opposite, right? Usually we simplify the problem and try to find the perfect solution to a simplified problem, and I think that's the problem. Okay, so of course this decomposition might be good, right? Because if the decomposition is correct, then we are solving the problem. Might be unnecessary because it's so complex you cannot deal with the problem. Maybe it's a good simplification because you get problems that you can deal, and might be a source of optimal solutions. Okay, the decomposition is correct and optimal. So there's this nice paper, Can a Biologist Fix a Radio, where he argues against this perspective. Right? If you study batteries, if a radio is broken, you think that the problem is the battery. If you study antennas, then the problem is the antenna. And you never think that maybe everything is working correctly. It's just a problem of interconnection between the modules. Maybe every component in your radio is perfect, but you just put the batteries on the wrong side. Okay, so sometimes optimizing the parts is not the same thing as optimizing the main system. So it's the same thing. You might have an optimal reasoning and an optimal motor control, but then you just forget how to make them work together. So maybe if you don't optimize too much each of the components, you can think about the overall process. So I don't think this decomposition is correct, because I think many times when you optimize each part, we are ignoring the interconnections between the parts. Okay? So now the question is the decomposition a good simplification? Okay, so if you decompose again the robot between grasping, reaching, scene detection, I think then the problem is that we get very artificial problems that are difficult and are not realistic. So if you get a list of hard problems in computer science, so hard problems should be problems that are hard to solve, right? And you have this problem, the traveling salesman problem, that everyone knows it's an NPR problem, because it's a combinatorial process. You have to try all the combination possible of paths to get the optimal solution. Okay, if you have hundreds or 200 towns, you can get hours to get optimal solution, okay? But actually, if you don't do that, you just make some fast heuristics, you can make some approximations, you can get anything between just 50% more than the optimal solution and 0.8% more than the optimal solution, okay? So one of the hardest problems in computer science becomes a very easy problem if you just allow for, I know, 20% of error, something like this, okay? So this is an example where you make a decomposition of a problem, and then you get a problem that is too hard, that people spend years researching, where an easy solution approximates exists. So I think this decomposition is not a good thing, because it creates problems that are artificially difficult. So, okay, we are grasping, we still haven't solved it. I know, SLAM, we haven't solved it, because we are trying to get everything very perfectly. So is the optimal solutions we get a nice overview for the overall system? Sometimes you get solutions that are not a good solutions for the real system. For instance, this is again an example from Sutton and Bartu's book. So if you have a cliff and you want to avoid to the cliff, from the start to the goal position, you have an optimal path, right? But if you are really in the mountain, are you taking this really narrow path, or are you going to go around? So would you take the optimal path, or you take the safe path? Of course, everyone will take the safe path, right? You'd give some distance. Why? Because the optimal path is just optimal for a very particular set of conditions that just exist in the lab. And you know that in the real world, even if you might have a 1% mistake in your model, then you go down the cliff, right? So why optimize for something that it's probably you are not going to find? So I think the answer to all these questions is that in general, again, of course, we have developed science a lot by doing these things, so I not want to exaggerate this, but in general, I think the decomposition is giving problems. We have problems of the decomposition, that the combination then is not taken into account. Sometimes you decompose and you don't need to. Sometimes when you decompose, we get problems that are much harder than what the real ones. And the solutions we get for these problems, then they don't apply in the real world. So I think we have been doing the intelligent components separately, and I think we should take them into account in the combined way, right? So we have to think that we have reasoning, we have planning, we have to learn, and you cannot really decompose these components separately, because then we cannot combine them, and that's the problem. So let's talk about a bit animals. So usually you just say that humans are very creative, are very original, are play, and then I know animals cannot do it. So we just assume that animals just care about survival and reward. Okay. And I think this is not true. So just consider the reinforcement learning framework, and let's have an example. So do animals just care about the rewards or not? So there's lots and lots of more recent research that tells us that is not the case, right? Animals don't care just about the reward. So this is an example where animals, monkeys can have two options. Either they go to the forced information condition, where they look at a screen and then they get an informative cue that tells them, are you getting a reward or you are not getting a reward? And 2 seconds later, they get or not the reward as the information said. 50% of the times they get the reward, 50% of the times they don't get the reward as the information tells them. Then you have the forced random condition where they look to the screen, they have a cue that is irrelevant, doesn't inform about anything, and 2 seconds later, then they again get the reward 50% of the time. So they get always the reward 50% of the time. It's just a question if they know 2 seconds before or not. And so given a choice, what do animals do? So given a choice, animals prefer the information. Okay, it's not just about the reward. They decided if they're given the choice, they prefer to get the information a bit early. And this has been tested, so they really know how to predict the reward. So this is not a side effect. Okay, just I don't have so much time to go to these details. So and they did these experiments with rats, with pigeons, with dogs. I know they all them as similar behaviors, and some species can lose 60% of their reward just to get this early information. Okay, they are losing reward to get information. In a more complex situation, you can have a cue that tells you are getting the reward or you are not getting the reward, and then they can explore. Okay, so if they explore, then they again get another confirmation. If they know they are going to get, the confirmation says you are going to get. If they say they know they don't get, the confirmation says they do not get, and then they get or not the reward. And then you have the 50% situation where you don't know if you're going to get, so you should explore the screen to really have the information. Okay, so in this situation and there's no new information, and here there's lots of information. So clearly they look more in the 50% situation where they get information about reward or not, but strangely, even if they already know that they are going to get the reward, they want more confirmation. Okay, they still want to know if they are getting a reward or not. And if they know they are not going to get, they look less. Okay, so it's a really strange behavior, right? So even if they already know there's no information, they still make an effort to confirm something that's already. So you have animals and robots, right? You have all these two conflicting perspectives, right? So if you are learning, you want to go to locations that you cannot predict, right? The 50% locations where you don't know what happens, so you want to go there to get more information. So this would be this exploration drive, right? 50% is what you want to go to because it's what you don't know. And after learning, when you're acting, you do the opposite, right? The parts that you cannot predict, you try to ignore, and you go to the parts that you can predict, either 0% or 100%, in case if it's like a good or a bad thing. But there's also another drive, right? If you prefer good news than bad news, okay? So only combining these three different sources of information, you could explain the behavior of animals, okay? So just trying to explain the behavior saying, oh, they want the reward, it would be impossible to explain all these experiments from biology and from neuroscience. So animals are not really doing the reward. So if you just think about the reward plus uncertainty, you'd get something like it's symmetric, right? They just look for the uncertainty. If you get the reward and the preference for good news, they will look more for the positive, less for the 50, and less for the 0, right? Only when you get to the 3, you can get the same behavior qualitatively as the mind, right? So animals, I know, are trying to combine these 3 mechanisms. So I think there's lots of evidence that tells us that animals are not optimizing rewards on a set of artificial decomposite skills. They really don't care about being optimal at each individual component. Okay, of course you can say, oh, they have a different reward. Well, that doesn't answer the question, right? We don't know that's what's the reward. So we cannot explain the play learning just by reward. So it's not about a simple component. So let's just change. I know it might look completely different, but I hope to make to show you my point. So a very mundane test, right? Trash collection, right? We want to recycle. We want to save energy. We want to optimize energy. So we don't want the trucks to go and not collect the trash. We want to recycle. So I know every city has this big problem, right? So we have to decide the shortest path. So because you want to save energy, so we already have a big problem in computer science, right? So if you have even a small city can have 200 or 300 bins, so it might take several hours to optimize the path. Okay, so we are already doomed. Okay, so if you decide where to go because you want to avoid overflow, so you go where trash is getting accumulated, but you also want to spend less energy, so you should avoid going to bins that are almost empty, right? So the problem is that we don't know. This is a big uncertainty problem because there's no variance on the different bins. There's no real-time information, so it's very difficult to predict, right? So if our reinforcement learning problem, I know in a simplified way, it can be it's already an NPR problem. If you take into account the lack of information, the lack of uncertainty, the lack of information about the bins and the future, we have an hidden state, so we have a POMDP, right? So if shortest path is already a hard problem in computer science, that is all in all books that we teach at university. I know a POMDP is much harder problem, right? In the garbage collection, we have a POMDP, so we have the cost of the path and the cost of overflow. So this is impossible to solve efficiently, right? So every city has to do this every day, and if you have 200 bins, you cannot do it you take a couple of hours, right? So you need to do this in a couple of minutes to do this trash collection efficiently. So how do we address these problems typically, right? So we simplify the problem typically, right? You choose between fixed routes, or we optimize the frequency to each location, or we assume a deterministic system and optimize for it, and then replan, or we divide in small regions. So what we do is that we simplify the problem, not the solution, right? We think that we will take a smaller problem and then that we can solve optimal, right? So we should not do this, right? We should not simplify the problem. We should simplify the solution. Okay, let's try to simplify the solution. So the solution, you take the same idea of, in animals, right? You have multiple rewards that are in conflicts, right? One is the path reduction and another one is to avoid overflows. And then, of course, you can sum the two, but it's a POMDP, so you cannot really solve it efficiently in optimal way, right? But let's not do it in an optimal way, just do it the naive way, okay? So each day we decide, let's visit all the bins that are going to overflow today, or that's a high probability of overflowing. And all the others, for the other bins, we just check if they are going to overflow tomorrow, how much we are going to pay a cost to go there tomorrow. But if we make a small detour today, we'll collect them before being full, but we don't have to go there tomorrow. Okay, that's the algorithm that wants to solve a POMDP. So the computational cost is linear in number of bits, and then plus an approximate travel salesman problem. Okay, actually, you can prove that this naive approach is close to the optimal, and you can solve it in a couple of minutes. Okay, the path is not optimal, the choice of the bins is not optimal, nothing is optimal, but the combination is close to optimal and can run in minutes, so it can be used. And then you can see, like, this is like I know, maybe this is Coimbra, so like the fifth biggest city in Portugal, and this is a smaller city around, so it has like 100 bins, and you can say for these 100 bins, you can make you can make the planning in a couple of minutes, and you can save 400 kilo for 40,000 euros a year just on the collection, right? Okay, and then if you want to decide where to put the sensors, it's even a more complicated problem about where to put the sensors, because you have to, for each combination of sensors, you have to make a POMDP. So it's ultra complex to solve. Okay, so a trash collection is a very hard problem, so harder than an NP-hard, and usually you just give up, or we try to simplify the problem, right? So here we did not simplify the problem, right? We did not assume it was deterministic. We did not assume that the road has a specific topology. We did not solve a smaller instance of the problem. We simplified the solution. Okay, we take, let's ignore the optimality. Let's make an approximated solution, and let's see where it gets us. And actually, it gets us close to the optimal, and in a very efficient way. So what we do, we are following the rich slogans. So we are approximate the solution, not the problem. We are still doing the real problem. And I think that's the main, I think my main point on this talk, right? We try to decompose, to simplify the problems, and then assume that you can do it perfectly, right? Then the simplified problems we assume that we don't have limits on computation, we don't have limits on perception, we don't have limits on the knowledge. And that's never true, right? We always have limits on the computation, we always have limits on perception, and always have limits on the knowledge, right? And so we should always think on our solutions into this perspective, right? So the first take-home message is this, right? Our decomposition, our division in academic departments sometimes is creating problems that are more difficult than we need, right? Is this travel salesman problem? It's not a really hard problem. Come on, let's stop telling this to students. Because frequently we can find quasi-optimal solutions for real problems, and you can go directly to the real problem. And there's another paper I invite you, is that this optimal isn't good enough, right? Because it's we should not aim for the optimal, because good enough usually is good enough, right? And if you want to make a combination of skills, you should not spend so much time optimizing each part, because you can find solutions that are more efficient. So my final take-home message is that the brain approximates the solutions of the problems, right? The brain has to live in the real world, and it cannot really change the world completely. So he has to find solutions to the real world, but he has to ignore some parts of the optimality, because it cannot do it. So it's, I know this citation, right? You cannot control the wind, so you cannot control your problems, but you can adjust your sails, right? You can find a solution for your real problem that it might not be optimal. Thanks a lot.
So thank you very much, Manuel. So we will there will be an interactive session, and then we can ask some question maybe in 30 minutes from you. So now is the time to go to the next speaker, who is Professor Ake Ispert, who is the full professor. I have to share my, let me share my, here. Yeah. So our next speaker will be the Professor Ake Ispert, who is the full professor at the EPFL, and he's heading the lab of biorobotics. And basically his research interests are in the intersection between robotics, computational neuroscience, nonlinear dynamic systems, and applied machine learning. Today he will give a presentation about controlling robots' locomotion with control architectures inspired from spinal cord circuits of vertebrate animals. So I hope Alk is here now.
Yes, I'm here. Can you hear me?
Okay.
Yeah.
So
Hi,
now
everyone.
we can see you. Hello, Alk.
So,
thank you very much for your time and being here.
Yeah, it's a great pleasure. And I think it was a very nice idea to move on with the workshop and do it online. I think it's really what we should do more in the future. And I really enjoyed the talks I've listened to. So unfortunately, I could not join the whole day because of family reasons, but really nice talks what I've assisted to. And Manuel, I love what you presented. I think, I hope I can complement this a bit with my work on more on the spinal cord, so the low level of this. So can everyone see my screen? Is this fine?
Yes, we can see you. Everything is good, great.
Super, yeah, yeah. And let me just shift this a bit.
We have you also in YouTube.
Yeah, oh, excellent, yeah. And I'll put my laser pointer here. Okay, so indeed, I like to focus a bit more on locomotion and this amazing skills that vertebrates have to do locomotion. And here the embodiment is, of course, very important. How this dog here controls more or less 300 muscles, and its nervous system is solving an amazingly complex control problem. It's highly nonlinear, it's high dimensional, it's a hybrid problem because the contacts change all the time. And for me, it's super impressive how the nervous system solved this so beautifully. And as you know yourself, when you go jogging, you don't think about it. It just works. And but once you try to implement that in a robot, you realize it's very impressive what's happening here. And this video here is just steady state. So look at what animals can do in non-steady state conditions. These are very impressive agility competitions where you see a dog running with his owner and its owner, and you get points to move across these terrains as fast as possible. And this agility is just amazing. So of course we do better and better robotics. Boston Dynamics, the first one, but we're still not, I think, there yet at this level of agility. So my dream in my lab is to, on one hand, understand this agility and use models and robots to understand, address scientific questions on biology, and then hopefully also contribute a bit to robotics to approach a bit this level of performance. So at a very naive way, the main ingredients for this amazing locomotion is, first of all, the clever mechanics. So we should never underestimate to what extent the biomechanics itself is well organized to already solve parts of any motor control problem, not only locomotion, but also reaching or anything. And then that will be a bit the focus of my talk, is the spinal cord. So as you know, the nervous system has not only the brain, but it has also the spinal cord. And the spinal cord is in fact the older part of the nervous system, and it's really fundamental. So it has many reflexes, and it has many pattern generators, building blocks of kind of feed-forward controllers that are implemented at a very low level, and that can generate both rhythmic and discrete movements just at the level of the spinal cord itself. Now, obviously, the high part of the brain are super important as well. You need your motor cortex, your cerebellum, your basal ganglia to do anything complex. Especially for moving around, especially in the second video. In fact, the second video has a lot of intensive descending modulation. But interestingly, the first video has very little, possibly just a drive signal activating the spinal cord, and it's really the spinal cord that's completely in charge for steady state locomotion. So I think we need models and robots to understand how all these components interact together and kind of decode this very impressive redundancy of locomotion control. Even yourself, if you go locomoting, you can do a crazy Monty Python walk, and that's then very cortical. But if you just don't think about it, it's purely your spinal cord that's in charge and just receive like a speed signal. So today my talk will be focused on the spinal cord. So I hope you're still interested in this, even if it's not the brain, but it's the nervous system and the spinal cord. And a key question of interacting between sensory feedback and central pattern generators. That will be a bit the focus of my talk. So why is the spinal cord such a beautiful idea from a point of view of the nature? I think it's a beautiful idea because, as you know, you have many muscles, and even every muscle is made of many, many muscle fibers. So you need a very high dimensional output to control your body. And the spinal cord is there to reduce dimensionality. There's no way that your descending pathways could have all the bandwidth to directly control all the muscle fibers. You need in between the spinal cord to have pattern generators to be high dimensional and send all these signals to all the muscle fibers. A second thing where it's good to have your spinal cord is that, as you know, neurons are very slow, and you want to have the feedback loops as local as possible. If all the state information has to go all the time to the cortex, you will not be able to play tennis or go running or play piano. All the feedback loops should be as local as possible. Of course, you have state information going up, but the fastest information, the fastest feedback loop should be in the spinal cord. There's no other way. So that's why there are multiple feedback loops within the spinal cord. And then I think nicely related to what Manuel just showed, I like the idea of seeing the low level of the spinal cord plus the body as a puppet on string, where by playing with a few strings, you can activate periodic and discrete patterns. Sometimes just a single global string will just drive the speed, like in the first video of the dog. And sometimes if you find a movement, you will play with multiple strings, but always a subset, a fairly low number of strings, just to help high part of the brain not to be overwhelmed with the dimensionality and help both learning and planning at a high level. So that's why I can already give you my take-home message now is don't underestimate the spinal cord. It's super important to help motor control and is a key part of the building block of learning and motor control and planning in general. It's in fact only in primates that you have direct control to your muscles with direct connection to the motor neurons. Otherwise, it's always through spinal cord circuits and pattern generators. So in my lab, we have been interested in decoding what happens in the spinal cord. We have worked on very abstract systems like dynamical movement primitives to represent these circuits, and also more neuroscience-driven models that I'll present today. But just to summarize, this concept of spinal cord is very interesting for lowering the bandwidth between high centers and spinal cord, faster feedback loops, and providing motor primitives as building blocks for more complex movement. So as mentioned, in my lab, we like to decode how this works in animals. And we also like to see how this has possibly changed during evolution. Because I'll come back to that a bit later in my talk, but I speculate that in lower vertebrates like lamprey and salamander, a big part of the control is generated by central pattern generators, these oscillators that have this feed-forward component. I'll come back to them later. And the more you go to mammals, the more you are sensory-driven and the more you need finer descending modulation. And to decode all this, I think we need models, mathematical models that I'll present. And we need embodiments. We need either a good simulation or real physics, real robots to close the loop with the environment. So today my talk will be presenting some work on salamanders first, and later on some modeling work on human locomotion. So let me start with salamander locomotion. So as you might know, I love salamanders for quite some time because these are really key animals from an evolution point of view. They are really living ancestors of all tetrapods, including mammals. And they have this very beautiful bimodal locomotion. So they can do swimming like eels or lampreys that you see on the left. And if you place them on the right, they'll switch to a walking trot gait, which is a quite different gait with nice activation of the limbs and nice coordination between body and limbs. Very interestingly, if you electrically stimulate the brainstem of the salamander, the descending pathways to the spinal cord, at low level of stimulation, you will induce a walking-like gait. and at high level of stimulation, you have a bifurcation and you switch to swimming. Just increasing the drive, pressing the gas pedal will make a complete switch of behaviors between these two quite distinct motor behaviors. So this is a bit older work we published in Science, where we demonstrated how, by starting with a primitive swimming circuit, adding new layers in the spinal cord models to represent the limb oscillators, we were able to represent this transition from swimming to walking by having a representation of this spinal cord circuit based on what we knew of its topology. And just by increasing the drive here, this is the drive signal applied to the descending pathways, we could nicely switch the behavior from walking to swimming and vice versa. So I will not go too much in the details, but we had different levels of modeling. The model we had in the Science paper was a very simple oscillator-based model, where a single oscillator represented by two state variables, as you see here, like a phase variable and an amplitude variable, was representing the bursting mechanism of a local circuitry, which in the animal has more or less 2,000 neurons. And then so we simplify these 2,000 neurons by represented by a single oscillator, but then we can represent the whole topology, the whole network by the simple oscillator models. And thanks to that, we could explore questions and hypotheses of the general organization of the circuit. And I don't have time to go in detail, but the main result we had is, indeed, we could demonstrate that by building on top of this primitive swimming circuit, we were able to generate a very rich set of movements, both for swimming and walking, and especially make this transition from swimming to walking just by playing with two descending drive. So if you remember this image of the puppet on string, in this case, we have two strings. If we activate a lot both strings, we are in the swimming mode. And if we activate them below a threshold, we switch to the walking mode. And we have a very rapid switch in between the two, exactly like the animal. And steering, interestingly, was obtained very easily by just stimulating more one side of the spinal cord compared to the other. So by just playing with two strings, like you are driving a remote control car, you have a very nice control of speed, heading, and even type of gait between these two. And I think the important message here is really to demonstrate, like this, in this case, a network of oscillators is a very rich way of generating movements. And then by temporally playing with two signals, you can have a very rich variability of motor skills. So this is important because sometimes people think that the spinal cord produces very stereotyped patterns, but no, here we demonstrate you can really modulate this pattern in real time and control the robot locomotion. So obviously, this is just part of the story, because that's for me the beautiful thing of the nervous system. We have many redundant layers of control, and the same motor behavior could in principle be explained by quite different sub-circuits, like subpart of the network. And a very long debate that's still not properly answered in neuroscience is how are rhythms of locomotion generated and coordinated. This is a very old debate going back from 100 years, a debate between Sherrington, who was seeing locomotion more as a chain of reflexes, very much driven by sensory feedback, versus Brown, interestingly, his PhD student, who had an opposite view. He was thinking the circuits are much more driven by oscillators, built-in oscillators, and like much more feed-forward controller. And I recommend you to read this very nice conceptual paper by Art Kuo, who very nicely demonstrates how you could drive a pendulum with two stimulated muscles and get more or less exactly the same kind of limit cycle periodic behavior with your pendulum by either being purely sensory driven, as on the left, or purely CPG driven, so driven by a neural oscillator which outputs to the motor neuron. And so this is a very fundamental question to see, okay, all the rhythms we see, are they more due to peripheral control, meaning sensory feedback, or more central control, meaning the central pattern generators? And this directly relates to typical trade-offs in robotics, is feedback control versus feed-forward control. So this is nowadays a big topic of research in my lab. And to address this topic, it's where you need the body. The embodiment becomes a key feature here. And that's really the link between the two. And robotics can be a beautiful tool to scientifically to include robot bodies in models, basically, and studies. And just to illustrate this famous dynamic walker by Steve Collins and Andy Runa and others, that showed very nice, pretty stable locomotion without any motor, without any sensor, purely mechanically driven, and with energy coming from a slope. Or here on the right, this is very nice work from Jin Liao, where he could show that this trout can nicely swim in a stream of vortices being generated by this half cylinder. And what's special here is that this animal is dead. So it's a dead animal. This is purely the viscoelastic properties benefiting from the vortices in the water. And this, for me, these two videos really demonstrate to what extent the embodiment is important. And you could kind of guess that just extracting signals out of these bodies could be sufficient to generate locomotion, like resonant modes of this mechanical system. So these days, in a project funded by the Human Frontier Science Project with several colleagues like Akio Ishiguro and Emily Standen here, we're exploring exactly this question to see this interplay between neural oscillators and sensory feedback. And we have this central hypothesis that it could be that a whole series of different amphibious animals, going from this Polypterus, which is an amphibious fish, to salamander, to centipedes, they might all be benefiting from the same type of sensory-driven synchronization of fairly loosely coupled oscillators. So it's a kind of interplay between oscillators, but with fairly weak direct coupling and a big influence of sensory feedback to synchronize patterns. So I don't have time to go in detail, but the key idea is that, first of all, sensory feedback, of course, plays a very big role in handling perturbations. So this is easy to show in simulation, like this is some older work we had done and Eckerberg had done as well, is where if you swim with just the neural oscillator part of the circuit, if you don't have feedback in the loop, you are very rapidly into problem. You enter into problem if there's perturbation in the environment, like non-steady state flow, like bigger forces here. And interestingly, in the lamprey has receptors which are stretch sensitive, which locally feed back into the oscillators. And these provide beautiful local synchronization mechanism to kick out perturbations and stiffen out the mechanism. So sensor feedback clearly has a very important role to play in handling perturbations. But nowadays, we think sensor feedback can do much more. So if I go back to this drawing here, and obviously I cannot present the results because they are under review, but we feel that locally pressure-based feedback plays a very big role in making the system very redundant and helps a lot to synchronize oscillators and possibly even to generate rhythms. So you could generate the same swimming pattern either by, on one hand, being purely CPG driven, like feed forward. On the other extreme, you could be exactly the same pattern, produce it by being sensory driven. So I don't have time to go into detail, but that makes the system super redundant and explains how you can have a very robust control mechanism. So robust that in principle, you could even split the robot in different parts and have it still locomote because you have this local oscillator and local feedback loops in the system. Okay, so to summarize the salamander work, you have a beautiful network of CPGs to handle rich locomotion. You have lots of local feedback that helps to handle perturbations, but even better than that, to also participate to pattern formation. And the two together create some kind of self-organized locomotion with a very nice interplay of oscillators, biomechanics, and sensory feedback, which make this system incredibly robust and redundant. So if you make lesions in the system, you can still locomote in many cases because you have two kind of systems in parallel to do locomotion. So that was a bit the salamander part. I hope this was clear up to now. If I have still 10 minutes, is that fine, Mozen?
10 minutes is fine for you.
Yeah. Okay. Yeah. I'll do it fast. I'll jump evolution. So in 10 minutes, we do like 200 millions of years in evolution, and we now switch to human locomotion. And here, interestingly, in humans, we still don't know the role of neural oscillators and if they exist or not to drive human locomotion. So the role of the CPGs, these neural oscillators. So in humans, being mammals, locomotion is much more unstable. So compared to salamanders, which have a low center of mass, a large support polygon, if you go to any mammal, the center of mass is much higher, the support polygon much smaller. So you have much more unstable problem. So it's kind of obvious that you need more sensory signals and you need more descending drive to locomote. And people have made beautiful neuromechanical models of human locomotion. I present some here. And one of my favorites is one by Hartmut Geyer and Yu here in 2010. Because they have made a beautiful model that could replicate many features of human locomotion. But interestingly, they're purely sensory driven, completely driven by reflex loops, no neural oscillators. And Hartmut is a good friend, but I found his model very annoying because of that. Me being a neural oscillator person, I was frustrated to be able to have such good locomotion skills by just being driven by sensory feedback loops. And the kinematics look good, the ground reaction forces, even the simulated EMGs look good. So it's really a good model and works well. We replicated it, works very well. So then you might ask, is there any benefit to plug back in this type of neural oscillators, the central pattern generators, the neural oscillators we find in lower vertebrates, to this sensory-driven model? And we feel a set of neural oscillators could really benefit, really be beneficial. We believe it helps to the control of speed. It helps against robustness in sensory noise and failure, and it helps in reducing transient times. Because in the sensory-driven model, it's quite hard to control speed, and it takes quite some time to reach steady state. So what we did here is a bit the opposite of what we did in salamander work. So we started by a sensory-driven model, replicating the model of Hartmut Geyer and Yu here, and then added on top of that a neural oscillator model, a CPG model, which tends to generate waves forms which are more or less the same as the sensory-driven ones during steady state. And we still have some control signals like frequency and amplitude we can modulate with descending drive. These are like the strings applied to the network. So I go a bit fast, but we then very systematically studied to what extent every joint could be, what's the optimal way of controlling it? Could it be purely feedback driven with the sensory feedback loops, or purely feed forward driven by the CPGs, or some combination in between the two with an open parameter alpha that we systematically varied. And we have like 25 open parameters. To explore this parameter space, we run an optimization. In this case was a PSO, particle storm optimization, with a fitness function where we try to reach a desired speed. And the main criteria was reaching a desired speed and minimizing energy. And surprisingly, in a fairly few number of iterations, you get a stable gate that has all these human-like features like Hartmut Geyer's as well. And the added value, I may skip just this, the added value is that we could then very nicely control the speed by just a single control drive that was changing the intrinsic frequency of our oscillators. So no need to play with multiple reflex gains, but just driving more or less the oscillators for the limbs, we could have a very nice control of speed over a big range and really confirm our first hypothesis that in principle, adding an oscillator in the loop could really help controlling and simplifying the control of speed. And yeah, that's the main message. It's really beneficial to have both the feedback loops and the CPG in this network. Interestingly, we found out that if you look at this hypothesis having different oscillators for different joints, like that was proposed by Stan Grillner initially, we believe it's most beneficial to drive mainly the hip joints by the oscillators, and the rest can be sensory driven. So you could have a kind of gradient where the more proximal joints are mainly driven by oscillators, and the more sensory, the more distal ones, like the ankle, can be more sensory driven. And Monica Daly found exactly the same thing in a separate study. So very rapidly, why is this interesting for robotics? It can be interesting because it produces stable locomotion. So that's why we are so good at doing locomotion once we have learned it, is our spinal cord has this pattern generated, it has all the reflexes. And that's why you don't have to think about it when you locomote. It's really your low-level control that's in business to give you a very high stability. And this could be a very interesting low-level controller for a humanoid robot, for instance. Obviously, if you make a big perturbation, you still want your cortex to be there to avoid that big perturbation or to stand up. So don't throw away your cortex, but at least for the low-level aspect, your spinal cord is good enough. And here, last 3 slides. That's why it's so frustrating in paraplegics, the fact that in humans who have a spinal cord injury, all these low-level locomotion controllers in the spinal cord are generally still intact. They just lack the strings. They just lack the communication channels to reactivate those. So one big hope is to stimulate them electrically, to reactivate them electrically. And that's a beautiful approach that people in neuroprosthetics do, also here at EPFL. An alternative approach is to have an exoskeleton to help with locomotion. And here, some work we did with Herman van der Kooi here was to, in fact, use our neuromechanical models, as we have here, as controllers in real time for an exoskeleton. And here is a paraplegic pilot that's completely paraplegic, so cannot locomote at all. But here, thanks to the exoskeleton and our neuromechanical model that's now a controller, it runs in real time. So we simulate muscles, we simulate the reflexes mainly. We have now a nice self-generated locomotion controller. So we don't prescribe a desired pattern. It really comes out of running the simulation. And what's interesting is we still benefit from all these low-level reflexes to have to handle perturbations. If you push the limb forward or back, the reflexes will correct this as an emergent property. And that's really the beauty of the spinal cord. That's what the spinal cord offers for the rest of the nervous system. So it's still work in progress, but we believe that the nervous system, spinal cord model like this could be beneficial for robotics and exoskeletons as well. So just to conclude, I really believe the spinal cord is a beautiful and sophisticated circuit, really beautiful to help locomotion and motor behavior in general, so that you can produce rich motor behavior with only a few descending pathways. CPGs and sensory feedback are very good friends, very redundant. They really contribute to each other to make the system very robust. My speculation is that their respective role have probably changed during evolution, as mentioned, by having more importance in CPGs in lower vertebrates and more importance of sensory feedback in mammals. And finally, for a message to roboticists, I really believe this kind of inspiration from a spinal cord control can be a beautiful low-level building block in a bio-inspired locomotion controller and a very robust and fault-tolerant mechanism. Okay, so that was it. Sorry for the rush a bit. I wanted to stay in time. I just want to thank the people here who did the actual work and the funding, of course. So I will stop here, and thanks a lot for listening so far.
Thank you very much. It was very impressive presentation and work. So now we are moving to the interactive session together with Ak and Manuel. Manuel, are you ready?
Yes.
You should unmute,
okay.
Manuel.
Yes, I'm here.
Okay, you are here. Is there any question here? And before that, I would like also to invite Alex Pitti as well as Marcel. Actually, Marcel is the head of the lab. Pablo is working under his supervision. And I would like also to invite him to come here.
You asked me to come here to ask a question? Or?
If because Alex, I saw you were asking some questions, or you were adding some comments in the chat. I think maybe you can ask a question here, or Marcel as well.
Okay, just sorry. Thank you for your talk. Okay, my question is isn't that a feedback reflex plus CPG or rhythm oscillator can be a chaotic system and can be seen like that? Thank you.
Yeah, very, very good question. So as you know, any pendulum driven by an input, rhythmic input, can very easily become chaotic. So you're right, it could become quite chaotic. In our case, interestingly, as soon as you close the loop and put feedback back into the loop, you tend to have limit cycle behavior. So really periodic behavior that is really periodic and not chaotic. But I like your point, because in principle, it's a very good idea to be chaotic or to be quasi-periodic, because being purely repetitive is a bad thing to do, especially if you're a bit stuck. So having a bit of notion of exploration through chaos can be a very good thing, like exactly what this trade-off in reinforcement learning by exploration. The chaotic behavior could be a very nice way of exploring a bit around the limit cycle behavior. So in practice, due to noise and everything, I guess our systems are not exactly periodic, but have a bit of quasi-periodic behavior and therefore a bit of chaotic behavior. But good point, yeah.
Thank you.
Is there any question here? Other question?
Marcel, did you have a question, or you just decided not to make it?
No question from my side.
Okay.
So we have.
Yeah, William Norse wants to make a question.
Yes, William Norse is here.
Yes, I have a question for Manuel. So I liked your talk where you're talking about how maybe this splitting up of these approaches, right? So trying to solve each individual part isn't maybe the best way to go. But one of the big things in robotics is guarantees, right? So guarantees of performance and guarantees of safety. And one of the big arguments against I guess one of the big arguments for splitting up and solving each individual approach is that it's a lot easier to have guarantees on the safety and performance. So I guess, what are your thoughts about sort of this more solving the solution instead of splitting up into the problems with that kind of perspective?
Again, and especially for PhD students, I also do the decomposition, right? I know the problems are too hard, so everyone does that. So just I was doing more a speculative thing. Of course, usually you make guarantees. When you do small things, you can guarantee, right? But I've never seen anyone proving anything at a robot level, right? You can prove maybe that your reaching is stable, but I've never seen anyone proving anything about my vision can detect my object, my arm can reach the object, and my hand will grasp it. You prove that your grasp is stable, that your vision has 98% recall, and but I've never seen any proof about if my vision, my arm, and my hand will work together. That's my point. Okay. That's what I would like to see, more systems approach for robot.
So any other question here?
Yeah, I might have a question if so the people gets more active somehow. I have a question for Oike. Thank you for coming. Every time I see your work, I'm impressed, and it's like I want to leave science forever. Anyway, so thank you very much. So my question, it will be like, you are talking about this kind of sensory feedback that is actually helping to develop new kind of movements that actually makes the CPGs to go to different regions of stability somehow. So my question here will be, so how do you think that this can scale up to actually to have some kind of inhibition control that we have also in that humans we have, like for instance. So how we can link these two things together, and maybe you have a bigger, better overview of that, of these two worlds.
Yeah, I think this is a very good question to see how, and it's still, I think, not clear to me, and not so many people have a clear idea of how we are able to do planning and sequencing of complex motor behavior while taking into account spinal cord dynamics. So I don't have an answer to you to that now, but I just submitted the ground exactly to address that question, because I feel, and maybe it's a question to Manuel as well, I feel we completely underexplore this, or at least people in neuroscience. Many people in motor cortex, they sometimes forget that there's a spinal cord in between what they do and the muscles. And it's obvious that we don't do planning in muscle space, we don't do planning in joint space, but we do a lot of planning in planning the spinal cord signals, like the strings to the puppet. So our brain must have an inverse model of the spinal cord. It must have, because then only you can plan movements. Then you can know which sequence you send to the spinal cord, which itself will send to the muscle. So for me, that's still a big mystery. I think what happens is, at the brainstem level, we have all kind, and we know it from simulation, you have all kind of little motor behaviors, like a cat. If you stimulate one part of the brain of a stem of a cat, it will crouch, another part it will jump, all that. So I think with the basal ganglia, the cerebellum, and the motor cortex, we are able to have this inverse model and know, okay, now I should sequence this signal, stimulate these pathways to then sequence different motor behaviors. So I don't know if it answers your question, but I think this is a key scientific topic in neuroscience that few people have properly explored yet. Manuel, maybe what's your point of that? Would you agree?
Yeah, I think that's an example, right? You cannot, I know the decomposition, we don't understand the combination of the systems, right? You have a nice work about the CPGs and stability of it, but I know if you put vision and all this, it's a combination. It's very difficult to understand.
Yeah, actually, I was looking also that Matt, Professor Botnick, was around and say something about this, but I don't know where is he right now. But we will have him afterwards. But it will be nice to have also his view about this specific topic.
Yeah, let's
maybe
get into
so he's coming. He's coming.
Yeah, let's maybe talk about that later for sure.
Okay, but you don't want to comment anything?
So hi Matt, do you have any question here, or do you have any comment? Let me unmute him.
About the motor primitive stuff?
Yes.
Yeah, I mean, I find it totally fascinating. It does seem to me like on the pure engineering side, people are getting better and better at learning complex behaviors sort of in a more end-to-end way. Sometimes starting from, mocap data and so forth. So, of course, what I'm thinking of is all in simulation, though. So I wonder, I mean, in terms of drawing inspiration from neuroscience or biology, how do you see the role of this kind of hierarchy? How central do you think it's going to be in the future?
Is that for me or for my yeah, no, absolutely. I think that's the that's a bit of the nervous system. If you have a hierarchy and at some point the planning you do at a high level will be a planning of how to combine motor primitives. So that's a really decomposition of in building blocks of motor behavior. At the same time, all the while you do this kind of activation motor patterns, I think there are many descending pathways that will do always fine-tuning in real time. That's why having all this state information still going up to monitor all the afferents, the corollary discharge, as it's called, like where your high part planning is checking your sequence and checking if the state is correct. that will always be important. So we should never, sometimes people criticize me being too simplifying. So of course, this multi-layer information goes there. And that's for me also the beauty of locomotion is the same gate, I'm really convinced you can make the same gate at the spinal cord level and at the cortical level. And some gates you make only at the cortical level because they're really strange. You never do that. Your spinal cord doesn't know about those. And there is a hierarchy where you can bypass to some extent the pattern generators if you want to, if you need to.
Yeah, this is not an area in which I'm at all an expert, but I was just lucky enough to collaborate with some people at DeepMind on a paper about hierarchy and motor control. And one of the things that really struck me in kind of being forced to catch up on that literature is how little the cortex actually seems to do, especially in rodents. It's almost hard to figure out what you need the cortex for, except for very unusual circumstances. Is that your impression too?
Yeah, I think the cortex is there as an internal simulator for me, to a big extent. So to do really long-term planning and everything, because people might not know, but exactly, you can have cats living without cortex. They have visually guided behavior. They have all kind of reactive behavior, even a bit planning, and they don't have a cortex. And the only place where you see that they're a bit different, they're a bit more aggressive than others. So it's surprising how the cortex is a beautiful thing for us as humans, but indeed surprising how redundant it is, and you can perfectly live without a cortex. So indeed, it's amazing. Yeah. And not many people are aware of that, the fact that you can have mammals surviving perfectly well without a cortex.
Well, hi, okay. Well, Mosen, I'm Gerardo from Glasgow University, and Mosen asked me to come to the stage. We have worked on sequencing behaviors in a very high level point of view, using simulation, for example, for grasping, driving these motor behaviors. We have used reinforcement learning, and we have shown that it can actually train really fast. So you work on these generators, supports this embodiment within robots, and probably a pathway to make robots to make useful stuff. Because I think that goes back to Manuel observations that we don't really have a systems integration approach in which we have useful systems. So from your perspective, what will be the generators, how they will fit within, for example, in the industrial context? How can we make useful applications out of it? And thank you, excellent talk. I really enjoy it.
Okay. Yeah. That's where you need this inverse model of the spinal cord, because you need to find a way of how to play with these strings. And some building motor primitives are really easy. So you, like the steady state locomotion, just put the drive and you have a proportionality between frequency and therefore speed and the drive. In other cases, you need to superimpose a few more motor primitives that will be just acting on some joints, some other joints. So for me, the challenge in terms of learning is that you have a very non-uniform control space. Except sometimes you play on a global effect, sometimes a local effect. So it helps you because you have fewer strings, but it's a bit challenging because some strings have different effects. So the key part for me is to have some kind of inverse model so that the high level levels can play with them properly. But then it should help reinforcement learning because your dimensionality is much lower than if you had to control directly muscle fibers. I don't know, Manuel, what would be your point?
I think you have a point, like you're studying biology and the salamander, right? You have a nice decomposition that was evolved, right? And then you have been studying and researching this decomposition, how good it is, right? And you found many things. I think we have a problem in robotics that for a new problem, like Gerard was talking about an industrial application, is that for a new problem, we don't know how to decompose. We don't know how to make, we don't know how to synthesize a decomposition that is useful. So what we do is that we decompose what we have, right? We have the modules that you can download, and I think we cannot create decompositions for new problems, and sometimes we just do the compositions that we can do. So I think it's a difference, synthesizing and analyzing.
Mm-hmm. Okay.
So great. Thank you very much, Manuel and Ake. We really enjoyed. I do agree the virtual conference and workshop is better than the physical one because we can save time and we can bring you here and learn from you. So thank you. So we have to go to the next part, which will be the presentation from our contributors. I think, Mohammed, you will be the next, right?
Yes, can you hear me now?
Yes, we can hear you here.
I'm going to share my screen as well. You can see that?
Yes, we can see here.
So yes, so hi, I'm Mohammed. I'm a PhD student at Oxford University. I'm going to tell you something about variational inference for predictive and reactive controllers. We take some inspiration, just a little bit, from the active inference framework, which is often described as a theory of the brain. And you often see this term unified framework for perception and action. And essentially, you have one general cost function, the variational free energy, and minimizing that can give you both your state estimation and your control. So this has been recently used in robotics applications. I'm going to give you a quick walkthrough of what happens. So generally, you have a state, which is a blue node in this graph. You have a prior over your state. You have an observation, which is a value you just have from your sensor. And you have some model about your sensor. And what you typically do, well, in something like a Kalman filter, this prior, let me point at it. This prior right here typically is some kind of prediction step. So given your previous state, your previous actions, what's going to happen here. But in active inference, you bias this towards a target state or a desired state in the future. So these two blocks are essentially two distributions, and these affect your estimated state. And you can have different ratios for which one is more important. And this is summarized by this plot right here. So the dashed blue line, which starts at 0 and minus 0.5, is the true position, is the real system. And you see it oscillates and then the oscillation decreases. If I only rely on my measurement, so I only rely on this block right here and very little on the other one, I get a state estimate, which is very close to my true system because I mainly look at the sensors. And the more I bias the system towards the target, the further away I am from my actual state and the closer I am to my target, which is at 1, which is given by the dashed black line. And why do you bias the state? Well, because afterwards you can do control. And the more you bias the states toward the target, the more aggressive your control is. But where is the control coming from? Because actually this model right here only has two variables, a state and an observation. Like, where is the control action? And that's something that we identify as the first drawback of this approach. You don't explicitly have a control action. And what you end up doing is doing some transformation with the observation to get some kind of control action. The second thing, which I find quite strange, is it's called a unified framework for perception and action. Yet your estimated state is not accurate. It's always biased unless you're at your target. So to be able to do any type of control, you have to bias your state. And finally, and this is like slightly parallel work, when we want to learn model parameters, it becomes actually very hard with the bias. And let me show you why that's useful. So let's say I have this robot right here, and it's supposed to simply reach some target like this. It's supposed to start at some state and it moves to another. If I if I change the model parameters in a non-optimal way, those correspond to the controller gains, and you get undesired behavior like random oscillations, and it never decreases. So ideally, what I want is to learn those parameters, which are the controller gains, and thus stabilize my controller, something like the following. And in this video, learning the model parameters works, but actually there are a lot of theoretical issues with it, and a lot of other cases it won't work as well. So how do we overcome these limitations? Well, we use a model that explicitly models the actions and gets away from the bias. And there are a lot of ways to do this. One specific case that I'm showing here is similar to what we had before, just don't bias the current state, and we introduce a future state, and then we combine them with a separate control action. And this still has the same properties. It's still, you can get one cost function for the free energy and minimize it to get everything you want, but it gets rid of the other problems. And just for the interest of time, I'm going to show one piece of results in this specific case, which is about including predictive behavior. So if you only rely on reactive controllers, so waiting for errors, your system will inherently always be slower. So if I want to track this dashed black line, the best I can do with a reactive controller is actually the red line, which is always delay. But I can, if I include this future state, I can predict what's going to happen next and account for it. And I can also add feed-forward signals quite flexibly here. Do I have time to show one more result, or?
If it takes like 30 seconds, not more than 30 seconds would be.
Actually here. So actually other things we're looking at the moment is generalizing this approach. And there's a lot of related work, for example, on planning as inference, which is very similar, but not quite the same. And that's a work in progress at the moment. And also we've been looking at extending the computational approaches we have. So generally you just assume everything is Gaussian. We do something called the Laplace approximation and we simplify everything. But we have like a short piece of paper here on extending that to non-Gaussian distributions, generic variational inference and stuff like that. And I guess that's 50 seconds. If you have any questions or want some of the code that's not released yet or anything like that, just shoot me an email, mohammed@robots.oxford.ac.uk. And thank you for listening.
So thank you very much, Mohammed. So if you have any question from Mohammed at the end of the sessions, there will be a time to ask questions from any contributors. So we are moving to the next one. Elnaz, are you ready?
Yes.
Okay, so we are, so stage over to you.
Okay. Can you see my presentation?
Yes, we can see here.
Okay. Okay. So my name is Elnaz Soleimani, and today on behalf of our author team, I'm going to present our work on robot semi-supervised adversarial transfer learning for human activity recognition problem. So I will start by an introduction on the hard problem and transfer learning, and I will explain our proposed model. Then I will shortly review the results that we have, and we will see the conclusion and future work of this research direction. So in this work, we focus on sensor-based hard problem in which we have a human user wearing a set of wearable sensors. And basically the objective here is to predict the ongoing activity based on a window of sensors outputs. But most of the classifiers, they are trained based on a hard-specific dataset. And the problem that we have here is that the dataset have a limited number of samples and subjects. And the models will face a performance drop-off when they deal with unseen samples from new users, because everybody is doing the activity in their own way. And so the conditional distribution of the classes will be different from one subject to another one. So that's where transfer learning can help us to improve the classification performance. So in our proposed model, we are using a GAN framework. And as you may know, that in classical GAN framework, we have a discriminator and generator module. But we are facing some challenges here. And some of the challenges are related to the GAN framework itself, like the instability and mode collapse problem that we are trying to solve it by using, by adding up a classifier component to the GAN framework model. And also we have some problem in terms of imbalanced distribution of samples. And we came up with the idea of a micro mini batch strategy of learning, and I will explain it in a few slides later. And finally, to avoid the negative transfer impact, we are focusing on one-to-one subject translation, which means we don't augment the samples that we have from all the subjects because of avoiding the negative transfer impact. So as you can see in our proposed framework, we have a semi-supervised setup, which means that we have samples from source domain with their labels, and we have samples from target domain without any annotation information. So it's a semi-supervised setting. So what we want to do is that using this adversarial framework, we want to draw the samples of target domain as close as possible to the samples of source domain in terms of distribution, so that we can assign the same label of the source domain that we already have to these samples of target domain and retrain and update the classifier at the same time. So at the end, from this whole framework, we will take out the classifier and we use it as a transferred model to classify the, to recognize the activity of target domain. But as you know, it is highly recommended to train the GRANT framework in batch mode. And this batch training will even aggravate the problem of imbalance in the in terms of distribution in the data set. So what we propose to do is to make micro batches of the same size from all the classes and combine these micro batches together to create a mini batch of data. And then we can train discriminator, classifier, and the generator sequentially using these micro mini batches of data. So we have evaluated our model with 3 different data sets with different size and number of classes to actually evaluate the robustness of the model to the challenges that we mentioned before. And as you can see here, for example, if we transfer the knowledge from subject 4 to subject 2, we are able to beat the other state-of-the-art model in terms of weighted F1 score measure of classification. So if I want to recap, we proposed a semi-supervised adversarial transfer learning model, which is robust to imbalance distribution of data. And we were able to improve weighted F1 score of the classification up to 23%. And for the future works of this research direction, we can consider using multiple sources of knowledge and actually dealing with the negative transferring instead of bypassing it. And also we can think of ensemble combination of the transfer model, which have been trained on different sources of knowledge. So thank you for listening. And if there's any questions.
So thank you very much, Elnaz. I think we can hear from you during the poster session. So I'm going to close this session and I will give the stage to Pablo and Natalia. So we're gonna have 2 very interesting talks by Matt and by Mehdi Khamesi.
So thank you very much, Mohsen. Sorry for the noise. We have like motorbikes passing by me right now. So actually we didn't have any break because of the nice discussion that we had. We prefer to give importance to the discussion than to eating. So let me mute some people, yes. So I think we are going good. I'm losing my sugar blood, but I think we have to continue because we are on time. And we want to thank again the speakers. This is BRAIN-PIL workshop. We have amazing speakers today. It is exactly 2:39. We're running 9 minutes late, but we have a nice blog right now that I will be hosting, and also Natalia will help me. And specifically, we will have right now Mehdi Khamesi and Matthew Botvinnik. We are really thankful for this specific part. This is the most close part related to actually neuroscience. What I can say, I will start first introducing Mehdi, and then I will go for Matthew. Let me open. I have like 1,000 things open. One second. Can you take care 1 second, Mohsen, that I'm looking for one thing?
I think Mehdi is here, right?
Yes,
yeah, can you look for Mehdi and start
Can you hear me?
Yeah. Yes, we can hear you. Yeah.
Great.
So maybe, Mehdi, you can share your presentation here.
I need some authorization to do so.
Okay,
yes. 1 second. Yeah, now.
I think now you can share it.
Yes. Can you see my slides?
Great. Yes, we can see your slide here.
So, okay, great. So let me introduce Mary. Thank you. Sorry, I was looking. Let me introduce Mary. Actually, correct me if I say wrong, okay? Because I just translated from the French to the English. So you are actually a tenure research scientist at the French National Center for Scientific Research, the CNRS, right now.
Yeah. In
the Institute of Intelligent Systems and Robotics at Sorbonne University, right? In Paris, France. And actually his interest is computational, behavioral, and brain mechanisms for online adaptive coordination, and also learning processes in animals and robots. And today the talk will be related to hippocampal replay through the lenses of reinforcement learning. So thank you very much, Mary, for being here. Please, the stage is yours.
Yeah, thank you very much for the organization and making it remotely. Actually, Juntani this morning showed a nice picture of his building in Okinawa by the sea. And it gives me the opportunity of a small anecdote that actually Tansu, Selikel, and myself, we met many years ago at Okinawa Computational Neuroscience course organized by Kenji Doya. But at that time, the building that Jun showed did not exist. But so nice to see you again, Tansu. Yes, I'm going to talk a bit about hippocampal replay through the lenses of reinforcement learning, and really in between computational neuroscience and robotics. So what we do, so I'm working in a team that is called Architectures and Models of Adaptation and Cognition. And what we do is really interdisciplinary research where we use tools, methods from engineering science, applied mathematics, to try to come up with computational neuroscience models of the brain. And then in the other direction, we take inspiration from what we understand about biology to try to improve robot decisional autonomy and behavioral flexibility. And so a lot of the things we are interested in are trying to understand but also take inspiration from the way animals seems to be able to adaptively alternate between different learning strategies. And so in the reinforcement learning framework, people put a strong emphasis on distinction between model-based reinforcement learning and model-free. So model-based is illustrated on the left, model-free on the right. And here for this illustration, I'm showing a classical task in a neuroscience where a rat has to navigate in a small pool and find a hidden platform, which is a hatch circle under the water. And so model-based strategy consists for the animal to explore and build progressively a mental representation of the task structure, so what we call a cognitive map. And so making a decision with this cognitive map consists in planning or trying to find the shortest path in a graph. So it takes some time to make this decision, because if the graph is big, then you need to propagate and find, maybe use heuristics, prune some possibilities and so on. But when the environment changes, that the second figure you see, for example, the goal location changes, you can simply update your internal model and replan. And so this strategy results in very fast adaptation to changes in the environment, at least changes in goal location. But the thing is at the expense of a high computational cost. Each time you need to plan, it takes a lot of time. On the right, you see a model-free alternative strategy where the agent, we suppose here, is not trying to model the environment, but it's just locally learning what is the best action to perform. So it's as if after learning, you have built a vector field and it attracts you towards the goal location. But then if you change the goal location on the extreme right, then you need to relearn locally so that after a few trials, maybe you know what to do when you're close to the new goal location, but you're still attracted by the previous platform location, and it takes a lot of time to propagate to the rest of the environment. So a model-free learning strategy here is very inflexible to changes in the environment, but it allows you to make very quick decisions, because you just need to compare a few values before deciding what to do. So just to be formal and to be clear, when, the convention in reinforcement learning, when you say model-based, is really manipulating two functions, a reward function and a transition function. And transition functions can be a probabilistic function, which tells you from any given state action couple what is the probability of arriving in another state. So model, can be used in many different ways. And for example, in Bayesian framework, even representing, estimating a distribution over a hidden variable is already a model. But here we really talk about models when we talk about these two functions. While model-free, you don't manipulate these functions and you try to learn a state value function, a policy function, or so on. So I just want to say briefly that we've been working for several years on designing computational models of how the brain might coordinate adaptively different learning strategies and to explain behavioral, lesion, neurophysiological data, but sometimes we also apply these models to a simple robotic task like navigation. And I'll show an example at the end. So here what you see on this scheme is 3 strategies, so 3 modules. You have an exploration which is external, which is a way to avoid to having exploration in each of the strategies, which might make the agent overall explore too much. You have an associative strategy, which simply learns by model-free reinforcement learning to associate some input information, for example, cues that you can visually see, to actions. And you have a model-based strategy, which actually receives some place cell information from hippocampus, so estimating the position, the state, and you can build a planning graph and propose actions. But in addition to that, we usually really investigate how we can efficiently coordinate these strategies. And for example, here in this model, we have an adaptive, a meta controller, we call it, which is an associative module, which in this work learns through model-free reinforcement learning. We can talk about that if you're interested. We have different versions when we try to explain data in neuroscience where it's not learning, but you measure some uncertainty and different criteria. And here, the meta controller is not learning to select actions, but it's learning to select strategies, which strategies is the most efficient. And this simple way of coordinating strategies seems to be a way to allow artificial agents to really take advantage of the strength of its strategy while avoiding, for example, the computational cost of planning when it's not necessary. So the questions I want to address in this presentation are at the interface between AI, robotics, and neurosciences. So from the point of view of AI robotics, what kind of prioritized experience replay can improve learning efficiency? So in AI, when people talk about experience replay, is the idea that the agent can store its experiences at each time step. It can store in which state it is, which action it has performed, what was the resulting state, whether it got a reward or not. So it can accumulate this into a memory buffer. And every now and then, the agent can randomly pick a few of these experiences and just replay them, and it actually bootstraps learning. You have other set of work where people propose not to pick randomly from this memory buffer, but rather give some priority to elements that were associated to large surprise when the agent was interacting with the environment. So, for example, one possible measure of surprise is the absolute value of the reward prediction error. So when you get a non-predicted reward, that's surprising. So maybe you should replay these states and consolidate there. So some issues are that these methods are computationally expensive. So one question, can we improve them, and can they work on real robots? So that's some of the things we are interested in. From the point of view of neuroscience, the question is, how does the brain prioritize this replay of memorized experience? And here we are particularly interested in the hippocampus, because the hippocampus part of the brain is known to be important for episodic memory. It contains place cells and contributes to a cognitive map. And actually, it turns out that these hippocampal place cells are reactivated both during sleep, but also during moments of quiet wakefulness. For example, when an animal, a rat, is waiting between 2 trials and it's just looking around, and sometimes you see those reactivations. So the question is, can this model-based, model-free reinforcement learning framework account for the dynamics, the properties of these hippocampal replay events? So just a few words about hippocampal place cells, because that's a workshop that participates to a robotics conference, so I don't know if everyone's familiar with it. So briefly, place cells are neurons in the hippocampus whose activity is selected for particular location in the environment. So what you see at the top of this figure is an animal running on a track, and you have, for example, cell number 4, which will be active, so it will emit action potentials only when the animal is at the beginning of the track, and when the rat is moving, the cell becomes silent, and then you have another cell that responds for the next location, and so on. So if the animal is running, and if you measure brain activity, what you will end up measuring will be sequences of activations of hippocampal place cells. And at the bottom of this figure, what you see is recordings of many cells in a square environment. So each square that you see is the activity of one neuron, and the dark blue is when the neuron is silent. So you see that many neurons are silent. Red is when the neuron is very active. Actually, you see a few neurons that are always active everywhere in the square box. And you also see some neurons that have a receptive field, which is either at the center, southeast, some have two receptive fields and so on. But as a population, we think that they contribute to encoding an estimation of the position, which contributes to a cognitive map. And about the fact that the hippocampal place cells are reactivated during sleep or quiet wakefulness, I like very much this example from David Foster and Matt Wilson, where it's an animal that was running in some maze, and so the center is showing you the sequence of activations of a number of place cells when the animal is running, but then you can look at those red and blue zooms, and what you see is in a much shorter time scale, the animal was immobile, waiting for something, and you see the same sequence of neurons reactivated, but much faster. And sometimes it occurs in the same order as what has been experienced by the animal when it was running, so they call it forward sequence. And on the right, you see sometimes it's reverse, so which is interesting because it makes everybody thinks about the reinforcement learning for algorithms such as temporal difference, where you need to propagate reward information to preceding states. So these are actually evidence that hippocampal place cells are reactivated during moments where the animal is not acting. So if we want to account for some of these biological phenomena with the model-based, with reinforcement learning, we have to be clear about some of the hypotheses. So that means here we're making the Markov hypothesis, which means that all the information you have about the present state is sufficient to determine what is the optimal action to perform. Of course, in some of the robotics application I will show you, we have to release these hypotheses and be more like partially observable Markov decision processes. And here we assume that the goal of this phenomenon might be to try to maximize a discounted sum of reward over infinite horizon. So of course, reward in everything I will show you is very simplistic. It's a scalar, 1 or 0, but it can be negative, it can be multidimensional. If you want, for example, like Manuel Lopez presented, take into account information, epistemic value as another dimension, possible dimension of reward. I mean, we can talk about these things, but here it will be simplified to just the extrinsic reward. And how to do that? Well, the mean is by learning and stabilizing state action Q-value function. And so the idea here is that both model-free with experience replay, with a memory buffer, and model-based with inference planning can be used to do offline updates of these Q-values, doing a Bellman backup. And so this idea was formulated at the same time by us and by the team of Marcello Matar and Nathaniel Daw. And I like very much this sentence from their paper, which summarizes this idea that planning and learning are better understood as different variants of the same operation. So using backups in different orders to propagate reward information over space and time. And I have to say, in their work, they really did very nice theoretical work to show from a normative perspective, why is it useful at all to do some replays? And they showed that it can be optimal if you satisfy some assumptions, and they derived a model for this process, which is very similar actually to our model, but with a different perspective. And so one thing that we do, which is original in our paper, is that we allow offline replay at every state. And so the agent is free to stop at any moment and continues to do these replays until convergence of Q values. So what you want to reach is a stability of Q values. And these variations of Q values will be sort of a way to estimate implicitly some uncertainty. So let me just illustrate how doing some model-free replay or model-based reactivation through inference or planning, how it can be done. So here is an example of what you can do when you want to do model-free replay in a forward order. So here I'm illustrating a rat sleeping and reaccessing this memory buffer. So you see each line in the buffer is one element. So with a timestamp, what was the state, the action that was performed, what was the arrival state, so first example, there was no reward, sometimes there is a reward. And this is ordered in memory. So you could process this in forward order, but actually it's not very common in machine learning because it's not very efficient. So if you process this buffer one time, it will be, you will be able to propagate reward information to the preceding state, but not more. And then you need to reprocess the whole buffer a second time and you propagate again. So it's as inefficient as during real world experiment. An interesting idea is to reverse the buffer. So that was proposed by Lin in '92. And here, when you process the buffer, a single processing of the buffer is sufficient to propagate to many other elements. So that's why it's more efficient. And it's interesting that, as I showed you, backward sequences are observed in neuroscience experimentally. But you could also simply shuffle the buffer. And in machine learning, it's known that sometimes you need to break the structure of the data, especially when you have a continuous state space where you might have interferences between a presentation of different states. Now let's move on to how you can do model-based, so sort of prioritized offline reactivation. So one classical way is to do what is called trajectory sampling. So you start from your current state and you sample a trajectory. So you mentally simulate yourself doing a sequence of actions. You can decide to be more or less exploratory during this mental simulation. And actually in our simulation, we show it's important to be more exploratory than during actual behavior. But an alternative, and which is very interesting and very efficient, is to do prioritized sweeping. So you decide to activate in priority those states that have been associated with large surprise, so with large absolute reward prediction error in the world. So here you see, for example, this, I don't know if you can see my mouse, but this state, the bottom left, has been associated to a large prediction error. So you start by this state, you give it a priority, then you propagate to its neighbors, and you can do that because you have an internal model, so you know the neighbors. You recompute the prediction error for those neighbors, and then you focus on the one with the second largest prediction error, and you propagate from this one, and so on. And what is interesting, and I will go straight to the point with this, not only you can be more efficient when you manipulate the model-based, the model, but you can also generate some backward replay. For instance, if you are simulating a maze with constrained corridors and you propagate information with this process from the goal state to state that preceded in time. So it's interesting and relevant for neuroscience also. So let me show you an illustration of how this works in very simple simulation. So it's a task inspired by a multiple T-maze task in rats that has been designed by Dave Reddish and his colleagues. So it's discrete states, and you have an animal that at each trial need to go either to the left arm, so it starts from the central arm, and it has to go either left or right. And during 100 trials, the reward will always be on the left, and after 100 trials, the reward will always be on the right. But here again, I want to stress that our agent makes a decision, learns through classical reinforcement learning, but then in the arrival state, it is free to start doing some replay. And if the Q values are stable, it stops doing replay. So it's just some background activity, let's say, in a simulation. But if the Q values are moving, then it's continuing to do this replay until convergence. And you will see to what it leads. So this is an example of the simulation results with here only for the moment model-free methods. So in black, this is classical model-free reinforcement learning without replay. And in blue, it's model-free reinforcement learning with backward replay. So the x-axis shows you the trials, and you see a trial 100, we have changed the location of the reward from the left to the right. What you see in black is, so the bottom plot shows the reward rate. So you see that the classical reinforcement learning learns very slowly, and then the performance drops after this change of the environment. It's even slower to learn. But a model-free model with backward replay is already super efficient, and it shows some behavior that is very flexible after the change in goal location. Things that on first hand, a lot of people, including myself, would have thought like, maybe that's the sign of a model-based strategy, but not necessarily. And you see at the top plot, it's the logarithm of the number of replay cycles that have been performed by the agent and accumulated during the whole trials over all the possible states. And what you see is completely emerging property of the algorithm that initially it's the agent stops a lot to think and to do these replays, but then when the performance improves, it stops doing replay. That's worthless. The Q values are stable. So, and then you change the goal location, and again the agent will stop and start to do a lot of replay and until convergence. And that's very interesting because experimentally in neuroscience, there's a behavior called vicarious trial and error, where the rats start to hesitate, spend a long time deliberating each time there's a change in the environment. So here it's another set of simulations, but now with model-based methods. And you see that, well, they learn as efficiently. So at first glance, it's not very different than model-free with backward replay. They have similar, so here we tested trajectory sampling, prioritized sweeping, and a combination of the two that I will explain just after. But what you see in terms of logarithm of number of model iterations, so during those reactivation of the model, that trajectory sampling is very inefficient. You spend a lot of time mentally simulating a lot of trajectories, while prioritized sweeping in green is much faster. So now let's look at where in the environment the agent stops to do those, to spend most of the time to do replay. And does it correspond to moments where we know animals such as rats would stop in this type of tasks? And so here it's a plot of the relative proportion of time spent by the agent in each of the states of the environment. And this is for prioritized sweeping. And you see that the algorithm predicts that the agent should spend time only at the 2 reward locations. So the first one, mostly because that's the first reward you encounter in the experience and in the experiment. And then on the right, the second, it's surprising when you find reward there for the second time, slightly less surprising, but you spend most time there. And in contrast, trajectory sampling predicts that not only should the agent spend time doing some replay at reward locations, but also in the central arm, which is actually what has been observed by Dave Reddish and others, that the animal is stopping there because there's uncertainty. It has to decide whether to go left or right. And so this model better predicts it. But as I've shown you before, trajectory sampling is less efficient in terms of computation time. So that's why we thought combination of both might be better. So here I'm arriving to this novel idea of a model-based bidirectional search where we alternate between both. So it's inspired actually by classical planning techniques. And here what we use is model-based trajectory sampling from the starting position, and you simulate some trajectories, but you alternate this with prioritized sweeping, which is triggered from memorized surprising states accumulated in memory, and then you propagate backward, but the backward propagation is again an emerging property. And when both of them connect, you found a route from a current location to an interesting state, and then you can stop and you can act. And actually it's very similar to do that with the theoretical proposition by Matar and Do, where actually from a theoretical point, from a normative point of view, if you want to, I mean, the usefulness of doing a replay can be decomposed into 2 mathematical terms: a need, so how likely you are to visit that state in the future. So it's not very useful to replay some states that you're not going to visit anymore. And gain, so how much reward you think you can get by reaching that state. And actually those 2 terms the 2 heuristics that I've shown you and that we're combining are ways of approaching these 2 terms. But the difference here is that our agent doesn't need to be omniscient to compute this, while in their theoretical framework, if you want to compute these terms, you need to know everything about the world, and you need to decide then whether it's useful or not to replay. So let me show you a last simulation within this framework, where what we are looking at is with this model-based bidirectional search, when the agent stops, in which order the state sequences are produced by the model. So what we see is on the left when the agent was stopping in the central arm, and on the right at the reward locations. And you see that most of the time, when the agent is stopping to do some replay, it generates some forward sequences. So that's the trajectory sampling component of the model, and it's very consistent with what is observed in rats. But very interestingly, you see backward sequences only at the reward locations, because that's there that the agent has experienced some surprising states. And this is consistent with what is observed in neuroscience. And in green, you can see that the agent is also sometimes generating what Dave Reddish calls imaginary sequences. So it's sequences of states that have not been experienced by the agent, by the rat when it was experiencing the maze, but it's just concatenation of sequences that you can reach when you use your internal model to do some mental traveling. And it can generate these things, and that's because you have an internal model with this. So it's interesting that the properties of this algorithm can capture some of the neurobiological data. So I want to finish this talk by illustrating two things more like when going back to the question of efficiency for AI, let's say, but in very simple tasks, and how it works when you apply this to robots. So here is a set of simulations that have been performed by Roy Tile, a master student in our team this year. And he did 4 different mazes that were taken from Matarendo. So the top left is the classical Sutton maze, but then at the bottom left, you have a more sort of constrained version of this maze. And on the right, you see bigger mazes, so an open maze and a constrained maze. And the question here is whether these type of algorithms would scale to more complex situation, and to which extent they would generate really nice sequences backward or forward when the maze is more open compared to constrained. So I'm just showing you one set of simulations. And what you see in the x-axis is the number of episodes that was sequentially experienced by the agent. And at the episode 20, we changed the goal location again. And the y-axis is the number of steps that were needed for the agent to reach the reward. And it's the logarithm of this measure. So look at the first circle number 1. I've highlighted this part of the curve is just to tell you that a simple heuristic like prioritized sweeping gives you a performance which is not different from this optimal normative model proposed by Matarendo. And in addition, when you look at the circle number 2, so after the change in goal location, prioritized sweeping is much less costly computationally compared to an omniscient model that needs to take into account all information about the environment to decide even whether it's worth doing some replay. And that's also reflected with a different figure on the right, which is the number of planning phases that were taken by each of the algorithms. And you see that prioritized sweeping is much less costly in terms of planning time compared to this other model. So it's interesting to think like it's very important to have, of course, normative perspective and why at all evolution might have led animals, mammals to have mechanisms for replay. But on the other hand, then when you want to apply this to artificial agents, maybe sometimes coming up with heuristics can be very efficient and at very little cost. So the last set of results, I mean, even the result figure I will show you in the next slide, are some results we obtained in the lab when we apply this to robots. So we applied this to 2 different sets of tasks. So a simple indoor robot navigation task where there are different corridors, but it's a non-stationary task. So sometimes we introduce obstacles to block some corridors, or we change the goal location. And we also applied this to a very simple human-robot interaction task. So it's a task where the robot needs to pick the blue, green, and red cubes and put them in the correct boxes. So it's very similar to the task that Juntani has presented this morning. And here you can simulate a human that sometimes comes and can intervene in different manners. So he can congratulate, or he can give instructions, say, decide for the robot. And what we do is we simulate humans that do this in a probabilistic manner. So you can have humans that do this only 80% of the time, 70% of the time. So it's more realistic. And we also do non-stationary simulated humans who initially do it and then are bored and stop instructing the robots. But what I want to show you very briefly, I'm not showing you the performance. We have a lot of curves and in these 2 simulated papers whose link you can see at the bottom. But here I'm showing you the cumulated time at the last action. So it shows you the computational cost of the algorithms we've tested. And it's 3 different conditions. So no interaction with the human is congratulating, or the human is taking over. And at the bottom, you see that each time we compare 4 methods. So pure model based, pure model free, a sort of random coordination between the 2, or our criterion, which coordinates them as a function of entropy and cost. I can explain if you're interested. But what is important is that a pure model base has an optimal performance in these tasks, but it's super costly. It takes a lot of time to decide, while model free, pure model free is nearly 0 cost. If you have a random coordination, you're a bit in between, both in terms of performance and computational cost. And with our entropy and cost criterion, we reach a non-different performance than the model-based. This you cannot see in this figure, but okay, you can see in the manuscripts. But what you can see is the computational cost is nearly as small as for the MF. So here you have a way to, at the same time, get very good performance, but also save planning time when you can avoid it, which is very important if you want to think about realistic applications to robots. Okay, so let me summarize what I've presented you. I talked to you about ways to do replay in model-based and model-free reinforcement learning models. I try to emphasize that there could be two different families, a way of doing it. So you can do model-free with experience replay with a buffer, or you can do model-based where you use your model to plan, to mentally travel. I've also tried to convince you that sometimes some simple heuristics like prioritized memory replay can be very efficient. And also I've proposed ways to do this with a criterion, which is you replay until convergence. So the agent was always able to do it whenever it wanted, whenever the Q values were unstable, and will continue until convergence. And this leads to efficient behavior and also reduced computational cost. And I presented you a model-based bidirectional search model, which turns out to mimic some experimental data in most of the time in rat navigation. And finally, I finished by showing you a way where to coordinate model-based, model-free, but also within this coordination, having model-based replay as a way to bootstrap learning in the model-free system. And when you do that, it seems that it has some potential for efficient learning in robots, while again reducing computational time. So I would like to acknowledge the people who contributed to this work, also saying that our work is open source. So if you want to play with the models I've done for the multiple teammates, you can download the code on GitHub. And I would like to acknowledge the funding. Thank you very much for your attention.
Okay, thank you very much, Mehdi. I hope that you don't worry. We just move the questions for the discussion, if you're okay for that.
Yeah, no problem, of course.
So the people can get ready for some questions about reinforcement learning also. And in this moment, actually, Matthew is sharing the screen. I want to introduce Matthew. For me, it's just an immense pleasure to have him here. I was really surprised when he actually said, okay, I will do it. And I really thank you for that, even if it's not in Paris and we are virtual, but at least we are saving some money for the travels and also for environment. I just want to say two things about Matthew, that I think he's one of the persons right now in the world, from my point of view, of course, that he really knows how actually it works in humans, and he can have this big picture of how to move this into artificial intelligence. And I knew him, his work before he actually joined the DeepMind company, and now he's currently, he can just tell me that I'm wrong, but he's right now director of neuroscience research at DeepMind. And also he's an honorary professor at the Gatsby Computational Neuroscience in the University College London. And actually I wanted him to be here because maybe you don't know him from robotics, or maybe yes, but he is an expert in cognitive control and conflict monitoring. And something that for me is amazed me, that maybe is that something that he did a long time ago, but he actually discovered the effect inside the rubber hand illusion that I'm totally obsessed in the last 2 years. So I don't want to just talk anymore. I just want to thank you, Matthew, again for being here. And it's a real pleasure for us to have you here. So thank you very much. Please go ahead. The stage is yours.
Thank you. Thank you very much. Can you hear me okay?
Perfectly.
Yeah, and my slide is visible now, yes?
Perfect.
Yeah, awesome. Okay. Well, let me start by thanking you for that extremely kind introduction, and for the invitation to participate. It would have been nice to be in Paris, but but it's great to be here with you all, even virtually. I am, I guess, a little bit of an outsider to this group in the sense that I don't do robotics, although I have many friends who do. But there's another sort of principal component to this workshop, along which I think we all align pretty well, and that's the idea that neuroscience and artificial intelligence, broadly construed, can help each other, and that's what I'm going to talk about. My title is on the screen. You can see that I took inspiration from Mehdi's title, which I liked a lot. So, and you'll see there's a lot in common in terms of our approach to science. So, so yeah, those of you who know me know that I'm a believer in this virtuous circle between neuroscience and AI research. And in fact, shortly after I joined DeepMind, I teamed up with Demis Hassabis and others at DeepMind to write a paper about that point of view. And we're continuing to push very hard on trying to extract insights from neuroscience. But one thing that's become clear to me as I've kind of planted a foot more firmly in the AI world than I had before, is that really neuroscience, it's not so easy to just kind of go to the neuroscience literature and grab insights and plug them in for AI, mainly because the questions that are traditionally asked in neuroscience are not necessarily exactly the ones that you need to be asked in order to gain those insights. And that's nobody's fault. It's just a question of what the traditions are and what the focus has been. So I'm kind of arriving at the conclusion that if we want to get neuroscience-inspired AI, it may help to do some AI-inspired neuroscience. And that way we can kind of prime the pump and get this virtuous circle really humming, and essentially continually cross-reference. Rather than looking to neuroscience for inspiration and leaving it at that, we can kind of work both sides of the street and keep updating our understanding on both sides in a way that's nicely coordinated. And in that spirit, I'm going to tell you about a particular project that we reported a few months ago in Nature. This is a neuroscience talk from here on, but hopefully it'll be clear why doing this kind of neuroscience might be of use to AI and the way in which AI is driving this kind of neuroscience. Oh, so before I advance, I just want to acknowledge the people who did the real hard work on this project: Jane Wong, Zeb Kurth-Nelson, and Will Dabney at DeepMind. And as you'll see, we work very closely with Nao Uchida at Harvard. So the project is about dopamine. I think a lot of people in this audience will already be very familiar with prevailing ideas about dopaminergic function, but just to bring everybody along, dopamine is secreted by cells that live in the brainstem and the midbrain and send their projections widely throughout the brain. And there's a very famous series of experiments that showed that dopamine neurons respond to unexpected reward, but they also respond to cues that predict reward in exactly the way that you would expect from a temporal difference reward prediction error. So the idea has emerged and it's been validated in a number of ways that dopamine, phasic dopamine activity can be understood broadly as carrying this kind of classical reward prediction error signal, and that the dopamine system is listening to a value estimate, which of course is necessary in order to compute that reward prediction error. And the value estimate is coming from widely distributed inputs from around the brain. So that's the dopamine story as it currently exists. And it's very important that there's this tight link between reinforcement learning theory and the biological interpretation here. Now, there's one thing about this interpretation of dopamine that I want to call attention to, because we're going to tweak it. And that's going to be the motivation for this research that I'm going to tell you about, which is that both in classical temporal difference learning, TD learning, and in the classical dopamine story, which is closely based on it, the reward prediction error and the value estimate are both scalars. They're both just ordinary real numbers. Now, that idea is, that's actually sufficient. That's the sufficient statistic for RL, and that's why the classical theory assigns both of these a scalar value. However, something interesting has happened in one corner of the RL literature fairly recently. A lot of you would be familiar with this, which is the idea of distributional reinforcement learning, or distributional TD. the idea here is, instead of using a scalar value to represent the reward prediction error and the baseline value, what if the system is trained to represent a full distribution for both of those quantities? So for example, in a Miss Pac-Man setting, the agent might be representing its predicted return, its value in this screen state, as something like this distribution. Or in a continuous control setting, you can hopefully make out this little humanoid jumping over a gap. The estimated cumulative return here has this kind of bimodal shape, and as time goes by, that distribution is changing. So what's going on in this little video, so to speak, is that the agent is starting off being pretty optimistic that it's going to make it over the gap, and as time goes by, it starts to worry that it's not going to make it over the gap. But the important thing is that it's representing full distribution over predicted returns or values, rather than just supporting a point estimate. And empirically, what's been observed in numerous studies now is that generalizing TD learning in that one way leads to dramatic enhancements in learning efficiency and in asymptotic performance. So you can just see that very easily in these two plots from those domains. Okay, so there are a lot of interesting explorations now for why distributional coding leads to these performance payoffs, but that's sort of a different topic that I'm going to skip over. We can come back to it in discussion if people are interested. What I want to talk about is this AI-inspired neuroscience research direction, which we pursued in this case. We said, well, look, if distributional coding is so great for artificial agents, and we know that dopamine, or we think we know that dopamine is supporting something like temporal difference learning, gee, I wonder whether the brain is using distributional coding, whether evolution has discovered that distributional coding is useful in exactly this way. And so that's what this project was about. So the first thing to do, of course, is to try to translate that question into testable predictions, like concrete hypotheses. So what are those? So in order to introduce you to a series of predictions and then empirical observations, I'm just going to keep coming back to the same graphic. I'm going to build it up right now. So in classical TD, we have a reward prediction error, which I'm just going to represent with this little node, and a value baseline, which is represented by this little node. And they talk to one another because they need to, in order to support a reward prediction error driven temporal difference learning. So the value is updated according to some scaled version of the reward prediction error delta. Everybody's, I presume, familiar with this problem. Okay, but if in the classical dopamine story, you have something like this. All of these, now think of these as neurons, they're all dopamine neurons, and they're all representing the reward prediction error signal. But importantly, they're all representing the same value, the same scalar value. That's why they're all the same color here. Now let's contrast that with distributional coding. Now, what we would expect is that all of the dopamine neurons would behave differently. Some of them would have signaling that indicates a sort of pessimistic view of the world, and all the way along a spectrum to neurons that are whose activity encodes a very optimistic view of the world. And the spectrum from pessimism to optimism comes out of a very simple tweak to the standard temporal difference learning algorithm. And that tweak is to add a parameter that scales positive reward prediction errors differently from negative reward prediction errors. And the relative magnitude of these parameters varies from channel to channel. In essence, if you have a scaling parameter that says that you're going to scale up positive reward prediction errors much more than negative reward prediction errors, you're going to get an optimistic value baseline, and you're going to get reward prediction errors that reflect that optimistic value baseline. Okay, I'm going to keep coming back to that idea, but that's the core mechanism in the flavor of distributional RL that we're going to be considering. Okay, so that's the hypothesis then at the computation level. What are some what are some testable predictions that we can take to the neuroscience lab? Well, there are actually a bunch, and we tested a bunch. So the first prediction is that you should see evidence for these asymmetries in reward prediction error coding. So different neurons should scale their positive versus negative RPEs differently. Some neurons, some dopamine neurons, should really have a steep ramp in the positive domain and a shallow ramp in the negative domain. And other neurons should have the opposite. They should be very steep in their firing curve, in like their tuning curve in the negative RPE domain, and very flat in their positive RPE domain. And there should be a whole continuum in between. That, for reasons that are hopefully clear from these equations, leads to a second prediction, which is that different dopamine neurons should be listening to different value baselines, and therefore, as you increase reward magnitude, each dopamine neuron should flip from a negative RPE to a positive RPE at a different reward magnitude. We're going to call this the zero crossing or reversal point for different dopamine neurons. And then finally, a core prediction of distributional TD is the simple idea that all of this diversity encoding that I've been describing implicitly encodes a value distribution. In distributional RL, this is true because these equations that I'm highlighting here are exactly the equations that are involved in something called expectile regression. So basically, the idea is this: if these two parameters were equal, right? If there was just, say, one alpha here, then you would be estimating the mean of the value distribution, which is in fact the thing that temporal difference learning usually predicts. But once you introduce an asymmetry here between these two, then you're marking out a different expectile of the distribution. The mean is the 50% expectile, but now there are also 25% expectiles, 75% expectiles. This is analogous to quantiles. Many of you will be familiar with quantiles. So when you take a bunch of expectiles and put them together, you're implicitly marking out a distribution. So these are the kinds of consequences of this algorithmic setup that we're now going to probe one by one in the neuroscience data. Okay, so now let's start talking about neuroscience data. So the first prediction that I articulated is that different dopamine neurons should have different tuning curves. Some should really ramp up their responses to positive RPEs versus negative, and some neurons should have the opposite kind of bendiness in their tuning curve, and there should be a whole continuum. So to look at this, we borrowed data from Naochia's lab. And the task here was super simple. It was just a mouse is listening to, waiting for a tone, and the tone tells it that it's about to get a juice reward, but it doesn't tell it how big the juice reward is going to be. And then the juice reward is randomly selected from a set of 7 magnitudes. And in the average dopamine data that now had reported before, you see very classical RPE signals. So if you look in the usual window, a larger reward leads to a larger discharge. The smallest rewards actually lead to dips corresponding to negative RPEs and a continuum in between. But we're going to look for diversity in the population of dopamine neurons. And what we're going to look for again is this bendiness of the dopamine neurons response curves. And so now to show you the first actual empirical result from the neuroscience study, long story short, we do see this kind of diversity across dopamine neurons. So this is a neuron that has a much steeper tuning curve in the positive domain than the negative domain for RPEs. And there are other neurons that bend in the other direction. It may look like we have very little leverage for the regression in the negative domain here, but each of these little data points, there are actually a lot of observations for each of them. So these fits are actually pretty solid. And in the plot on the right, what you're seeing basically is a summary over all the neurons for which we had data showing that this bendiness, the degree of bendiness and the direction of bendiness really tiles a space uniformly. So it looks like dopamine neurons really do scale their negative and positive reward prediction errors differently, and the relative scaling is kind of reproducibly diverse across the population. That's hypothesis and result number 1. Now, the second thing that distributional TD predicts is that different dopamine neurons are going to be listening to different value baselines, and therefore, as you increase reward magnitude, different dopamine neurons are going to flip from negative to positive signaling, negative to positive RPE signaling at different reward magnitudes. So in Nao's task, in a standard TD setting, as you increase the amount of reward from a little bit of juice to a lot of juice, all dopamine neurons should flip from signaling a negative RPE to a positive RPE at about the same juice magnitude, modulo a little measurement noise. In the distributional case, the story is totally different. Some neurons that are very pessimistic that are very optimistic should require a lot of juice before they start getting excited. Whereas other neurons at the other end of the spectrum that are very pessimistic will get all excited even if they get just a little bit of juice because they were expecting very little. We can do actual simulations of classical TD and distributional TD and look at exactly the pattern that we would expect from the distributional TD case. Again, here in the classical case, virtually all neurons, which are arrayed along these rows, are crossing that 0 point and flipping to a positive RPE at the same reward magnitude. In the distributional case, different neurons are flipping from negative to positive at different juice magnitudes. And in the empirical data, these are fits based on the actual dopamine data. We can see this kind of diversity. And it may look like we're just kind of making a big deal about Gaussian noise, but that's not the case. This variability is reproducible across halves of the data, and you can see it really clearly in individual neural responses. So these are two neurons in the same animal responding to the same juice reward, the same magnitude of juice reward, and this neuron is getting all excited and firing a positive RPE, and this one is definitely unimpressed by that amount of juice. Okay, in the interest of time, I'm going to skip over a bunch of slides. I can come back to them if we end up having time, but I want to get to the punchline, and so I'm just going to skip over this and we'll see how we do. So so far we've talked about the tuning curves for dopamine neurons and their bendiness, and we've talked about the zero crossing or reversal points for different dopamine neurons and the diversity there. Now, distributional TD makes a particularly interesting prediction, which is that these two things should be linked. So neurons that really scale up their RPEs in the positive domain should end up producing value baselines that are optimistic. Essentially, what you're doing if you really scale up your positive RPEs is it's a little bit like putting a large learning rate on your in the positive domain, which is essentially going to drag your value baseline in the positive direction. It's going to make you optimistic. If you really ramp up your negative RPEs, you're going to drag down your value baseline. So there should be a relationship between the bendiness that we see here and the point at which dopamine neurons flip from firing a negative to positive RPE signal. So we're going to go back to now's data from this same task and test that hypothesis. So again, we're looking for a correlation between bendiness and zero crossing or reversal point. We have the data for both of those. We've already measured the bendiness for each dopamine neuron, and we've also measured where each dopamine neuron crosses the 0 point. So now we're just going to look for a correlation across neurons between these two measures, and we end up seeing a very impressive positive correlation between those two quantities. So on the y-axis is the amount of juice at which the neuron flipped to firing a positive RPE. And on the x-axis is a measure of that bendiness in the tuning curve. And you can see a very striking positive correlation. Okay, so now kind of to the punchline of it all, why bother playing with these tuning curves? Why bother moving these value baselines and reversal points around? Well, the reason for doing that is that what you end up with is a distributional code. Again, what you're basically doing by bending these tuning curves and moving around these value baselines is creating an expectile code for the value distribution. The bendiness for each neuron essentially is identifies which quantile or which expectile is involved. So for the purple curve here, the line where alpha plus and alpha minus would be equal, basically you'd end up with a value baseline, which is the mean of that distribution. But for neurons that bend the RPE tuning curve in different directions, the bendiness of those particular neurons' tuning curves are going to mark out different quantiles, different expectiles of the distribution. Now, the particular value at that expectile is represented by the reversal point of that dopamine neuron. If we're talking about the expectile which marks the mean, then the point at which that particular neuron crosses from negative to positive RPE signaling is the mean of the distribution. So you have to take into account both the bendiness and the zero crossing of the neurons in order to get to this distributional code. Okay, and we have both of those again for our empirical data, right? We have the reversal points and we have the bendinesses. So the prediction then is that this scatter plot is implicitly encoding a value distribution. The value on the x-axis and the value on the y-axis, if you take them together and you look at all of the neurons and where they sit in this space, that is the signature of a value distribution under an expectile code. So one way of testing empirically whether the brain is supporting that kind of distributional code is to say, can we decode the true value distribution from this scatter plot? So we know what the actual value distribution is because we know the juice volumes that Now was providing to his mice. And that's represented in these plots by this, this gray, this multimodal gray plot in the background. That's just a smoothed version of the actual value distribution. And then we can do this decoding analysis on artificial agents. We can build a standard temporal difference learning agent. We can look at what its dopamine neurons are doing, and then we can pretend those are marking out the expectiles of a distribution, and then we can use MATLAB to say, well, what distribution has the maximum likelihood fit with those quantities if we pretend that they're expectiles? And we get a very bad fit to the actual value distribution in the classical TD case. But if we have a distributional TD agent, and we treat its dopamine neurons as if they're representing that code, then in fact, modulo a little noise across simulations, which has to do with the sensitivity to the initial seed, we actually can back out something that looks very much like the real value distribution. So we can go from the bendiness of the neurons and the point at which they cross the zero line, their reversal point, and we can then use kind of inverse logic to get back to the value distribution that fits with those quantities. So the question is, what happens if we apply that strategy to the actual dopamine data? What happens if we say, all right, we know how bendy the tuning curve is for each dopamine neuron, and we know where it crosses the zero line as we increase reward magnitude. Now let's pretend that the bendiness tells us what expectile we're talking about, and the zero crossing tells us what quantity is estimated for that expectile. And now let's use MATLAB to identify a distribution that's the best fit with that set of data points. And what we get from the experimental data is this. So just looking at the dopamine neurons, not applying any privileged information about what rewards the animal was experiencing, we can infer something that looks very much like the distribution of rewards that was involved in Now's experiment. Okay, so I'm going to draw it to a close. I do have a minute, not really enough to go back to those results that I told you I was going to skip over, but I'll just tell you what they're about, just in case people want to talk about them, or you'll at least know they're there in our paper if you want to learn more about them. They have to do with reward probability rather than with reward magnitude, which is what we focused on throughout my presentation. And suffice it to say that dopamine neurons range from pessimistic to optimistic in the reward probability domain, just like they do in the reward magnitude domain. And importantly, although everything I've talked about focused on dopamine neurons and therefore the reward prediction error signal, sorry, wrong way. The theory, of course, accords an important role also to signals that represent value baselines. We don't know where those live in the brain, but there's good evidence that one set of neurons that seems to encode value baselines is also in the midbrain, in the ventral tegmental area, and those neurons are GABAergic neurons. And it turns out that when we look at those GABAergic neurons, they also seem to span a pessimistic to optimistic spectrum. And this is something that we observed in the probability domain. So apologies for flipping past all these data slides, but I just want to give you a flavor for what was in them, just because I had a couple minutes to talk about that. Okay, so let me just close by coming back to the top level. So again, with apologies, this has really been a neuroscience talk, and it's just an example of how we can go from AI to neuroscience. So maybe I can close by just addressing the question, well, great, that's cool, Matt. You went from AI to neuroscience, but you said before that by doing that, we would be able to advance our interest in getting from neuroscience back to AI. So how has your work helped in this regard? And I guess the cowardly thing to say is time will tell. But let me give you just one quick example of how having done this work that I just described, we might be able to go full circle. And this actually has something to do with robotics. So everything I've talked about so far is based on a version of distributional TD learning, which is risk neutral. In other words, it doesn't weight negative outcomes any differently from positive outcomes. It's just like standard TD learning. It just cares about the mean of the distribution in the end. But if you are representing the full value distribution, then, unlike in the standard TD case, you have the opportunity to adopt risk-sensitive policies. So if I say, oh, gee, I want to be really careful right now because I don't want to risk a bad outcome, having the value distribution actually gives you the information you need to do that. And by the way, this could be a really helpful thing in robotics, as a couple of studies have already pointed out, because you don't want to break your robot. So if you're going from sim to real, for example, you might want to estimate the value distribution in simulation and then adopt a very risk-averse strategy when you try things out on a real robot. So, so how does this neuroscience research help us with that? Well, we seem to have identified that the brain is using something like distributional TD. Now we can do further neuroscience research and ask, how is the brain regulating its risk sensitivity based on those distributional representations? So just an idea for future research. Anyway, okay, so I just want to stop by thanking, again, my collaborators on this who did most of the hard work, Jane, Zeb, Will, and our amazing collaborator, Now. And thank you.
So thank you very much, Matt. I think now the audience is trying to digest all the new things that you're saying. That for me is actually awesome. I really like the distributional TD approach that you did present. So, and for that, we have the discussion. I know that it will be complicated to ask Matt questions from neuroscience, but you don't have to ask questions from neuroscience. It's better that you actually talk about your field and try to make a nice discussion. And so let me check. So actually, I have to say that could be questions for Matt, also questions from Mehdi. Mehdi, are you there?
Yes, and actually I have a question for Matt. Sorry.
Oh, okay, so you can start if you want.
Thank you very much. Great talk, Matt, as usual. Yeah, so there is this debate whether dopamine neurons might asymmetrically code the positive and negative, and I think so. A lot of people argue that they are doing little with negative, but I think this distributional reinforcement learning framework still stands even if you just shift the thing. So I'm wondering whether you have quantified this, and as a corollary, I think the idea that I tend to think from neuroscience that maybe the brain is treating reward and punishment with different subsystems seems very different than what we usually do in AI and robotics. And I think it can be very interesting, very inspiring for robotics. So I want to know what you would like to say about this.
Yeah, I mean, there are kind of two different issues there. One thing that's made it a little complicated to do the study that I presented is that there appears to be range restriction in the negative domain, right? Because you can't have a negative firing rate. And so, if you look at these average response curves, the response in the positive domain, is very large compared to what you see in the negative domain. And so we did a lot of ancillary analyses just to make sure that this kind of range restriction wasn't, invalidating our approach to the data or affording different explanations for the empirical findings. And one thing that we observed actually, and this is obviously just in Now's data, it could be different in different animals and different tasks, is that range restriction really isn't much of an issue. Like the brain seems to use that little gap between baseline firing rate and 0 pretty efficiently. And so that was just something that I thought was interesting, something I learned from just fishing around in the data. The other point you raised about different channels for appetitive and aversive outcomes, that's a completely different, as I know is a very different set of empirical phenomena. And one thing I want to mention is that the dopamine neurons that we focused on are just a subpopulation in VTA, as is becoming increasingly clear. And like these are the dopamine neurons that seem to do like the classical thing. But if you move posteriorly, even in VTA, now Uchida himself has shown that you get dopamine neurons that seem to be doing something very different. And they seem to be coding for, for aversive stimuli or for saliency. So I think we're just starting to like bring into focus all of the crazy diversity that exists in the dopamine system. So what we're talking about in the work that I described is diversity within one population, but it's only one population in a much more diverse set. So in a way, there's like hierarchical structure to this, I guess. Like the real name of the game now is to understand diversity at all of these levels, and hopefully we'll gain some insights for for the way that we're deploying RL in artificial intelligence settings, very much along the lines that that you described in terms of like understanding the diversity of replay.
Okay, actually I want to make a question from the YouTube, because we have a lot of people in YouTube, because some people they try to access and they couldn't, I don't know why, but we have a lot of people following from the YouTube, and I have a small question from directed to Mehdi, that is from Wei Wei Chen, that is asking whether, it's a small question, okay? So whether the backward replay that you saw is designed or just happened to be there by prioritized sweeping. I don't know if you understand the question.
Yeah. I mean, I want really to insist that it's an emerging property. So when I showed it, I mean, you can do it in different ways. If you have experience replay with model-free reinforcement learning, here you can design a reversal of your buffer and you produce backward replay, but of course it's designed. But in prioritized sweeping, it's really an emerging property. The fact that you're experiencing corridors and you have reward. So if you propagate to neighbors, the only neighbors you have are the preceding states. So this leads to backward sequences. And of course, this predicts that if you are in an open environment, that's what we are studying now, you should not observe to the same extent some backward replays.
Actually, sorry,
yes,
I'm
sorry. You can interrupt.
Can I ask a question?
Yes.
Yeah, so I have a question for Mehdi. So forward and backward replay. I don't know whether you happen to see this, but like quite a long time ago, a colleague and I published a paper on planning as inference, and we used this graphical model to and it's very much like what you described. You have forward propagation, you have backward propagation within this graphical model. But it was all based on full bore Bayesian inference, and it seemed to me like something like a sampling-based procedure would be much more biologically plausible. But the problem is that you're doing you're doing particle smoothing, basically. And so you have particles going in the forward direction, particles going in the backward direction. And in large state spaces, it's very unlikely that the particles are going to collide. So you can have particles going forward and particles going backwards, and they never touch one another. And so you don't get any progress in learning. And so my question for you is, in large state spaces, one trick that the brain might be using is having some kind of heuristic guidance. So in other words, if I know that there's a reward over in that corner of the room, my forward search isn't going to just be blind and random. It's gonna, like, I'm gonna use my understanding of like the metric properties of space, and I'm gonna send my forward rolls in that direction. So I'm thinking here of sort of the kinds of spatial representations that Tim Behrens has been talking about, which really give you a kind of manifold representation for space. But you can imagine this in non-spatial settings too. So the basic question is, do you think that there are representations that guide the direction of forward search to kind of point it in the direction of distal goals?
So I think so, and I think there are different ways of doing it. Actually, it's interesting because in the paper by Marcello Matar and Nathaniel Doe, there is this need term which somehow also attracts those forward replay towards particular regions of the environment. I think, so of course, what I've shown is very simple environment, so it works fine, and and you need to add heuristics if you want to generalize to more complex situation. I think an interesting question for me at that point, if you reach more complex situation, is that at the same time you need to focus a bit so that you don't search everywhere, but you should not reduce mental exploration. And so this trade-off, I think, is key. not only the trade-off during actual experience, but also during mental simulation.
Yeah, yeah, exactly. Agree. Thanks.
Yes. Any questions for a round? Because I have one question that try to put it in the robotics settings also. Like sometimes, and this is for both of you, Mary and Matt, we think about reinforcement learning that is kind of the solution for everything, right? But then it is not totally solving what we want to do. And you're proposing one approach to solve it is like with kind of distributed rewards, a distribution of the rewards that you are getting. But still, we will have to engineer this into the robotic system, right? And then in the end, the rewards are actually related to the task, right? So we are engineering this distribution related to the task. How we can go beyond that? How we can really move from rewards engineering to the task to something that allow us to some kind of other adaptation to other tasks?
Mehdi, I'm happy for you to answer first.
Yeah, so it's a crucial question that we also ask ourselves every day, I would say. And that's why we're trying, for example, when we apply to robotics, some of these models, we work always with very simple tasks, but we try to diversify, like navigation, human-robot interaction, and so on. I think for me, these models are a way to at least approximate discretized space and just do something. At least within a few trials, you can get to some performance, but maybe in the background, you have other parts of the brain that are observing, learning simply through Hebbian plasticity, and you can, with much maybe more general mechanisms that are not only implied in reinforcement learning, and that progressively then you can adapt to that. But at least I think if you simplify this, you discretize, you can still, in a diversity of tasks, get to something. I'm not trying to reach the optimal performance with these models alone. So that's how I see it.
Yeah, I agree with that. I think this is sorry, my screen just went to sleep. I'm gonna wake it up here. If I can remember my password. So yeah, I mean, I'm quite an aficionado of reinforcement learning. It kind of strikes me that there's a lot more discussion of deep learning than reinforcement learning in the AI community in general. But my philosophy is that RL is it. Like if we want agents that come up with solutions that we didn't think of, then we need RL. So like there's no substitute. But if you have that commitment, then you're on the hook for the reward function. That's the problem. Like we're stuck making up these reward functions, which are which are problematic. It's a problematic job to have. And actually, it's something I've been thinking about a lot. And I think my solution to this in the end is quite radical, which is value alignment. I think the only way forward in the long run for AI research, if it's going to be based on RL, is to build systems that just infer the human reward function and just try to make people happy. That's obviously not something we're ready to do like today, but the things that we can do in the meantime I think are the things that we're already doing. Aside from doing shaping rewards, we can train agents with auxiliary losses that give them rich representations, so we don't have to rely on end-to-end RL. Importantly, we can design curricula, kind of training our agents like babies. Obviously, more and more people are doing that, and it lends itself, by the way, to kind of hierarchical architectures like the ones that were discussed in the last round. But yeah, I think in the long run, we're going to have to get ourselves off the hook for these reward functions. It's because essentially what we're ending up having to do is knowledge engineering, right? Which is what killed classical AI research. We're trying to build. We're trying to, instead of trying to build knowledge in the way that classical AI did, we're trying to come up with reward functions that will build all that knowledge in. And it's just a losing proposition.
Yeah, it was difficult. I know that the question was difficult to answer somehow, but I wanted to see what is your opinion on that. And we have a question from Sal that is around. Please, can you ask the question? Yes.
Hi, so my name is Man Yen. I'm from ENSA. Thanks for the very interesting discussion and very broad questions that you just raised. I have very much more specific questions for Mehdi, actually. So the first one is about the results you showed about the different replay orders at the different maze locations. And in particular about the imaginary inference, that it showed more when the agent is at the reward location, more than at the central arm where things are confusing. And intuitively, I didn't get the idea why it would get more imagination when it's reaching the reward, instead of being at uncertain places where I would think that intuitively I would have the idea that it would try to imagine more and try to invent more things. And my second question is about the works that you've done with human intervention inside. So I'm very interested in that because I'm also trying to study how humans can help RL robots to learn, but more in an active manner where they ask questions to the humans and try to get different kinds of messages from the humans too. So could you detail a bit more what you've been doing on that field? Thank you.
Yeah, thank you very much for these questions. And I have to apologize because I realized the way I talked about imaginary replay was a bit misleading. So I'm not saying that it should be privileged at the reward location at the other. So the main idea was like with an internal model, you can generate, some novel things that you have not experienced. And this can happen anywhere. But in this particular task, because of the topology of the maze, when you're at the reward location, it turns out that the sequence of small paths that get concatenated are more likely to emerge. It's just specific to this particular topology. When you're in the central arm, you're already in the middle of one of those trajectories, so it's less likely. But I'm not saying that it's a general property of the system. And so thank you very much for pointing at this. Yeah, and for the human-robot interaction, so as you have seen, it's very simplistically, so like very simple, like the human is just giving a reward sometimes, and the robot. So I have to be clear that there's a reward to the robot just for doing the task. So when it completes, it put the right cubes in the right boxes, and sometimes we impose a particular order to do so. The robot gets a reward. So it can do the task alone, but a model-free system will learn it very slowly, so it can be helped by the human. And the model-based system helps the robot being less dependent on how the human is behaving. So it's very simple. Yeah, very simple way. I don't remember if you had a specific technical question about this part.
No, it was more about trying to know what kind of questions you were looking into in that.
But the question for us in that specific work is whether, if you have a robot that is controlled by a hybrid system that combines model-based, model-free, whether it makes the robot less perturbed by the variability of human behavior. When you have human-robot interaction, some humans are only punishing, some are only rewarding, some are do it a bit and then they stop, some are very probabilistic, they do it only sometimes, and we want to be robust to that. That's the goal in this work.
Okay, thanks.
Thank you, Sal. I will love to continue because but I think if my co-organizers, if I continue, they will kill me. So I think we have to move on because we have another block to go on. And actually, it's a pity that we cannot continue talking about this because it's my passion somehow, but we will move on. And I want to thank you from all the audience also and in the YouTube for Matthew and Mary to be here. You can also stay a little bit more for the two contributions that are happening just after I talk. And it will be 5 minutes and then we go for the next block. So everybody, please thank you a lot from the speakers, Mary and Matt, for their view on these subjects. Thank you very much. And I continue to the next one that will be Jansu and Guillermo. Please go to the stage.
Okay, can you hear me?
Yes, we can also see you.
Okay.
he's going to present a contribution, but I'm really sorry that it's too much sometimes about active inference. It might be my fault, but let's see what is this here. Thank you.
Okay, thank you, Paulo. My name is, hello everyone, and thank you for being here. My name is Guillermo, and together with Jansu, we will present deep active inference for robot perception and action. So the first part, I will present the first part, and Jansu will present the second one. As a brief introduction, according to neuroscience, we humans, we adapt our internal model or beliefs to infer the world and approximate reality. There is a mainstream in the scientific neuroscience community describing the inner brain as a Bayesian inference machine. So active inference, based on the free energy principle, suggests that perception, action, and learning all arise from the same thing, the minimization of surprise. That is the discrepancy between the current state and the desired or predicted one. We know that robotic systems must interact under uncertainty due to many different factors. For example, incomplete information of the world or partial information of the world, model discrepancies between the theoretical and the real robot, noisy sensors, and so on. So the question is, can we apply this neuroscience model to robots? Could we achieve the long-sought characteristics such as multisensory perception and action, uncertainty handling and adaptation, and scalability and generalization? We have two parts. On our first part, we adapted this model for ICOP, attendant-driven humanoid robot. We'll use the encoder values and the 3D reconstructed position using both cameras and binocular vision of the end effector as the inputs. And in this case, there's some noticeable discrepancies between the real robot and the forward or generative model. So this algorithm will will minimize the free energy bound, update the internal belief, and performing an action to approximate this belief to the observed reality. We have also added encoded a goal into the system so it can perform tracking and reaching tasks. So the article is available at Archive, and also the code is publicly available at GitHub. So there are two parts, two results from this part. The first one is adaptation. The robot has to reach a target, shown in blue, and it has a prediction of internal belief and the visual feedback. We can see if the visual position is modified, the algorithm generates an action that moves the new position towards the goal, reaching equilibrium. So if the visual input is forced to a different position, the robot will change its belief and adapt to this conflicting information. Second part, the second result is we tested how the system behaves in two real-world tasks, which is upper body reaching and head object tracking. The algorithm minimizes the prediction error to reach toward a target. You can see the upper body tries to reach the object, while the head and the eyes keep the object in the visual sight. So if you have any questions, I'm happy to talk about it during the poster sessions, and Jansu will now start her part.
Hello, everyone, from my side too. So in the second part of our work, we combine free energy optimization with deep learning to directly work with monocular camera images as sensory input, hence the name deep active inference. So the agent first learns the approximate generative model that maps the internal belief, which are joint angles in our case, to images. And this is implemented as a deep convolutional decoder. And while interacting, the agent's expected sensation predicted by the decoder is then compared to the real visual input. And this prediction error is used to update the internal belief and to generate actions. And all this is performed by means of optimizing the variational free energy bound. Next slide, please. So with deep active inference, first we can perform dynamical body estimation. So if the internally predicted image of the agent does not match the observed camera image, as you can see in these examples, then through free energy optimization, the internal belief will converge to the true arm position. So the agent can infer its true body state. Next slide, please. Secondly, we can also perform image-based goal-driven control. So the image of the desired arm position is set as a goal in the sensory space, as you can see in the faint arm poses here. And by minimizing the free energy bound, actions are generated so that the robot's arm moves to this desired goal position. And the actions here are generated from representation, so without an explicit policy. Next slide, please. So to conclude, we have provided a proof of concept that active inference can be applied to robotics, and we've shown an empirical study on a real humanoid robot, the iCub, on reaching and tracking tasks. As a next step, we have scaled up active inference to deal with higher dimensional inputs by incorporating learning with neural networks. And we can then perform image-based dynamical body estimation and goal-driven control. As future work, we want to explore applications to industrial tasks as well as multimodal systems, and also use active inference to model perception and action in humans, as well as to model body illusions. So thanks a lot for your attention, and we hope to see you in our poster session where we can answer your further questions.
Okay, thank you very much, Jansu. And the next speaker is Adrian. Sorry that I cannot make my question. We are really running out of time, so we will wait for the poster session. Yeah. So the next speaker will be Adrian Benatot, and the paper is called "So Artificial Agents Ask for Help in Human-Robot Collaborative Problem Solving." So please go to the stage.
Yes, I'm just going to share my screen.
Can you manage?
Yeah, just a second. Here it should be working. You see my screen?
Yes.
Okay, great. I'm just going to launch the video because I recorded myself. Hi everyone, I'm Adrien Bento and I'm going to present you the article "Should Artificial Agents Ask for Help in Human-Robot Collaborative Problem Solving" that we wrote with Vicky Charisi and Natalia Diaz-Rodriguez. This article is based on the previous article written by Vicky Charisi and her colleagues called "Child-Robot Collaborative Problem Solving and the Importance of Child Voluntary Interaction." It is a paper about the emergence and development of cognitive strategies for the transition from exploratory actions toward intentional problem solving in children. The paper presents an empirical study in a human-robot interaction setting which investigates children's problem solving from a developmental perspective. Their main hypothesis is that in a child-robot interaction problem-solving activity, children that voluntarily interact with a robot are more likely to show better improvements over time than children who interact in a turn-taking setting. To verify this hypothesis, they considered the game of the Tower of Hanoi and conduct a behavioral experiment to evaluate task performance and design two types of robot intervention, voluntary and turn-taking. During the voluntary, or also called on-demand scenario, the child can ask for help whenever it is needed, while in the turn-taking scenario, the robot will show the optimal action to the child every 2 turns. The results indicate that the children who participated in the voluntary interaction setting showed a better performance in the problem-solving activity during the evaluation session. The conclusions of this article that interest us are that in the child-robot interaction problem-solving activity, children that voluntarily interact with the robot are more likely to show better performance and improvements over time than children who interact in a turn-taking setting. Starting from this conclusion and considering that it would be valuable to transfer developmental discoveries to artificial intelligence, we propose to verify if the above-mentioned hypothesis is equally true for a basic reinforcement learning algorithm as for a child. We wanted to check whether receiving help from an expert when solving a simple close-ended task allows to accelerate or not the learning of this task, depending on whether the intervention is canonical or requested by the agent. In other terms, whether the learning is driven by the teacher or by the learner. As in their paper, we choose the game Towers of Hanoi that you can see here are the figures. It has 27 possible states with 1, 2, or 3 possible actions at each steps, and our agent is a simple Q-learning algorithm. We tried to reproduce as faithfully as possible the behavioral study design of the above-mentioned article, so we also have 2 conditions. In the first one, the learning agent solved the task in collaboration with the expert in a turn-taking scenario, and in the second one, the learning agent solves the task independently, having the option to ask for help to the expert whenever this is needed, which result in an on-demand intervention by the expert. In order to test the different variation of our setting, we work on two main parameters. The first one is the canonical intervention rate, namely the frequency of the expert's intervention during the canonical scenario, so helping every 2, 3, or 4 turns, and the ask for help parameters, which means how much the learning agent asks the expert to do the next movement, as a proxy to simulate the need for help during the on-demand scenario. The ask for help parameter was created because we were looking for a way to simulate what happens when a child asks for help. We choose to model it using a threshold, meaning that if the best policy value is lower than the ask for help parameter, the expert will play instead of the learning agent. Here are our results for the first scenario. So as it can be seen on the figure, the learning agent is directly more efficient when it is helped by the expert in a turn-taking scenario, whether it gets helps every 2, 3, or 4 turns, but it converges faster to the optimal solution when it is helped every 4 turns rather than every 2 turns. It shows that it's important for the agent to be able to explore on its own rather than having always the optimal solution. And here you can see the result for the second scenario. The asking for help agent is also quickly more effective than the regular one, the regular performance, as it is always asking for help during the first episodes, as it does not know yet what to do as the score of every policy is under the ask for help threshold. And after asking for help for many times during the first episodes, it starts solving the task by itself, resulting in a loss of efficiency that we can see here. We interpret it as the learning agent exploring and gaining confidence in movement, which, while are not perfect, still allows the task to progress towards its resolution through state exploration and trial. Compared to the not helped learning agent, the asking for help agent is much more efficient, but there is not a lot of variation between the canonical and the ask for help configuration, and this is probably due to the rather simple simulation of the ask for help trigger. The simulation of a child behavior is a complex task, and more emphasis is needed on accurate description of the child behavior, especially on how to simulate the ask for help. We conclude that getting help from an expert is beneficial to an agent's learning process, whether the learning is driven by the teacher or by the learner. As our point is to verify if hypotheses derived from an empirical study in a human-robot interaction are valid when translated from children to a reinforcement learning agent, the difficulty lies in the simulation of the child's behavior by an artificial agent. The addition of a mechanism like intrinsic motivation on the desire for the learning agent to solve the game by itself could increase the accuracy of this comparison. Our learning agent asks for help when it considers that a movement is not good enough to be played, whereas in reality the mechanism pushing the child to ask for help are much more complex. So this is one of the many possibilities that we plan to explore in the future. And it would also be valuable to increase the difficulty of the task, as this one has only 27 different states. So thanks a lot for your attention. I'll be available to answer to your questions during the poster session later this afternoon around 5:30. Thanks a lot and goodbye.
Yeah, thank you very much. Actually, thank you for reminding that at 5:30, various time, you will have able to talk with all the contributors in their own chats, okay? And thank you very much for all the speakers of this block. Thank you very much for everybody for being patient. Thank you very much for the people that go super fast to toilet and come back. And we have a next block that will be hosted by Mohsen that is around. We are in the BRAIN-PIL workshop. Today is 31st of May, it's Sunday. It's a nice Sunday for the families, but we are stuck here in the computer because we are interested in the workshop. But that is really good. And people are following in also on YouTube. I will share my screen to, or you share it, Mohsen. Okay, perfect. Thank you very much.
Great. I think we had very great presentation, talks, and discussions so far. And actually, I was talking with some of other friends or other colleagues to the other workshops, because at the same time, I'm in 2 workshops. So we really enjoying having a virtual workshop, virtual conference. First of all, we save time and we are not even making our environment more polluted. We are in a green conference now. And also we are giving opportunity to many people in the world to contribute to the workshop, because I know there are many labs, they are having financial problems, or even there are many people, they have even problem to get visa in order to come to Europe. So by having a virtual workshop, virtual conference, we can give opportunity to everyone to contribute to the science. So we are going to the last session. Last session means the last blocks for the talk. So I'm not sure if Fumiya is here.
Yes, I'm here. Can you
okay, so great. So we are going to have Dr. Fumiya Lida. He's actually the reader or professor at Cambridge University, Department of Engineering. And he's basically interested in bio-inspired robotics and neuroscience. And he's the head of bio-inspired robotic labs. And his research is basically focused on modeling of biological systems, self-organization, and component development. So I'm really looking forward to learn from you. So stage over to you.
Okay, thank you very much. Can you release the screen?
Let me make it, okay.
Okay. Good. Do you see my screen?
Yes, we can see your screen here very well.
Okay, brilliant. Yeah. Well, first of all, thank you for the organizers to organize this a very stimulating meeting today. I usually don't talk about this brain-related research in front of many people, so I'm a bit nervous today talking about this relatively new topic for me. So I'm running this lab called Bio-Inspired Robotics Lab, and we are usually building robots similar to inspired from nature. But obviously, if we mimic biological systems, we need to look into all aspects of animals and including brains. So we are great interest in the brain of biological systems and how we can mimic it in the engineering manner. But that's something I'm going to talk about today in this talk. So let me see what. Yeah. So this is the kind of robots we usually work on. So this is the robots we call brainless robots. So we usually build robots without brains. And so these robots, walk, runs, dance, or swim, all different kind of biological inspired behaviors. But the one common feature of these robots is that these robots are really useless. We didn't build robots for the purpose of doing something useful for humans, but we rather want to understand what's the natural principle of biological systems. And how can we replicate such principles in engineering manner. And the second feature we're showing here is that these robots are brainless in the sense that there's no brain, so no sensory feedback to the system. And there's no real control in the system. So robots are basically oscillating part of the body back and forth with fixed amplitude and fixed frequency. But still, these robots can actually show great variation of behaviors. And that is actually trying to demonstrate the importance of body. In other words, its embodiment embodied intelligence is kind of interesting aspects, what we are usually working on. So what do we mean by bio-inspired robots here? So what we can characterize bio-inspired robots as compared to conventional robots is that we are actually breaking a lot of rules of engineering methods in building robotic systems. First of all, we take advantage a lot of passive dynamics or under-actuated dynamics, so to speak. that the robots are often consist of passive joints. So not all the joints in the body are controllable all the time. And because of this, we can actually introduce a lot of degrees of freedom, many degrees of freedom, very redundant and often infinity, which is, usually engineers don't do. Because the many degrees of freedom makes everything so expensive, so uncontrollable, and so difficult to maintain in the world in the first place. So that's another aspect we're interested in our robots. But that's how natural systems, the biological bodies are built for. So that's something we're kind of using this principle. And then, the bodies are not always controllable because we have too many degrees of freedom and we have dynamic interactions. So not always, the control is not always possible. The reason why, biological systems do all sort of this, counterintuitive engineering approach is because, biological systems are built for energy efficiency rather than precision in control. We are always energy hungry entities, and we have to always save the energy to do whatever we need to do for survival. And finally, exploiting system environment interactions, also very important principle in nature, that the conventional robots usually take advantage of very static and very structured environment for the sake of better controllability and better prediction. But biological systems are living in a natural environment where we really have to take advantage of unstructured environment for their behavior purpose. So these are kind of really things that conventional engineers cannot really think about for building our system, especially when we want to build complex robots like a humanoid robot. But this is somehow the principles we found in nature, and so that's why we are kind of trying to break the rules of engineering and build the bio-inspired robots following these principles. So what does it mean from a brain research point of view? I think what we want to really trying to do in terms of brain research is we want to bring in some aspects of embodied viewpoint in the artificial intelligence, in a sense that our bodies, our brains, or our controller or AI systems are always sitting on top of a physical system. If the physical system is like computer, relatively simple and very well controlled, it's quite straightforward to really thinking about controlling brains. But in a body, if the body is really complicated, like our natural biological system, then we really have to think about how the brain should be developed on top of this body dynamics and morphology. So this is the kind of diagram we introduced in the papers in 2007 and 2014 about how the brain is related to the system environment interactions through the physical constraints or specifics of our body. So we have a mechanical system and sensory system, and always interfacing the brain to access an environment. And if you want to think about the brain activities in natural environment, we cannot really ignore how the body is built. So that's the perspective we're talking about. And usually people talk about interested in how brain controls the body, but from our point of view, we're actually rather interested in how brain is being controlled by the body, and that's something we want to bring. This is the kind of perspective I want to bring in the discussion in this workshop today. So what does it mean by brain being controlled by body? I think what's really salient in this context is the growth and learning process in the especially early stage of our life humans. So if you look at the developmental system, development of brain in the human beings, a lot of things are actually happening even before we're born. So our life starts, immediately after the fertilization, but from there on, the brain and body develops together in the mother's body. So here, there's a recent research on how their brain body develop together, shown in these papers, and it's really interesting that the basic structure of human body is already developed in the week 9 or 10, and by the time we're ready to born in week 30 or 40, we actually have almost complete setup of our body, including brain. So if you really want to understand how these things work in a bigger picture, we just need to think about what's actually going on in this very early stage of the developmental process, and we should probably thinking about how the brain and body develop each other in this early stage. So one of the things that important in this early stage of development is the developmental spinal cord, spinal reflexes. And the spinal reflexes are obviously very interesting for both biologists as well as roboticists. So I think this is a really interesting research topic that can overarch these two disciplines. So what we mean by spinal reflexes is these activities, motor activities mediated by our neurons in the spinal cord. So as we all know, most of our muscle activities are triggered by neurons in our backbone, and the brain has access to these muscles only through the spinal cord. So I think it's very interesting to really look at in detail how the muscles and the spinal cord are related to or connected to each other. And we know a lot about the reflexes, and we have literally thousands of reflexes in our body, but we can actually do quite good systematic bottom-up research about how such a spinal reflexes can be built on top of each other. So in our research in the last 5-10 years, we have been looking at relatively low-level, simple reflexes such as a myotatic reflex. So this is kind of things that we usually see when we have a weight exerted on our muscles. So muscles automatically push it back when you have force. And this is actually the command given from the sensor signal from the muscles, and then the muscle activity comes from the spinal cord without the involvement of the brains. But if you have too much force acting on one muscles tend to give up, go against the force exerted. So this is called a reverse myotatic reflex. So that actually protect the muscles to be broken from too much force exerted on the muscles. And also we have looking at the coordination of two muscles. So if every our skeletal system has lots of muscles connected, and some of them are conflicting to each other. So if you have two muscles connected to one joint, and two muscles should not pull to each other, because then it's going to destroy muscles. So we need a bit of coordination, which is called the reciprocal inhibition. And on top of that, withdrawal reflex is also very well known, that when we have touch fire or some acute pain, you automatically retract our hands or legs from that pain, and that is triggered by tactile sensors in the body, and that automatically inhibit a lot of other actions from anywhere else, but you just solve this problem right away. So these are kind of very basic behaviors that we all have. It's not only humans; a lot of other animals have this kind of reflexes. But we can actually do so many complicated behaviors out of this simple circuits. And if you look at things like stepping onto this needle, we need actually quite complicated coordination of different muscles and together, so that we avoid the stimulus, but still maintaining balance and so on and so forth. So all these things are done in spinal cord, and we want to understand these circuits before, getting higher brain involved in the planning of actions. And so that's the kind of question we're working on, this early stage development of babies. And apparently all these the reflexes, well, usually reflexes are considered as the hardwired innate circuits, but of course, nothing is innate in our body, and everything has to be self-organized in some way. And we're interested in how such a basic components of our behaviors can be developed in self-organized fashion in early stage of our development. So this is actually the very good collaboration project together with Mark Brumbaugh, neuroscience scientist in the United States, and he's in charge of all sort of very interesting and inspiring neuroscience activities over there. So what we are working on is so-called the muscle twitch hypothesis. So we all know that our muscles are randomly activated from time to time without our conscious control. But the hypothesis here is that such a muscle twitches could be playing a very important role understanding the development of spinal reflexes. So basically the question here is, so we have this behavior. If you have so many muscles in our body, and we have a switchboard of the brain, and the brain has to find out how this switchboard and muscles are related to each other, and to have this causal relationship in between, we can actually use the muscle twitches to see how they are connected to each other. So there's some evidences that the muscle twitches are actually happening in the random manner. So this is a sleeping rat with the EMG sensors and some motion tracking system. And Mark and his group did all sort of measurement how the muscle twitches actually happens in rats, and they seem to be quite random, but it's also very temporary, separated each other. So this might be a really good starting point to believe in this hypothesis of muscle twitches. But neuroscience cannot go too far away from this experiment. So we have somehow contributed to their the deeper understanding of a hypothesis about what if we can build artificial computational models of learning of in a simplistic manner. So what we are doing here is that we built a sensor motor system in simulation. So and this muscle motor system is connected to hypothetical spontaneous motor activity. So this is simulating muscle twitches, giving random signals to the motors regardless of any sensor signals in the system. But then this motor system obviously interact with the simulated physical musculoskeletal system in the environment, and that gives automatically the sensor signal, generate the sensory signals. And what we can do is that we can implement some simple learning rule, like Hebbian learning rules that can pick up the relationship between motor activities and sensor signal. Then we can actually make a causal relationship between motor signal and the sensor signal. And that's the kind of one easy way to apply a hypothesis of test the hypothesis of muscle twitches. So that's something we built in our system. So what we did is a very simple neural network. So we have motor neurons and sensor neurons, and they just fully connected to each other. And we just apply usual Hebbian learning rules. So when two neurons fire together, we wire together. What's important here is the motor system we use. So we use the simplified muscle models. Here we use a variant of a heel-type muscle model that it has the contractile elements as well as some passive element, because the passivity is very important in this the muscle twitches. So we try to mimic as much as possible that the muscles can behave both passively and actively. And on top of that, we include some proprioceptive sensors such as muscle spindles and the Golgi tendon organs connected to the muscles that measures the displacement of muscles as well as force exerted to the tendons. And then we just let it run together and see what correlation can be picked up by this learning system. So we are looking at the motor to sensor correlation here. But obviously, we can reverse this connection from sensor to motor afterwards, so that such a connection can be used for anything useful afterwards. So this is the overall framework we are working on. And let's see what actually happened. So what we did is everything in simulation so far. But we can already observe something really, really interesting. So even in a very simple system, like one joint and two muscle system. So in this simulation setup, we have a one joint connected to one limb. And this joint is connected by two motors and with the sensors, the spindle sensor and Golgi sensor connected to each other. And we also attach some tactile sensing elements so that we can simulate some the interaction with the environment. So what happens in this kind of simple setup is that we can introduce some muscle twitches artificially. So we just give stimulus to have an activation in one of the muscles here, the blue muscle here. And then, but this one obviously induce sensor signal on both muscles because these two muscles are connected to one joint. So we observe the changes in the length of sensors as well as force. Force is only acting on only one tendon because the other one has no influence of the motor activity here. And then if we have some environmental friction, then the both tactile sensor can actually react to it. And then if we twitch other muscles, and then we see the opposite reaction of it. And in this sense, we can actually start investigating how self-organization of a sensor motor causality can be picked up. So in this example, at the beginning, before learning, motors and sensors are all connected to each other. So there's a fully connected arrangement. But having heavier learning picked up some causality, in the end, we can actually observe really interesting all four types of reflexes we can observe. So myotatic reflex related to one sensor to motor, and the reciprocal inhibition, like how two muscles can relate to each other, can also happen by using this simple setup. And the interesting thing is the withdrawal reflex and reverse myotatic reflex can also happen if the muscle gives up some forces afterwards. The interesting thing is that this setup is a self-organization. So we can scale up this mechanism to very complex systems. And these are some examples that we extend the same, apply the same mechanism to two joint four muscle systems. So we have a copy of this mechanism to two joints, and we can actually see how muscle and sensors are correlated to each other in this fashion. And even if you have a two joint and eight muscle system, here we have more muscles acting on the system. We can actually, the system can automatically pick up the correlation automatically just by applying to this. So this is actually a very interesting starting point how we can investigate the more bio-inspired approaches, like this mechanism here. We are building simulator with more bio-inspired musculoskeletal setup. Here we have a two joints, hip and knee joints, connected through 6 muscles, and some of them are biarticular configuration, in the sense that muscles span over 2 joints. And this muscles is kind of interesting because it shows a lot of nonlinear effects depending on the angles of the two joints and so on. What we did is, at the beginning, we actually run some random muscle twitches. So activate one muscle after another in a stochastic manner, and then just running through it for many, many times. And then we can actually develop this kind of interesting sensor motor causality map. And this one is much more complicated than other previous examples, because the muscle configurations are a lot more complicated than others. So if you look at, for example, rectus femoris, this the biarticular muscle has influence to most of the all other muscles in various manners. So you can actually see the correlation between rectus femoris to other sensor signals are quite complicated. But this kind of thing can be automatically picked up because everything is self-organized by Hebbian learning. So what can we do with it? So in the second half of this video, the system is tested in the reverse manner. So whether this connection can be used for anything. So what we are doing here is in the jumping behavior. So if you drop this system from the air and put it on the ground and giving some force acting on the muscles, and then the muscle reacts to this ground reaction force in a very coordinated manner. And this is kind of interesting. If you look at the very slow motion of this, at the beginning of touchdown, you actually see some of the muscles are activated at the same time because they have a reaction to the force on the sensors. And then the second half of stance phase, when it's taking off, the other side of the muscles are activated. And then all this, the dumping reaction can also happen while it's in the air. So this is actually quite interesting, that a relatively complex coordination of the reflex, the muscle activities can be generated from this relatively simple the learning mechanism overall. So obviously, all these things are so primitive, oversimplified in many ways, and we just don't know how far we can go. But we're hoping that we can bring it up to much more complex scenario, like bipedal walking, or this is the example that's shown by Hartmut Geyer almost 10 years ago, about the walking of bipedal walking can be achieved purely spinal reflexes. So if we can develop a good circuit of spinal reflexes, we can do quite complex behaviors for complex systems as well. So of course, we're talking about really low-level control of the body, and we still don't know how this has anything to do with embodied cognition in the future. But here we have some hints from Andy Clark's Being There book, talking about how passive dynamics and non-causal spread of interactions can spread over our structure of a perception and learning of the system. So we want to really look at how this low-level passive dynamics can be related to a higher information processing through sensor motor coordination and so on. So we are actually trying to build really more robots in a complex fashion. So one of the research we're doing is the building of a robotic hand that is a place where we can implement a lot of sensor motors and motor components in non-trivial manners. And here we need a lot of variation of behaviors playing role, especially for the dealing with complex tasks that we do with our hands. So, our efforts at the moment is how can we bring in such a self-organizing processes we did in simulation can be bring it to the real world. So we're trying to build the robots in a bio-inspired manner. So here is the example of 2.5 fingers replicated in robotic systems. So with 3D printed bones and elastic soft components covering over different joints. So these are kind of almost one-to-one replica of a musculoskeletal system of our hands. But the real challenge here is, even for 2.5 fingers of our hand, we need almost 14 motors. So that's equivalent numbers of muscles we have in our hand. So if we have, control of 14 motors at the same time, it's a really significant task for robotic engineers. So here we really need a good self-organization principle so that robot can pick up its own behaviors through interaction with the environment. We also take advantage of more advanced 3D printing processes that we can mimic complex behaviors, interactions like, this thumb joint interacting with piano. The real next question is how we can put sensors in such systems. This is probably not much relevance to the interest of this community, but this is really a challenging problem. I think the next speaker is going to really talk about this problem, but how we can implement tactile sensors or sensors in soft structure is a real challenge we are facing at the moment. So that's something we need to solve if we want to get more bio-inspired brain to work in our bio-inspired robots. So I think, so time is almost up. So I think I'm going to summarize my talk here. I just want to point out there's so many open questions, even in the very, very simple behaviors like spinal reflexes. But we have some interesting insight from biology, or especially biomechanics, at how passive dynamics and the under-actuated dynamics play an important role in the behaviors of the system, but also these behaviors can be important for the learning and the self-organization of a brain signals. And finally, we're kind of wondering, what's the implications of our research so far, because all this spinal reflexes learning scheme is assuming that robots are sleeping. So as soon as robots moving in active manner, this mechanism of self-organization doesn't work. And that's why we're assuming that the spinal development can work only in an environment like a mother's womb. But so that's kind of interesting question, whether robots might have to sleep in the future or not, just to develop its own sensor motor coordination. So we are actually building robots together with Yasuo Kuniyoshi of University of Tokyo about the fetus robots platform, so that we can study this kind of problems in details. Okay, so here's a publication if you're more interested. Most of the things that we talk about today was already published, so you can have a look at the details in there. And obviously, this is a lot of the result is this presentation is results of lots of collaboration with a number of collaborators in the past. And with this, I would like to stop my presentation. Thank you very much for your attention.
Thank you very much, Fumiya. It was very great talk and presentation. I really enjoyed. But only one thing, Professor Yasuo Kuniyoshi, because he was my PhD supervisor as well. We also developed a baby robot, which is called Nabi. I think maybe the Nabi was after the fetus robot, which we did the whole body manipulation and exploration. So thank you very much.
Okay,
I think there will be some interactive session and also some question from you at the end of the presentation of Ravinder.
Okay, yeah, thank you very much.
Thank you very much. The next interesting talk will be given by Professor Ravinder Dahiya. I think Ravinder is here.
Yes, I'm here.
Ravinder is here. Hello, Ravinda.
I'm here, Mohsen. Yes, I'll keep my video off because my internet is not great.
Okay, okay. So, Ravinda is. So, can you please share your screen? Then we can see if it works or not, right? Okay, so Professor Ravinda Dahiya is a full professor at the University of Glasgow, and he's a professor of electronic and nanoengineering. He is the leader of the bendable electronics and sensing technology, and he has the largest research group in Scotland. And his research basically is focused on high mobility material-based flexible electronics, electronic skin and wearable systems with the application in robotics. And he is also the president-elect of IEEE Sensor. So Ravinda, thank you very much. The stage over to you.
Thank you, Mohsen, and thank you to all organizers for inviting me to this interesting workshop. So today I will talk about neural transistors for computational electronic skin. And at the outset, I must say that it will be disappointing that I will not be presenting tactile sensors in soft robots. As previous speaker mentioned, there's a lot of literature that I will be mentioning, which you can refer to if you want to learn about how soft sensors can be integrated or embedded in various soft structures. So today's focus is primarily on how to get computational electronic skin. So to start with, I would like to highlight briefly what we do in Bendable Electronics and Sensing Technologies Group. Basically, if you look at this side, we try to understand the human sense of touch and use this knowledge to develop the electronic skin or large area skin for robots. And in the process, the technology that we got, we are finding several interesting applications. And one application is through wearables, connecting and to human body again and measuring vital health parameters. So in a sense, that closes the loop as far as technology is concerned. But coming back to the touch sensing, why do we need touch sensing? And this example, this small experiment will highlight the importance of touch sensing. If you try to put your hand on an ice block and for some time and then grasp the object nearby, you will see that very likely you will fail to grasp the object. Object slips out of hand, and there is nothing much you can do it. Because for momentarily the tactile sensing is not there because hands are numb, and as a result the control mechanism fails. So this highlights the importance of tactile sensing in humans, and then it also raises an important question: why are we developing robots and prosthetic limbs and several other machines which are without tactile sensing? I will not go through many examples today, but one slide to summarize various application areas. On the left-hand side, you will see this side are some of the areas which are pushing the research today. And these are some of the futuristic areas which we see as a pull factors for tactile skin research, whether that's minimal invasive surgery, telerobots, or future haptic interfaces, as you see here, or excuse me, or soft robots with the tactile sensors and ability to grasp and manipulate objects. So, and also brain controlled. So these are various areas where tactile sensing can be connected. Primarily over last 2 decades, a lot of work have been, tactile sensing has attracted significant interest, and a lot of works have been done. And key areas and advances, if you look at the state of the art, are in relation with the fast response sensors that allow robots to react quickly, the conformability of electronic skin or tactile sensors, because our body is curvy. Likewise, many robots we are developing, they are curvy. So then this demands a question: why are we using electronics which is flat? We should have conformable electronics. And that's where many solutions have come up. I'll give one example of each of these points before I move on to computational electronic skin, the scheme that we are currently developing. Then there have been a lot of works on multi-sensors, multiple sensors over large area, starting with the hand-based manipulation, taking it to whole body manipulation, etc. And after these sensors and conformability, the next thing that has attracted attention, and this is still getting a lot of traction these days, is energy autonomy. As number of sensors increase, the requirement for power also increases. And if a robot has to work autonomously, then new schemes are that the electronic skin, in fact, can become a source of energy. So energy autonomy, self-powering, low power operation through low power electronics, etc., is another area that is connected to electronic skin and gaining and attracting attention. Then the last point is the handling of large tactile data. We are no more talking about hand-based manipulation, but several areas where we have also talked about using large area contact from the whole body. And when you talk about whole body, unlike sensory modalities such as vision and audio, which are quite central, you have 2 eyes or 2 ears, skin is distributed. And skin is distributed with large number of sensors. Density of these sensors vary with the body part and the sensitivity. And there are large range of parameters that skin measures, for example, pressure, temperature, sleep, etc. So as number of sensors increase, the amount of data they generate increases, and it becomes very difficult to handle this data, particularly on a robotic platform which has limited communication bandwidth. So given the current technological bottlenecks in terms of communication, in terms of computation, etc., there is need to develop also new schemes to handle the data. In any case, if you look at the structure of human skin, you will find that skin has many type of receptors or sensors embedded in soft material, embedded at different depths, and they start computing the data right at the point of contact. And this is then processed at various levels before it reaches to higher perception levels. So in a sense, I'm trying to say is there's a scaling down of data at various levels, and brain gets much lower amount of data than the skin captures. So that way we have to also think about the electronic skin or tactile skin or synthetic skin as known by many names in literature. We have to consider this aspect also. How can we develop computational skin that handles the large data, that downsamples the data at various levels, and in that sense allows us to use the communication bandwidth, which is limited. It's not just one-way transfer of information. You have to consider that it is a two-way transfer of information from sensors towards brain and from brain towards sensors. That will make complete haptic cycle. So coming to the first part, before I move to, I would also like to refer to some of the background work. If you wish to go through the details of what I'm going to talk today, then here's a list of papers over the last 10 years published by my group. And recently in 2019 October, we also published a special issue in Proceedings of IEEE, which talks about flexible electronic skin from humanoids to humans. So some examples of skin in humanoids, some example of skin in humans through wearables, etc. As I mentioned in the first slide, applications where these technologies are making way to wearable system, allowing us to measure vital health parameters. So these are for you to refer, and some more examples are given in this slide, including the book which we published a long time ago. So coming back to the key areas and advances, I'll give one example of each of these. First is fast response to allow robots to quickly react quickly. So one example here is the POSFET tactile sensing chip, which we developed almost 10 years ago. POSFET stands for piezoelectric oxide semiconductor field effect transistor. Now, normally you will come across this MOSFET terms where M stands for metal. And in this case, what happened is we replaced the metal. This is the normal working of transistor. You apply gate voltage. That gate voltage leads to modulates the channel current. And in a sense, apply more voltage, more current will flow. That way you can say that the input is a voltage and output is also is a current, and that way you can have a device voltage to current conversion. But if you replace this material with the top side with a piezoelectric material, which is polarized in a particular way as shown here, then when you apply additional force, there's additional charge produced here because of charge neutrality that gets reflected into the channel. So in a sense, you can say that the external force can also control or also modulate the channel current. And this becomes then a touch sensor, because silicon devices or electronics in principle based on silicon is quite fast. So we got sensors which were quite fast as well. We tested them up to 5 kilohertz, which is quite high with respect to human sense of touch, which we cannot sense vibration more than 700 to 800 hertz. There are various studies that reflect that point. So in this sense, we developed the highly sensors, which are fast responding sensors. And then overall response when it comes to action and reaction complete cycle also depends on the transmission of this data, and then processing of the data, then from processing, sending signal to the actuators and how fast actuator acts, etc. So that also depends. So it has to, sensor has to work with the other parts also. So this was the 5x5 touch sensing array. There were various other variants we made, and this was published at various, as this advanced, it was published at various stages. So, and eventually the idea was to integrate on the fingertip of this humanoid robot that you see here, called iCub. And that also was an interesting point where we realized that the silicon-based electronics is quite interesting. It leads to fast response, but it is a bottleneck, and bottleneck is it's not conformable. The moment you try to bend it, it cracks because silicon is a brittle material. And that led to the interesting direction in my own research. We started working on, there was a good motivation for us to explore conformable electronics and soft electronic skin. So that brings me to the next part, conformability control surface. We developed various examples over years. So this is 3D printed hand, these two, where sensors are not at the outer surface. They are all embedded in the structure that you see. There's a graphene based skin, which is conforming, ultra flexible and transparent. And this was the large area skin implementation on iCurve using capacitive tactile sensing, capacitive tactile sensors and flexible printed circuit boards. So various range of technologies in terms of conformability. Flexible PCB approach is a solution that you can explore today, because the off-the-shelf electronics is integrated on flexible printed circuit boards. But bendability is limited. Then there are graphene-based skin approach, which is something we need to be scaled up to get to large area. But it is highly flexible also. So these are various solutions available. And then there are many other solutions related to, the skin, the nanowire based variants of skin, which are ultra flexible, such as the tattoo-like skin that you see here, or the large area implementation of skin using nanowires. Now, nanowires, as the name itself suggests, its structures are less than 100 nanometer, and they are, if you make electronics from those structures, it will be ultra flexible. And using this approach, we are printing nanowires. We are developing a new method where silicon-based electronics can be printed. Now, I mentioned a while ago that silicon being brittle is a challenge to make it flexible, and that challenge still remains, but at nanoscale, the brittleness, these are highly flexible devices. The bulk properties are not same as the properties that we see at nanoscale. So we are printing nanowires to get electronic skin, but this skin does not have vibration. This has, if you look at this, the top layer is nothing but a pressure sensitive layer, which is essentially if you change the resistor, if you press it, resistance between these two or capacitance between these 2 points will change, and as a result, the channel current, the current through this device, this channel will change, and hence you can say that transistor you are developing is modulating the channel current. So that way we are making it, we are printing it, and we are making it over large area. So this is a work in progress. Unlike flexible PCB based approach, which is skin, that skin is currently available. Printed approach is something that we see in next couple of years to make the next generation of skin. Then come to the next point, which is multiple sensors or large area. So there are several examples. I must say that I've picked up only few examples here. But if you go to literature, you will find implementation of electronic skin with multiple type of sensors by various leading groups in Asia, in Europe, as well as in America. The large area skin, as I mentioned earlier, number of parameters are to be measured, and they include the hardness of material, softness of material, temperature, hot or cold, the glossy surface or textured surface, etc. So there are various approaches here. The one example shown here is large area implementation of skin. Other hexoskin is shown here from TU Munich, from Gordon Cheng's group, where proximity sensors and temperature sensors, etc., have been implemented over large area. So the idea here is basically in all these implementation is that our skin is capable of detecting various parameters. So the robot should also be able to do that. The next example is related to energy autonomy, self-powering, and low power operation. So there are this energy autonomy has started to gain interest recently. Not much was, it did not attract that much attention a couple of years ago, because perhaps the focus was more on developing tactile sensors. And now that we have developed tactile sensors, we have started to integrate them on large area, and we have started to use them in various studies. So the next problem, the problem that arise related to energy, related to data, they are attracting attention. And one example here related to energy is from my group, Energy Autonomous Skin, where we integrated graphene-based capacitive sensing layer on solar cells. Now, solar cells, flexible version of solar cells is also available, although performance is not as good as the flat version, but that's a part of a development cycle. As technology improves, that will also, we will see better results there. So graphene has an advantage that it is transparent. And many other skin variants that were reported before this work, the skin was not transparent. For any solar cell to generate energy, the light must reach the solar cell. So in this case, by integrating graphene skin on top of the solar cell, we were able to get touch sensitive layer, as well as generating the touch sensitive layer on solar cell. Solar cell were able to generate enough energy to operate the skin. In fact, skin in this case, graphene being highly conductive, was the power consumption was only 20 nanowatt per centimeter square. So in a sense, we were generating more energy than was needed. And this research was further advanced. We added supercapacitors, flexible supercapacitor, which is equivalent to flexible battery, to store the charges for the time when there is no sunlight, and so to allow a continuous operation. So idea here was to show that because skin is large, present over large area, unlike other sensory modalities, which are present over small area. If you look at the area of eyes, that the skin would be much large area. And when it is large area is not a problem, as has been thought, as has been argued in many papers also, because large area is also an opportunity. If you have this kind of solution, then the amount of energy that you can generate would be significantly high. And that energy could then be used not only to operate the skin or the computing unit related to skin, but also to operate some of the actuators. So this brings me to the last point, which is handling large data. And in terms of large data, if you look at the example here, number of sensors, number of mechanoreceptors shown on this slide. On the palm area, roughly we calculate, if we calculate, then it is about 5,000 5,000 receptors that you will have in the palm area. Now imagine if you have to consider sensors over the whole body, and if you want to imitate the sense of touch in humans, then you can realize how many mechanoreceptors or how many pressure sensors you will have. I've not even included here the receptors related to pain, related to temperature, etc. So the point I'm trying to make is number of sensors will multiply very quickly, and you have to find a new way, because technologically it becomes quite challenging to handle this data. If you look at our own skin, there are sensor receptors embedded at various levels in soft layer, and acquisition and processing starts right from this point itself. There are neuroscience studies which reflect, which indicate that the first spike of the neurons that are connected to these receptors, if you ensemble of neurons from the first spike itself, you can get the information such as amount of force, the direction of force, and the location, etc., which means that the processing starts right from the point of contact. And throughout these two channels that you see, throughout these two channels, there's a processing takes place at every stage. And by the time the data reaches brain, it's much smaller amount of data. It's already processed. So brain then is taking a higher level decisions, whereas the processing, etc., previous processing takes place, takes the decision much earlier. For example, the direction of force at the contact point itself would be a decision that would be connected to slip. So this means that we need to develop skin that can handle, process the data at various stages. So this cartoon just shows that the concept here. So you got various type of sensors. Consider these sensors to be the skin, and then you have, these are connected. In this case, multiple wires are shown connected to the computing unit. Of course, this is not possible in reality. You cannot have that many wires in our skin. Each receptor has that kind of connection, and then at some point this becomes a two channel. That is not possible. We still have to find some way for connecting a large number of sensors. Normally you come across this row column fashion, but there could be other arrangements also that need to be investigated. Perhaps distributed computing would be an answer to that. So in a sense, you have the processing at various stages, and by the time it reaches brain, you have much lower amount of data. Now, so what happens is, what you do conventionally is shown here in figure number A, above the dotted line. So basically you got the sensor signals. So analog input is coming in, sensor detects that. Using A to D converter, you can convert the sensor data into analog data, and then there's a computation takes place based on that data at some point. So you are transmitting all this data to the computation unit. There's no distributed processing taking place here. And what you get is a digital data, process data, which can be transmitted, or it can be used for actuators, etc. It can be used in whatever way you want. So whatever is the intended purpose, basically. So to handle this, this large amount of data directly going to computation, at this point, you have to think about the communication bandwidth, which is a problem. So to overcome that problem, one way is to use neuromorphic sensors. So what happens in this case? You have the analog, the input coming in, neuromorphic sensor, which will be using, instead of A to D conversion like this one, 0-1 format, you make spikes. And that's using a spiking neural network. There are so many variants here available. Normally what happens is you are getting all the data. So data is not reduced here. Still you get, but because of spiking network, you are able to use effectively in a much efficient way the communication bandwidth. So spiking neural network will then process the data, so extract some information, and then this information is sent to decision. So sent to for action, whatever action is based on tactile feedback. So the neuromorphic approach has been able to, the tactile skin has started to attract that attention, but we are still getting a lot of data. We are not scaling down data. We are not doing the distributed processing because distributed processing would require hardware. And that's where my next point comes in. Can we realize that kind of hardware? So neural transistor that I mentioned as the title of my my presentation today is a basic building block that I want to present here, which can be used to develop a computational scheme. A computational scheme is not just computing at single point, it's kind of distributed throughout the skin, like actual skin. So if you look at the figure A here, which is how a synapse looks like, and where there are many inputs, multiple input coming to a synapse. There's a soma here where the action, whatever decision or computation takes place. And based on that, there's a decision. Based on that, there's an output, and multiple output go to the next level. So this is presynaptic neuron, that's postsynaptic neuron, and that way the neural system is working. Now, one important point I want to make here is neural system is working on analog data, whereas most of the approach today in neuromorphic that we have, they are based on digital versions. We have not really gone beyond the perceptron model that was developed almost 4 or 5 decades ago. So in that sense, neuromorphic approach itself requires new directions. So what we have done is, if you look at synaptic junction, this is how various inputs are coming in. There's a summation takes place, and that summation here with some activation function gives you the output. This is standard any neural network would do. How can we implement such things in hardware so that we can do the transmission as well as computing at various levels? And one example is a multi-gate transistor based on nanowires. So this is the nanowire on which, this is the model shown here. There's a nanowire on which we have 5 gates. And under 5 gates, each gate is connected through a floating gate. So you have basically a modified version of transistor. One gate, you have 5 gates. This is a symbol shown here with 4 gates, but we implemented 5 gates. And there is a floating gate. And I'll explain in the next slide how these computing, how they are, the summation is taking place. And the figure E here shows the fabricated device. So we have source, drain, various 4 gates shown here. There's a silicon nanowire used. And this is the output of a transistor. Let me take you to the next slide because I have explained the output there in more detail. So that's the version we got, 5 gates, as you see here. Now, what happens as these gates can be connected to, either the previous neuron, or it could be connected to various type of sensors. So assume G1 is connected to sensors, pressure sensor 1, G2 is connected to temperature sensor 1, G3 is connected to another pressure sensor. That way you can have various inputs, and these inputs, based on these inputs, like I mentioned in one of the slides in the beginning, phosphate device, that you apply force on the transistor, and with force you are able to modulate the channel current. The configuration remains same. So you are essentially, instead of 1 input, force input, you got 5 inputs here. And based on the combination, either 1, 2, 3, or all of them working together, you can operate this transistor, you can modulate the channel current. So when you are modulating the channel current with multiple inputs, you could say that this device is doing what summation is done here at this point. So that means one transistor can do many things, and that way you can handle the data more effectively in the hardware itself. You don't have to develop neuromorphic. Now, I'm not saying that neuromorphic approaches based on software are bad. It's just that they are not as efficient as hardware implementation would be. So this is a step towards hardware implementation. How does it do? If you look at this characteristic, so when one gate is on, so transistor, the output is not very high, so transistor remains off. So you can set the threshold, like synaptic junction. At that point there's a threshold. Above the threshold, if summation of inputs is above threshold, then there is the data goes to the next level. Likewise, you can set the threshold for the transistor also. If gate 1 is not giving you enough output, then the transistor will be off. And that is interesting from the power perspective, because you are not using transistor all the time. It will be on only when there is enough input available. So that is another aspect. So this is when 2 gates were on, 2 gate on, you have red color here, 3 gate on, likewise. So as number of gate increases, you have more current through the transistor. So this is also the same thing. This is the drain current versus common mode gate to source voltage. So as you increase the voltage, you get these results. And this is simulation versus the actual result. So how do we do it here? So this is the floating gate. FG is a floating gate, which is essentially shown here. That's the cross section, which is floating gate here. So the floating gate voltage is a summation of the capacitor of each gate, because there's a floating gate and this is also metal, and between these two there's a dielectric. So essentially each gate is making a capacitor, and because we can change the dimension of the gates, as you see here, this width is decreasing, so dimension of these gates are different. So because dimensions are different, this capacitance is different. So that means the capacitance versus voltage divided by total capacitance of the floating gate plus the individual capacitance is what we get as the voltage at the floating gate. And if you take this as assume this as the weight, then essentially what we are getting is floating gate voltage is summation of all input gate voltages. And this is what we are doing here, similar to this synaptic junction. So in a sense, this building block, if I use this building block and scale it up, then I should be able to get a neural-like function. A skin, because it is made of nanowire, it will be flexible. So I'm not losing the flexibility function here. I can still use the same previous variants where inputs are the sensor inputs, but now it has sensors plus flexibility plus the computing part as well. So this device is interesting that you have the computation in the transistor itself. You are not sending all data in the hardware itself. If you have to take a summation, you will see that circuit complexity would be quite high. You will need several transistors just to get the summation of various inputs. In this case, you are doing it with one transistor. Of course, there can be other configurations also to improve this. Now, to show you further how we could take it to the next level in terms of neuromorphic computing, and I'm talking about the hardware implementation of neuromorphic computing, we have we demonstrated through simulation using neural nanowire effect or neural transistor based approach. If you take this as an example, you have X in input, V input here, and we use capacitors which are equal. So assuming these capacitors to be the multiple gates that I was mentioning in previous slide, so these are corresponding to these gates. And this is the neural FET that we have. Using 2 neural FET, neural transistors, I have made an inverter here, and this inverter is then connected to another transistor inverter here to make it an activation function. So in essence, this slide is showing you how neural transistors can be connected together to make a complete neuron. So you have a summation like synaptic equal weights here. We just for the sake of an example, we have used equal weights here. Then you have, if you're using neural FET, we also implemented activation function, and here comes the output. So if you look at the simulation results shown here, so this green color is so for one synapse we don't see anything, but as the number of synapse increases, number of these inputs increase, the response that you see here, input response is input is number increasing. So you have 2 synapses, the neuron starts to work at this point, at this voltage. This is the output voltage. When 3 synapses are on, this increases, this comes to the left hand side, and neuron starts to operate at much lower voltage with synapses, which indicates a step towards neuromorphic computing, that more inputs you have, the quicker the synaptic junction at the soma itself will it will trigger to the next level at much lower voltage depending on these inputs. This is another example where non-equal weights were considered, and this is the response for that. I suggest, if you, in the interest of time, I will not go through the detail of these circuits. You can have a look at this paper, which is also mentioned in the background work that I cited earlier. So to further take it towards the programmable synapse simulation, we also simulated the EEPROM like the neural fat synapse, and these are the outputs shown here. With that, you can get the SOMA is made from neural nanowire fat. Sorry about that. So you can get excitatory synapse as well as inhibitory synapse using this arrangement. This is one implementation. We have not implemented this in hardware so far. Hardware implementation is only related to neural transistor, but this is just to show that the whole electronic implementation is the next step once modeling part is done. Here is another example how we can implement. In case of neurons, the plasticity and short-term memory, long-term memory, sensor memory, they are all very relevant. So these two examples, the one in this slide and this slide, they are indicating how we could implement using neural fat, neural transistor, how can we also bring in plasticity and various memory through circuit arrays, through circuit implementation. So again, so this was a step towards synapse with plasticity using neural fat approach. I suggest that these details are given in the paper. I suggest that you can go through that paper if you want to know more about how computation is taking place. One example is shown here in the video. So this video, this video shows the implementation through simulation only. So what happens is we have got the model using neural fat, neural transistor. We have got a model of the neuromorphic system, and the input to that system is through the skin, which is basically a 6x6 capacitive array developed using ITO. Now, readout of this goes to the system model that we have developed using our neural transistors, and out of that output of that system, then touch, where the touch is, what direction the contact was made, and gesture polarity. So in a sense, something I mentioned earlier about neuroscience studies talking about the first ensemble, this first spike of ensemble of neuron response tells you multiple information. That way, using this model complete thing that I explained, we are able to also get multiple information, which means what you get at the input can be processed at in situ, it can be processed, and much lower data will be then transferred to next level. So this video just shows that. I'll play this video. If you want to have look at this video later on, that's the YouTube link given here. This video is also present there. So you got the 6x6 array, and that's the neural implementation. So that's the contact point, one contact here, and it goes through the models as you see here. So this is so that's the 3x3 cell we got. What, it stopped basically. Okay, let me start again. So that's level 2 network here. So this is detection of touch and decoding of direction. So if the slide, this is the slide, then you can see here the touch as well as the direction was shown here. This is the direction in this way. So the input is taken from the skin, and it is processed by the model, which is based on neural transistor that I was showing you earlier. So based on this approach, we are now working on the printable tactile skin, which is a neuromorphic print skin. I mentioned about printable tactile skin in the previous slide when I I gave example of conformable skin, but we have in that, sorry, we have added in that another layer, which is a neural processing layer. And that processing layer is based on the circuits that I just mentioned. Some of these circuits we are now realizing for electronics in backplane. And the idea is that these sensors on top, when you press them, you should be able to get not through simulation as I presented in previous video, but directly in the hardware, you should be able to get an output of the motors, the locomotion force and directional force. So that is, in my view, will be a significant advance and will be a breakthrough in the field of electronic skin. And what next? We would like to then use the skin in such a way that as shown here. So the one example is shown here. That's the skin. You got tactile image. So that image is goes to the input layer of the network, which is this is the computational skin directly here. And there's a neural layer underneath which processes the information. So there's a processing like human skin. You have a distributed processing, and there's a coding that can take place. This can be quite different coding depending on the overall architecture, and based on that you have the feedback here. So you don't have to send all the information. Some of these action can take place based on the local processing also. So in terms of, there are 4 more examples. I'll just use 2 examples and then I'll close this presentation. Touch sensing plus computation is something that we have just developed. So basically what happens is you have different type of sensors, and in human skin, both static and dynamic responds to both static and dynamic stimuli. So in that regard, we have developed skin which has a stack of capacitive and piezoelectric sensors. As you see here, this is the model shown here. So so this is the model shown here. There's a fingerprint on top. You have static sensor, dynamic sensor, and the signal goes to the microcontroller. And then from there, by programming, we are able to detect the response of static and dynamic sensors. Basically, piezoelectric sensor would respond to only dynamic conditions. So at the onset of a when an object is touched, or when you remove the touch, that's when the piezoelectric sensor would respond, and capacitive sensor would continue to respond all the time. These are analogous to the slow adapting and fast adapting receptors in human skin. Using that input and wavelet transform, etc., we made these this video that you see here. So this is the response from the capacitive sensor, which continues to respond, and piezoelectric sensor would respond only when there is a change. At this point, when change starts, then only you get the response from piezoelectric sensor. So that way, we also implemented some, in addition to in the hardware itself, we implemented some low level of processing. Other example where we are developing electronic skin, so the hand, robotic hand with sensors embedded in the hand itself. As you see here, all electronics and is embedded in the 3D printed structure. And the capacitive sensors, these sensors are designed in such a way that when you print the structure becomes itself a sensor. So we don't have to bring highly sophisticated skin here, and local computation can still take place by using local memory here. So, but this technique is limited to, you cannot think of high density of sensors. Number of sensors are limited. So depending on the type of application where robotic hand is involved, in some industry applications, you don't need human-like sensitivity, just a couple of sensors are fine. So, and robustness is needed in those applications. That's why all electronics, all embedded in the structure, can be helpful. These videos, again, the links are given here. These videos show the working of this type of hand. So that's it's embedded, so you touch it, you get the response here. All sensors are embedded in the 3D printed hand in this case. So, well, that brings me to the end of my presentation. I would like to acknowledge the support that I'm receiving in various ways from my funding agencies, EPSRC, which supports my fellowship on new print skin, European Union, Scottish Funding Council, Royal Society, and Royal Academy of Engineering. And I would like to say big thanks to my group members. Most of the work that I presented is several of them have been working on various parts related to electronic skin, and I'm thankful to them for that. And I also thank you very much. So there's a website, links, emails, etc. There's a TED talk about skin work that we have developed. All links are given here on the slide. Thank you very much.
Thank you very much, Ravinder. Very interesting. So we have to jump quickly to the next step. Is there any question? I would like Ravinder to stay here, and also I would like to invite Fomia as well.
Yes, I'm here. Yes.
Fomia, thank you very much. So is there any question here?
I have a question. I have a question, Mohsen. So because this question is for Professor Dahija, because I'm really impressed about the sensors that he is developing, but also because I work mostly in the AI part, and sometimes we see that everybody is developing sensors, but then we cannot use it. So what do you think that would be the next step so we can really actually start to be used as we can use cameras in the world of tactile systems?
Well, Pablo, is that correct? I noted Pablo is correct, right? Pablo was speaking.
Yes.
He's Pablo.
Yeah, so Pablo, the question is, yes, there are many types of sensors, and the bottleneck remains if you want to use it like camera. There is problem here is in camera, you have CMOS imagers. There's a distinct technology available. You just have RGB combination, and that you can process the information. So you got the limited in terms of sensory inputs, you got limited information. In case of tactile sensing, that's not the case. You have so many parameters that you need to measure. Based on with these parameters, there's an action taking place. So you have to measure slip, you have to measure force, you have to measure temperature, you have to at times measure the humidity also. So that's why the point you said that there are so many sensors, but you don't find a kind of effective solution. So it is difficult to have one sensor with all these responding to all these inputs. So one way to get this is to have multiple type of sensors, but then that will also increase the other problems that I was mentioning in terms of handling data, etc. For specific applications, you may have those limited sensor and it could still work. But I would find it difficult to say that there would be a camera-like or CMOS imager-like solution for electronic skin.
Thank you very much, Professor Dahija. Mohsen, we have a question in the chat, and maybe also, yes, please.
I think we have one question here.
Let me see.
I would like to ask a question.
So Oliver, you have a question, right?
Yes,
please.
I have a question. To Professor Dahija, I've seen you've been developing transistor gates. Have you been using also ASICs or FPGAs to process the data in real time, or only microcontrollers?
Well, we did not, as when it came to neuromorphic thing, we have not used any FPGA, etc. I mean, there are alternative techniques available with FPGA, and there are others also. But problem is when it comes to the complexity is much higher in those cases than a direct hardware implementation such as neural transistors. So this was the argument we also made in the paper that I was mentioning. And we have also mentioned there are various other solutions, including FPGA, which are alternative solutions at this point. So scaling it up with those techniques may be challenging, whereas neural fat, you can print over large area and you can make skin, which is kind of a distributed computing. That's the whole argument here.
Okay, thank you.
So any other question? So if there is no question, we're gonna have a
Yeah,
group
can I make a
photo
question,
here.
last question to Professor Lida, please?
Yeah.
Because there was no question. So you are in this type of soft robotics, and then you say that it was complicated to talk about the neuroscience and so forth. But I'm seeing also that this is split between the artificial intelligence, robotics, and then sensors somehow, right? That actually we also did this in these blocks. We split neuroscience, artificial intelligence, and then sensors somehow. And I think that is a problematic part. And my question will be like, how you see, how we can help in the AI community to develop better soft algorithms or algorithms for soft robotics somehow. We have to go for the sensor part for the body only, or we can get the data, or what do you think that would be the direction for that?
Well, I think one of the fundamental differences between biological systems and conventional robots is the number of degrees of freedom and numbers of components, active and sensing components. And as we go more and more with the advanced technology, like Professor Dahia's technologies, we have more sensors, more computing unit, more actuators, hopefully. And then I think the learning technique becomes more obvious that we definitely need some self-organizing solutions to get sensor motor coordination done, for example. And we just, so far, we didn't have enough sensor and motors. And I think that's one of the discrepancy between biological system and robots. And but the years to come in the future, I think it's more obvious that we have more sensors and more actuators and more learning to be necessary, and that's where I think we're going forward.
Okay, thank you very much, Fumiya. And also I want to, Mohsen, you can actually tell the people that we are going to make a group picture, the first.
So I have already told them, I think if it's possible to everyone, if you would like to be in a group picture, please turn on your camera.
Yeah, actually people are in their houses.
Or maybe, I don't know how is it going, but maybe Natalia, since you are the host, maybe you can activate everyone's, right?
Actually, we can see that Matt is still here. And also Juntani, that right now you are really late in Japan, huh?
I think Juntani is in the bed. Maybe.
I can or I should activate everyone. So whoever wants to be in the picture with the camera on should turn it on.
Yes, please activate your camera. I don't know if you need our like a permission here, or you can do that, right? I can see, yeah, you can do it.
But I don't know the way that Pablo did it was nice. I'm not sure how you should.
I can do it. So, okay, we don't force anybody to be in the screen. This is not mandatory, but I will do.
I can see Emre. Hi, Emre.
Where are you, Emre?
Istanbul.
Istanbul, okay.
Yeah, I'm in Istanbul. It was very nice workshop organization. Thanks.
Okay, so I will make a picture of several pictures. Thank you very much, everybody, to be here. Let me make, this is a technology to the state of the art of the technology. Good. And also another here. Okay. So thank you very much. All right. I think that's okay. It's not the same as a group picture in Paris under the Tour Eiffel, but whatever. So I think we have to close. I know we have the contributions. Sorry.
Actually, we have 2 contributions.
Yes.
But unfortunately, I have to say goodbye to all of you because I have in 2 minutes I have a talk in another workshop. So I hope you enjoyed the workshop. And yeah, I hope to see you soon, either in next ICRA or IROS. So I think Pablo and Natalia will take care about the rest of the workshop. So have a great time. So goodbye from my side.
Thank you very much, Mohsen. Okay, one second. that I will share the next. I think I have to eat.
Yeah,
This
I
is
think,
also recording
Pablo,
in
you
YouTube.
have to, because I will pause the recording. I think you should
Yes.
start recording.
Yes, that's good. So we are here. Okay.
So have a great time, everyone. Bye.
Thank you very much,
On my
Mohsen.
side.
Bye.
Okay. We have right now 2 contributions, and then I will close it, and then we will have the poster session. For the poster sessions, there is a link that you can access, and there is the name of the contribution and the Zoom link that you can access and ask questions to the contributors, okay? In that case, you can go out and go inside every Zoom and talk, and you can share whatever you want. You can go until night talking, have a beer, whatever you want in the poster session. But beforehand, we have to make Sikong Xian to go to the stage. Remember, 5 minutes. I will ask everybody to turn off the camera just in case we don't break everything. And please, Sikong, I think I'm
Yes.
saying right. Yes.
So can you
Thank
see
very
it?
much. Yes, perfect.
Okay, good. Hello, everyone. My name is Chong Xian. I'm a developer from KUKA Robotics. In the scope of this workshop, I would like to introduce unsupervised shape-like learning in back-of-word sense as a way to extract human interpretable features from time series data. The touch here is not the input from the tactile sensor, but rather the measure torque at each robot joint axis. And we use these shape-like features to make sense of touch. Basically, it is an unsupervised feature learning or selection algorithms. That is to select or learn features without class labels, or as Professor Denver has said, feature extraction on mono-modeled tasks. A quick introduction about what is shape-like learning. So as you can see here on the left, there's a video running. So the LBI EVA robot tries to slide the lever up on the switch mounted on the electrical cabinet. Here, 2 different errors can occur. The switch is already on. That is, the lever of the switch is already pointing up, or the switch is broken, where the lever cannot be easily recalled. We record the external force on the Cartesian y directions, and the trajectory representing 3 different situations are presented on the right. That is, switches normal, switches broken, switches already on. And we can see that these 3 traces distinguish themselves by the bold marked subsequences. We refer to these bold marked subsequences as shapelets due to their different shapes. We then transformed the original time series data into the similarity measurement into these shapelets and use them as features. To evaluate the goodness of the feature selection algorithms, we compare the accuracy of clustering algorithms on these selected features. The pipeline is illustrated here on the right, where 2 different ways to perform clusterings. One is that the input data is directly fed to the clustering algorithms, whereas on the second way, feature selection or learning algorithms are first employed, and then only the reduced features are fed to the clustering algorithms. To ensure comparability, for different feature selection algorithms, we always use the same clustering algorithms, that is k-means at the end. Using this pipeline, we obtained evaluation results. We measure the clustering accuracy using rank index, which ranges from 0 to 1, with 1 as the best. For each evaluation, I use the data set from our robot switching application, as I have shown on the last slide, and also the UCR public data set to evaluate different feature selection algorithms. I chose 3 from them. One is the unsupervised discriminated feature selection, that is to select the significant data points from the input time series and use these significant data points as input for k-means. Another one is the unsupervised shape-like learning algorithms, where shape-like learning and clustering are performed simultaneously, and we can directly obtain the cluster labels for evaluations. The last one is our proposed method, neural network with T stochastic neighborhood embedding layer, where we extract the shapelets and transform the time series into the distance measure to this shapelet, and then apply k-means. It's to note that for each data set and each algorithm, the best result is selected after hyperparameter tuning of the corresponding algorithms. I highlight the best RAND index scores in bold. As you can see here on the table, in the table on the left, we can observe in most cases using our proposed method neural network with embedding layer as feature selection algorithm before applying k-means can help us achieve better clustering results. Can achieve better results, and on average, 16.7% of improvement on clustering results can be achieved compared to without applying any feature selection algorithms beforehand. That would be all for my brief introduction about the workshop paper. Thank you for your attention. If you would like to know more technical details about the proposed methods, as well as a possible collaboration with ASCUCA, you're welcome to join our poster session. If you are not watching this live, you can also reach me by email. Thank you.
Okay. Okay, thank you very much. So this is the Zoom for the session, but it's also in the chat and also in the website. We are losing the people around. Remember, the poster session is super important. Okay, we go for the next one. That is who is going to present, Ali or Gerardo?
Yes, Ali.
Ali, okay.
Hi.
Ali, please go to the share. So 1 second. Okay. All right. So can you share?
Yes. So are you able to see what I have here?
Yes, perfect.
Good. Okay, so hi, this is Ali Gallaf from University of Glasgow. I'm here to present research about a pilot investigation into robotic self-awareness by Ali Gallaf and Gerardo Aragon Camarasa. Under the research conducted under a computer vision and autonomous system group in the University of Glasgow and supported by NVIDIA and Kisser. So our motivation behind this research that robots need to be adaptable and as the human do during doing a task. So based on this, we inspired by the Rochat's 5 level of self-awareness that each level has more confidence about the self while during the child development actually. So we hypothesize that level 1, which is the differentiation for artificial self-awareness in a robot, increases its self-certainty in unseen environment. And as we show here that mainly our research focusing on allowing the robot to know itself before actually interacting into the environment. So this is the main distinction, is knowing itself before interacting with the environment. Based on that, our paper actually has the first step toward the artificial self-aware architecture that we propose. And also it has the way that we process the different modalities that we use within our architecture and the groups that we created to validate our work and the architecture with the confounding signals. For this reason, we propose this neural network that it gives that ability of learning and doing the self-acquisition for a robot by processing the robot's perception and the proprioception in order to predict if robot itself or the environment, and to elucidate if the robots are really getting this artificial self-awareness, we plotted the histogram and calculated the mutual information across different groups. Here, as you can see, there is a joint groups, and based on the data that we have for the mutual information, there is no really major differences between each group that we created, despite the data set is really different, which gives us the confidence that the architecture is learning the robot to get into the self. And the general average classification among all the groups are 68.2 for the unseen data set. So in our conclusion, actually, we explored whether our architecture is able to provide the robot with the self, and yes, it is. It gives the robot the sense of self, which is our target, and this revealed by our experiment through different environment with confounding signals. The main limitation in our approach, which is associated with the level 1 that we inspired by Rochat, which is that the robot is not able to locate its limbs within the environment. And this can be solved by having level 2 into the consideration of the study. So please, if you are really interested in our work, come and join us in our poster session on paper 8, please. So thank you very much.
Thank you very much, Ali. Really interesting. So where we are, let me check where we are, but we are actually finishing somehow. So we are here. We are 1 hour later. That I cannot believe. No, half an hour later. That's good. So it's not that bad. So okay. So after this, what we have is the poster sessions. Okay. You have the link in the chat and also in the website. You can also retweet to everybody if somebody wants to join. I know that it's Sunday late. We have families somehow, and it's complicated. But it's for us, it was important that not only big speakers talk, but also people that they are studying. I think it's really important for the workshop to have people that they are really trying to start their research, right? And to learn from the ones that they already have some kind of position. So in that sense, I just want to thank you, everybody, and I want to especially thank the organizers. I have to say that this is a lot of work. This is a workshop. This is not a conference. I have to remember. But this is a lot of work for us, but we do it because we like it, and we wanted that you also have access to this kind of information that usually you cannot. It's a pity that we are not in Paris. We have the situation with the virus that hopefully it will be solved. Well, I don't know in the United States, but in the rest of the world, probably better. Well, we don't know actually how it's going to behave everywhere. So anyway, so I just want to thank you everybody again. Natalia, Mohsen, David Filiat, Tansu, Selikel, and all the people behind us, and also the ICRA, even if it's not online, and they tried to help, but they couldn't help us so much. The BMW group, the Donders Institute, where I also work, the ENSTA also from Paris, and that's it. So please, I will not close this one, because if you want to check the PDF with the Zoom access, I don't want to close it, but I will also pass through the Zoom posters, right? So we have here the poster sessions, and the important thing is, like, you can ask the question, discuss whatever you want to do, and if you want to move to another poster, you just disconnect and connect to the other meeting. Okay, you have in my Twitter also the PDF if you don't find it, and also in the website there is one thing that says poster session, and you can click just in case this goes off or something. So Natalia, you want to say something?
No, well, thank you to everyone who attended on a Sunday and given the circumstances. So thanks, Pablo, for taking care of everything. And yeah, I hope we can catch up with a real social at the next workshop. Thank you, everyone, for coming, and thank you all the attendants and speakers.
Thank you. People are thinking in the chat. We are going to stop the YouTube sharing, okay? This is all more or less over. So I will also stop recording. Okay, now I did it right. Good. So thank you very much again. I will place one more time the poster session, and you are free to move around, right? And I will also move around to the poster to see what is going on. And thank you very much again. I just say it many times, but really there were a lot of people in the Sunday listen to the screen, and I think that's important. Okay, so I also want to thank you, my student that was trying to help also in the chat, and everybody that was doing the maximum to help in that the Zoom works. Okay, so thank you very much. If you have further questions, you can always. I think I didn't cancel the Natalia. I think I didn't cancel the YouTube.